the slides and videos for these presentations, you'll be able to find them on the website later on if you need it. Okay.
Okay, thanks, Eddie. Okay. Okay, so Tay, do you want to test whether you can hear the audio?
I can ask people on chat.
Oh, yeah. Yeah, where they can hear it. Okay, test. Okay, great. Okay, thank you. Okay, good morning, everyone. So first, we want to thank you for coming to the tutorial for a comprehensive tool and the recent advancement toward real-world visual geolocalization. It's a long title. It's taken me a few times to memorize it. Okay. I happen to technical director at SR International. So I'm going to give the first talk. It's about introduction to general visual geolocalization. Okay, so here's the outline for this talk. First, I will define the definition for image-based geolocalization. And typically, the image-based geolocalization, there are two steps. The first step is code search. So I will describe the major approach and compare this approach. And then I will also talk about the recent trends that along some new work in this area. The second step is file alignment. So it's performed after the code search. Then after we describe the overview for these two steps, I will describe some real use case for the real world applications. And the conclusion will be made in the end of this talk. Oh, please find a seat. Oh, okay, got it. Okay, so image-based geolocalization. So for this problem, hold on. For this problem, that the goal typically is that by given a query image, right, you want to search over a region of interest and try to compute the 3D geodetic position or 3D pose, that including 3D position and orientation for this image. So that's a definition. So for this tutorial, that we focus on this problem. So basically just using a single image for geolocalization. Let me try to minimize this one. Hold on. I just minimize this. No. Hide. Okay. So there are many different applications using the image-based geolocalization. So for example, if you have a lot of images from the history, right, you want to label that the place where this image come from. And then the other application is to improve the GPS accuracy. So for a lot of industry application like a self-driving car, there are some environments GPS just not so reliable. So if using cheaper sensors, right, like a camera, and use the camera for the geolocalization, fuse those information can improve the overall navigation accuracy. And then personal photo open. Also for some pedestrian, right, if working inside the urban city, GPS typically is not so accurate. So if using the photo for the image-based geolocalization, that's a good application too. Okay, so there are typically two steps for the image-based visual geolocalization. The first step is code search. So code search basically that is predict the location for the query image. And then assuming you have a database for georeference data. And then in some fields, this step is also called place recognition. The second step is file alignment. So basically, after the code search can give you a candidate list of potential location based on the query image. And for each candidate location, treated as an initial 3D position, 3D pose, then you try to register the query image to the 3D georeference database to refine the 3D pose to get a more accurate 3D pose. So this step typically require detailed 3D information in the database, such as 3D point cloud from LiDAR or some detailed data, those kind of 3D information. Some fields is also called the Geo-Registration for this step. And currently, that in image-based visual geolocalization, there are 3 different categories: cross time, cross view, and cross model. So for the cross time, the difference is like the reference data inside the database is also taken from the ground viewpoints. So the view changes across the season, different lighting, different weather. But the query image is a ground viewpoint. The database image is also from the ground viewpoint. The cross view is like still your query image is from ground viewpoint, but your reference data is from aerial viewpoint, right? So for example, like a satellite image or the UAV image. The cross model is like your database actually is even using the data collected using a different sensor model. It's not a camera anymore. So it can be LiDAR sensor data or the OpenStreetMap. So this is just a map data. So you can see for these 3 different categories, the difference is like for the cross view and the cross model, the matching difficulty is even harder than cross time, because in addition to the viewpoint, ground viewpoint change, there are larger appearance change due to the different ground aerial viewpoints or different modalities. However, the advantage is like if you want to create the ground database for the entire world, right? Collecting the ground image actually takes a lot of time for some region. But the ground cross view, the aerial reference data, like a satellite image, actually you can get the satellite image for the entire world, right? So the availability of the geo-reference database is actually more popular, more easier to get reference data for cross view and cross model. So that means that there are some potential if you want to move toward to the entire world, right? Real world application. So that's why recent years you will see more and more papers that in the later 2 categories, including the talks that from these top researchers in this field today. Yeah. So for this tutorial, we will start from the cross time. Because the cross time among these 3 different categories, still this is the first one. So there are some ideas and methods actually when they develop in the cross time geolocalization problem, there are some methods can be reused or inspired for the other 2 categories. So for the cross time that image-based geolocalization, actually, even compared to the other 2, this problem itself still a very difficult problem if you consider you want to move this toward the real world application, right? Because the real world is dynamic with lots of moving objects and the continuous scene change. So if you want to develop a method that actually can be adaptive to the change in season, time of day, plotting the scene, actually it's very difficult. And in addition, if you want to scale the method for entire world, let's say you search the entire world for a real world application, right? Even for cross-time geolocalization, it's very difficult. Okay, so now we'll move to the first step, the code search. Okay, so typically in the code search, which is also called the place recognition in these fields, there are 2 major approaches. The first one is called the retrieval-based geolocalization based on image matching. So the idea for this approach is for each image, you try to extract the features and use one descriptor to represent this image. So assuming you have a database, you have the georeference data, the idea is that you will collect a lot of georeference ground image, and each image it is represented by an image description, right? A vector. So now you have a query image, you use the same method to extract the descriptor. Then you use this descriptor to search the entire database. So the problem becomes a database retrieval problem, right? You basically just compare this descriptor against all the descriptors inside database. Then based on the similarity, you get the best match based on which the vector is the closest one to the query image, right? So based on nearest neighbor search. So this approach is called the retrieval-based geolocalization. So there are a lot of works that in this field. So one major difference among different methods in this approach is that, okay, what kind of visual vector you use to represent this image. So for example, in the beginning, people start to use the local feature descriptor, the traditional feature descriptor, right? Like one single image, you extract many different feature points. And for each feature points, like the corner feature points, you get the local neighborhood that the pixels and extract the descriptor around it. So each image you can represent it as many feature vectors, visual detail point with descriptors to represent that image. And then based on this approach, there's another approach is like try to aggregate the local feature descriptor. So the idea is like for each local feature descriptor, you project it into a higher dimensional space, right? It's called the embedding state. Then aggregation is like you try to get come up with a single descriptor by summarize all the corresponding feature descriptor in that space. That's called aggregation. So for example, Villa, the FB, and the bag of words are all from this approach. Then there's also a global descriptor. That means that you directly use one descriptor to summarize the entire image, right? Like the color histogram or the GIST. And then from all this traditional image representation, the recent years is all moved to the deep learning approach. So one famous example is the net ballad. So net ballad, the idea is like for the ballad that two steps, the embedding and aggregation, basically use the differentiable operations for this step. Then they have end-to-end network can train for it and get good results. So basically, this summarizes that this approach. So there are many works that in the retrieval-based approach. So the representative work is that the Iron2 GPS and Iron2 GPS deep, because the Iron2 GPS was the first attempt to apply the image retrieval to the entire world, the world scale geolocalization problem. So Iron2 GPS basically is like still is based on the traditional features. So they, they collected 6 million of the training images from Flickr, and then they evaluate different kind of the traditional image representation, like a color histogram, geometric context, and the GIST. Yeah, so basically they use that for the image retrieval but applied to the world scale. And after Iron2 GPS, the Iron2 GPS deep basically is a deep learning version for the Iron2 GPS. So the idea is like they extract the image representation using the deep learning network. So basically it's a convolutional neural network. I think they use is the convolutional layers from the VGC16 network. Yeah, so it's a traditional one. But they basically use that to extract the vector to represent each image using the deep learning method, and then apply the same K nearest neighbor search among the database and outperform the Iron2 GPS. So these two are the first attempt to move the retrieval-based approach to the entire world scale geolocalization problem. So for the newer work that in this field, I highly recommend the next talk that from Dr. Carlo Mason and the Dr. Gabriel Burton, because they wrote a really good survey paper in this field. Yeah, so and also they have the newest work that in recent years. So the next talk that will give a more deeper understanding about new work in this approach. Okay, the second approach to the coast search is a classification-based geolocalization. So this is a different approach compared to the retrieval-based geolocalization. So the idea is like the formulation is totally changed. they formulate the geolocalization problem as a classification test for the entire world. So basically, they first put the world map and divide it into the grids using, for example, the Google S2 library. So after they divide into many different cells for the entire world, right? They basically treat the geolocalization problem as a classification. You give a query image, then classify which cell this query image belongs to, right? So then the predict geolocation for the query image is the center of the predicted grids. So that's the general idea for this approach. Okay, so recent years, there are many works in using this approach. So I want to talk about the PlanNet, because the PlanNet is the first implementation for the classification-based geolocalization. So same idea is that they divide the world map into different cells. So they start with 6 cells. Then they recursively to further divide the cells, right, based on 2 parameters. The first parameter is T1. So in their experiments, T1 is 10K. So basically they keep dividing the cells and until each cell that contains more than that certain number, the 10K image, right? So they don't divide the cell that if the cell is small, that the training data is less than 10K. So that's how they divide the cell. And then they remove all the cells if original content less than minima of the 50 T2 photos. So basically, why they use this approach is like in this way, when they divide the cells among the world map, right? Although some cell is bigger in the cover region, some cell is smaller, but overall, all the training data in each cells are balanced, right? So in this way, that when they train the model for classification, they actually can put more results in some regions that although those regions that maybe it's not a bigger region, but they have a lot of training data, right? So they divide it into multiple cells, so they can pay more training attention into it. And then this way that if you do have the small cells, that right, then if you got a correct prediction for the query image from that small cell, the accuracy actually can be comparable to the street level accuracy, right, when the cell is small. So this is the first work for this approach. Then their classification model is trained a convolutional neural network based on the inception architecture with the Bayes normalization. Still is a typical way to do that, but the good thing is that actually this is a first implementation for this approach. So actually it opens a totally new direction. Okay, but if you look at the PlanNet, what they did, right? One limitation is like they will have some large cell, and then even the correct results should from the large cell, but then when they return the prediction is centroid for that large cell, right? So that the accuracy actually won't be as good as some small cells, right? But the trade-off is like if they want to divide more small cells using that large cell, then the training data, right? You won't have sufficient training data for the small cell if you further divide it. And then in addition, if you have more cells, then you will have more parameters you need to train. So actually you require more training data. So to solve this trade-off problem, they come up with a combinatorial partitioning strategy. So the idea for this strategy is like, if you look at that picture, so in the left side, they can come up, for example, 2 different partitions for the entire world. And these 2 partitions that each cell contains a similar number of the training data. So by merge these 2 partitions in the right side, actually they generate 14 different distinct cells, right? So then combine these 2 partitions, they have 14 different cells. But when they train the model, they don't need to train these 14 different cells. They only need to train the left side. Left side actually is 5 multiplied to 2, so only 10 cells, right? So the idea is actually if they have more partitions, actually they only require to train a smaller number, fewer parameters, right? But they can still use that combination to actually cover that more fine-grained cells using this approach. So the advantage is like in this way, using the left side, they still maintain the balance of the training data in each cells, but actually they can reasoning more different cells after they combine it. And the training model, actually, the classification model actually is very similar to the PlayNet. The difference is like they use the same inception encoder, but in the end, they have multiple branch for each partition, right? So during the reasoning, actually, it's like based on the, for example, I think they use 5. Totally in the experiments, they use 5 different branch. So 5 different partition. And then in the right side for each distinct cell, right, they get the classification result for all the branch, normalize the score for each classifier, they summarize it for that particular distinct cell, right? Then the second thing is like, okay, I really want to minimize this. Yeah, I think I click it, but why it come back again? Okay, and then when they predict the location, right? Now it's the highest scoring cell. They don't predict using the central point for that cell. They predict using the average position of the training image. So this actually is a smart change because assuming you have a big cell, right? Maybe in the middle is the ocean, right? And your land is in the border. So if you use in the middle location, actually your location accuracy will be big, right? So they use the average of the training data. So this basically summarizes the CPlayNet. Okay, so a comparison between the retrieval-based approach and classification-based approach, right? So the first one is the 5 scale. So the retrieval-based approach, actually, it depends on the training images inside the database, right? So if you have a region, you can have a very dense training images. In the final scale, actually, your accuracy, if you get the correct database image, your accuracy can be really good. But then for the classification, right, the final cells that if you want to have very small cells for the classification and achieve 25 that kilometer about city level classification, that you do need to increase the number of the parameters to train the model. But then compared to the worldwide modeling, right, the retrieval-based approach that if you want to apply this approach to the entire world, right, you do need to collect the training image, right, and have a sufficient sampling among the world. And then in this approach, the database, you need to store all the vectors to represent all the images, right? So the storage is a consideration. On the other hand, the classification is a different formulation, basically just a classification-based method, right? So you don't need to store all the vectors. So that's a different formulation. The environment that this is still under debate. I think the retrieval-based approach that for some methods do require some overlap between query image and database image. So if you have a spatial landmark, that's easier for the retrieval. The classification, basically the formulation, try to generalize across different environments from the cells. So yeah, on this, I think for the past few years, there's a trend that people, researchers start to think if we combine classification and the retrieval approach together, right? So basically, maybe use the classification-based approach to first try to get a candidate of the cells. Then for those candidate of cells, if you have the database image, then you apply retrieval-based approach. So by combining these two approaches together, maybe you can improve both the generalization and the accuracy. So that's something that to think about that in the future. And then for these two approach, actually the newest work in code search that we have 2 additional talk that in the morning. Yeah, so basically that I also highly recommend you guys stay to listen to these 2 talks. Yeah. Okay, so now we are going to talk about the trends for the code search. Okay, so here is a comparison for the recent years that some works that I think mostly from the classification-based approach to the cost search. So these days has many benchmark data set that has covered the entire world, right? So this method actually can be test on this benchmark data set for the comparison. So between 2018 until now, so there are many works in this area. So here that shows it's a visual geolocalization accuracy comparison. So basically, assuming there's a radius, right? In this way, currently the radius is set 25 kilometers. So basically, it's a city level visual geolocalization accuracy. Then you have a query image, right? Then how much percentage of the query image actually the prediction compared to ground truth locations fall within this radius, the 25 kilometers, right? So you can see, for example, 2022 translocator on IM2 GPS data set is 48.1%. The query images fall within 25 kilometer radius compared to ground truth location. Yeah. So here's a comparison. Yeah. Okay, so based on these works, right? So there are several trends that we can see from this work. The first trend is like an incorporation of the scene types. So the basic idea for this trend is like because now everything moved to the worldwide, entire world geolocalization, right? So there are many different environments and many different things. So people start to think, okay, if I just train a general model to cover all different environments, might not be sufficient. And actually, different kind of environment may rely on different kind of visual features, right? So the basic idea for this one is, okay, how about that if we can get some contextual knowledge about what kind of scene types, what kind of environments, and then based on this kind of scene type environment, we try to extract particular features or train a particular network to handle it. So if we move to this direction, the entire accuracy can be improved because you have a special way to handle different scene types. And there are some works in this area recently. For example, I think one famous work is the ISN, Individual Scenery Network. So in this work, basically, there are two major contributions from this work. The first one is like this is a classification-based approach, right? But in addition to just one single label of the sales partition among the world, they have a hierarchical 3-layer actually for the different partition among the world based on different spatial resolution. So when they try to learn the geo-estimation, actually they are not learning from just a single label. They learn from the 3 different labels and use that, use a multi-partition loss function to train the model and use that for prediction, and that improve the results. Because the higher level actually, some information can be also help the lower level. So in this way, that actually improve the accuracy. And then the second contribution is what we just described, the scene types, right? So basically, they try to classify the scenes based on the scene types. They use the ResNet model, I think it's trained from the place2 data set. And in the original, this scene classification is already pre-trained, I think 60 million training image for 365 different place categories. So during their experiments, they use 3 super scene types, urban, nature, and indoors, used for the to train the ISN. And then they treated the scene classification and the geoestimation as a multi-task problem. So they have a multi-task network, try to train 2 classifiers for these 2 tasks, complementary to each other. So the total loss actually is a summation for geographic loss and scene loss. So basically that's the major idea, that how they incorporate scene types into their work. Okay. The second trend is like to use the scene semantics, right? So in recent years, there are, I think it's a huge advance in the scene semantic segmentation fields. So basically the idea is like for each image pixel, you try to classify into one of the pre-trained class, scene class. For example, you can see the right video, right? So each pixel you can be classified into the road, the sky, tree, or vehicle, or the pedestrian, right? So the idea is like when you do the geolocalization, in addition to the appearance, you want to also use the semantic information to improve the geosegmentation. And the semantic segmentation actually can also guide the extraction of visual features, right, to help the geolocalization. For example, the global layout, right? Different place may have a different scene layout. And then second thing, the good thing is like it actually can separate the foreground object from the background, right? So typically foreground object like cars and people cannot tell much about the geolocation for that image. So you want to focus more on the background classes, right? So using the scene semantics can give you some indicators about the foreground and background. Okay, so in both the retrieval-based approach and the classification-based approach, there are representative works to use the scene semantics. For retrieval-based works that sent, I think it's in BMVC 2019, actually from SRI, we also use the scene semantics to improve the results. So the idea is like, in addition to appearance image, we also get the semantic segmentation from the image. Then you put both information queue into embedding space, Euclidean embedding space. Then the training data we have is 2 million images collected from more than 2,600 static webcam. So these webcam are distributed among the entire world. So each webcam you have more than 1 year of the data to look at the same place. So that data actually can indicate the scene change and weather change over time for a particular space. So when you try to train this embedding space, basically you try to train all the different image vector belong to the same place, should be close to each other inside the embedding space. But if the image vector are from a different place, during the training, the embedding space should be far away, right, from each other. So the idea is like you train this embedding space using this webcam data. And then based on the experiments, right, because in addition to appearance, we also get the pixel level semantics information as an additional cue into the embedding space. And from the experiments, the semantic information actually can improve 8 to 15% absolute improvement accuracy, depends on which data set, which benchmark data set we try. And then the other thing that we did is like we also applied the attention module to combine these two information cues, appearance and the semantics. So the idea is like it try to encourage the network to try to pay attention to the important information from the image, which is more robust to across the scene change for a particular place for geolocalization, right? So basically, it try to pay attention to more like a background classes automatically instead of pay attention to the foreground cars or the pedestrians. And then by using the attention, we also use the channel attention and cross attention. Basically, you attend each different cues, but you also fuse them together to try to pay attention to which part help to the other cues. So attention module actually improve additional 4% of absolute accuracy in this work. Okay, so this is a demonstration video. So after you train this embedding space, right, you go to a new city. So then you collect the georeference ground image during the nighttime. Then in the daytime, this is a 2 kilometer database. You just drive around. And for each image, you query the database and say, okay, where is this image? And for top 4 return results from the database, if the distance to the ground truth position is within 6 meters, with green highlighted it. So you can see that this basically is a single image retrieval, right? So overall, that actually the green highlighted one is pretty consistent for the top 4 match. Actually, this is a pretty difficult problem because even when I drive around, if you ask me which daytime image corresponds to which nighttime image in this city, I mean, it's difficult for humans, but actually the system can figure it out using this approach. And the results can be further improved if you check the consistency across the sequential video frames, right, based on the retrieval results. But just for evaluation, now it's still is just an individual single frame query results. Okay. And then the other representative work is from the classification-based approach, translocator. So translocator actually is recently, I think a few years ago, that about using the semantics. So basically, they use a serial vision transformer as the backbone. So vision transformer, I think now is a very popular serial network architecture. So originally it's inspired from the language processing, right? So they apply this for the image data. So basically, they need to split the image into a sequence of a 2D page, then put them together, fit into the transformer. And then they add the classification token, right, to the sequence as a typical BERT approach to the transformer. So basically the major innovation here is like they have two different branch using the transformer. One is using the appearance information, the other using the semantics information. And then transformer basically has many blocks connected together, right? And each block has a multi-head self-attention mechanism and with the feed-forward network. So when they do these two branch, right, their major idea is like for that transformer two branch, they have many blocks. So for each block that basically the classification token they consider as a abstract global feature representation. So basically each block that they will just connect the CLS token together from two branch, then they propagate it to the next one, the next block. So it's a very simple way they fuse information together and keep propagation. And then in the end, after the transformer encoder out, they have a fusion module. Basically apply the model attention generation to attend different module, the appearance and semantics, then combine the weight together for the final results. So basically, that's the high level idea for this work. Okay, the third trend is a multi-model geolocalization. So this trend is like using single image search the entire world is a very challenging problem. So people start to think, could we use additional information such as a text label to improve the geolocalization? So for example, if you look at image, right, there are a lot of labels to tell you which, like a city, those things. Could we use this as additional information to train a model? So the representative work, one is the G3, geolocation, guidebook and grounding. So this work is very interesting. It's like it was inspired by a game, the web game called the GeoGuessr. I don't know whether you guys have played this game. It's very interesting. Just on the web, right? So people try to look at those video frames and tell, okay, I think this image is from which place, right? Which city. So it's like a gaming on the web, but it's so popular. So it's a web community now start to share information about okay, what's the cue you can use to guess that which this image from which country, right? So then on the web community, there's some guidebook from those discussion about okay, how to guess that which this image from which city. So this work basically they create the data set, include the image and the list cues. Right, these cues, how to guess that this image from which country. And then, for example, this is an example about the cues that they collect from the community, right? For example, this image is from Thailand. And then there are some people, some experts on the web to say, okay, you want to guess this image from Thailand, right? Thailand, typically, the cars is driven on the left side. The roads with the yellow center lines, and then typically there are two-story houses in Thailand country. So these are some tricks that people share that on the web community. So basically, G3 uses this idea, right? They have the encoder to extract visual from image, but they also have a text encoder to extract information from all these tricks among all the countries, right? So So basically now you have a query image, right? Then you give the query image. They basically try to use these extract image features and the extract cues for different countries to try to help to predict which country this image comes from. And then if they lay out their results compared to ISN for the country label classification, they outperform it. So they prove, okay, these cues, right? You do have some knowledge base about to guess which image from which country, it actually helps. Yeah. So it's a very interesting work. Yeah. So it actually opened a different direction that for the image-based geolocalization. And the other representative work is the IN2CT. So this is also a very famous work like in this area. So IN2CT basically is a multi-model learning kind of idea. So basically they want to learn information from both image and the text and use a clip, right? The contrastive language image pre-training model. So basically the idea here is like, okay, for the image they extract the features, right? They also have a set of the city labels, right? They also extract features from it. And they use the prompt, like, okay, for each label, each city label, right? They use a prompt like to encode the information like in city to city from city. The different kind of combination, then fit in the text encoder. So now for each query image, right, during the test time, based on the correspondence, the predict probability correspond to different city labels, they select the highest probability one to predict the city location for the query image. So that's the idea for IN2CT. So here are some results, right? So basically you can see the left side, they show here top 5 prediction, right? Which city it comes from. And there are some successful examples and some failure examples. But basically, IN2CT is a worldwide scale and using the multi-model learning combine both image and text label for the geolocalization. Okay, so we are going to talk about the second step file alignment. So now, assuming that you run the code search, right, you get the candidate list of the location for the query image. The file alignment, the idea is that you want to verify that candidate location, whether it's accurate, and also refine the 3D pose, get the very accurate 3D location orientation. So for this step, you do require you have 3D georeference data or map inside the database. So the first step we already described is, for example, image retrieval. You search the database, like for code search. Then the second step is like, okay, based on your candidate returned image, you try to detect match image features to get the correspondence. And then for the georeference image data, the feature point, you also have 3D data inside the database, right? So the final step is like, okay, based on the 2D and 3D, you can compute the camera pose, 3D position, 3D orientation by resection using this 2D, 3D correspondence. So it's a very typical approach to do that. So you can get the finalized, refined 3D pose for the query image. So basically, this summarizes the file alignment steps. Okay, I'm going to talk about the use case. Okay, so now we have a very a high-level overview about the code search, different approach, and file alignment. So in the real world, actually, so far for the past years, image-based geolocalization has many different real-world applications, and actually did prove there's a huge potential for this research area. So the first one is navigation for self-driving cars. So self-driving car, this topic has been very popular over many years, and people keep a claim it's a solved problem, but actually it's not so easy as many people thought. Yeah. So for example, that currently now the self-driving car industry, they do require GPS and very high quality, big, expensive LiDAR to build a map and to match the map, right? So each LiDAR can be more than $10K, right? So if you want to self-driving car to be very popular, that means that when you sell one car, you need to sell one additional LiDAR. It's very expensive, right? That's one reason you cannot make it a low-cost popular solution. And then if you don't use 3D LiDAR, the GPS quality actually is pretty bad, especially in the urban cities, right? So recently there's more and more research will try to use a low-cost sensor like camera for geolocalization, and it fills information with GPS, so it provides a lower cost solution. And then the 3D geo-reference database can be ground image or aerial image or even LiDAR data, right? So one approach is like you can have an expensive LiDAR to build a geo-reference map beforehand, right? But then when you have the self-driving car, you use a camera to match to the LiDAR map for geolocalization. In this way, you can reduce the cost when you sell the self-driving car. So here, that basically shows some results we have. The bottom right is a video. Actually, it's during the night time using the low light cameras. Actually, it's 9 o'clock at least Eastern time at night. So when I collected that data, I can barely see anything. It's too dark. But the low light camera still can see it pretty well. And you can see that just based on one camera and one IMU, that's the trajectory navigation results for that driving car. So pretty accurate. Yeah. Okay, the second application is the large scale augmented reality. So augmented reality basically is it requires very accurate 3D pose estimation for the moving platform. Because the idea is like from the user's view, right? You want to insert the virtual object or virtual icon like those red dots into the real things. So how you can enable that insertion is like you need to know the real-time 3D position, 3D orientation of your head, right? While you are looking around. Then you can insert the very accurate icons in the world to see through your display device. So if your localization result is not accurate enough, those red dots will have jitter or drift in the scene. But you can see that it's very stable there. It's very accurate, stable there all the time, even no matter how you move your head. That means your localization results and tracking result for your head is very accurate. So GPS and traditional SLAM approach actually cannot provide the required accuracy for this kind of localization to large scale augmented reality. They only can provide like a small scale, like a room label kind of thing for SLAM. For large scale AR, you do need the GPS combined with additional information, like a visual geolocalization for pre-built 3D georeference database. So that can give you the sufficient information for this kind of application. So Teddy actually will give a talk to talk about more details about this application. Actually. Okay, the third application is GPS denied aerial navigation. So now there's a very popular to have those small UAV flying around, right? So again, using the UAV then for like the delivery surveillance application, you do require the geolocation for that UAV, but GPS accuracy is not good enough for some application. So there are methods basically based on the image from the UAV. In real time, you do geolocalization, georegistration to a 3D database of the world. So you can see that's without GPS, just using that UAV image, you can register on the 3D map in real time to precise overlay the image onto the map. So overall, the accuracy without GPS is 3D accuracy less than 10 meters for this application. So this actually can be used for the surveillance and the delivery and also military applications. Okay, here is another use case. It's about let's see, georegistration of the video to the 3D site models. So it's for the surveillance too. So basically, you can see in real time the input image, right? That can without GPS, basically do the geolocalization, georegistration to align to the 3D model. Okay, so now we come to the conclusion. Okay, so before we make the conclusion, I want to give a quick overview about the agenda for today's tutorial. So we finished the introduction to the general high-level visual geolocalization. But after this talk, we will have a very good talk about the recent image geolocalization benchmark and large-scale real-world scenarios. And then the morning talk focus on the cross-time geolocalization. So the newest work in both the retrieval-based approach and classification-based approach that the CJ and Mover work will give two very good talks in the morning session. In the afternoon session, we will move to the cross view and the cross model geolocalization. So our director Rakesh Kumar will give an overview about cross view and cross model, code search and file alignment with the different real world applications. Then we have many good talks about the newest work that in both cross view and cross model geolocalization. Okay, so the conclusion for image-based visual geolocalization. So we did this tutorial 2 years ago that in CVPR 2021. The past 2 years, I mean, the biggest difference is that you can see everyone now move the problem formulation toward the real world, large scale, search the entire world. Yeah. So in both the commercial and the military world, actually, we see this is the trend and now becomes feasible. You can really use one query image to search the entire world and give accurate results. So now it's really that things move to, I think it's a very exciting moment right now. And it has a huge potential and a broad impact to many different applications. Right? So I think even for the new PhD student, it's a great research direction topics for exploration. And here I want to show one final demonstration video. So here is basically it's like even without GPS, right? You have the 3D LiDAR data as a reference database. You do cross-model code search and cross-model file alignment. So you can actually get a very accurate geolocation pose for that camera. So you can insert the virtual object inside the real scene. So by the right side, actually you can see there's some vehicle in the dot here. It's not real. But you can accurately put it inside the real scene because you have accurate estimation for your geo pose of the camera. Okay, so this is my final slides. Yeah, thank you for listening. Yeah.
Any questions? Maybe questions. We talked about this damage paper, where we're dividing like the maps in these different divisions basically. What do those divisions look like? So maybe could you also just like have some horizontal lines and then vertical lines? Use that as the division of the map?
Oh, okay. So the C-plan net basically use a combination, right? So in their work that they try to use the different kind of partition for that. So they basically I think they use some heuristic to define different partitions based on experiment. I think the final is like 5 different partitions.
Okay. Yeah. Would other partitions be possible? Like for example, like a really simple partition that basically just makes a grid out of the map.
Yeah, right. That I think that's also possible, but I think currently the trend, I forgot to put that in the slides. There's a trend is like when you try to define those region cells, right? Instead of just randomly divided or just based on some randomly seed, they want to define the boundary more aligned to the nature kind of landmark, like among the mountain, right? Mountain or among like the seashore, those kind of things. Yeah, so there's some work about like a semantic geolocalization using this boundary. So I believe that the future trend is like use more semantic information, not only to get pay attention to the feature inside the scene, also help to define how you divide the cells among the world for the classification approach. Yeah. Yeah. Thank you. Yeah.
First slide, you guide.
Okay.
Seems like a really powerful way to use like
yes. Right.
That's
Yes, yes.
that I know that
Yeah, yes, that's true. So,
human guidance systems.
right. Yeah. So I like this work a lot because I think it did open a new direction for many different applications. So at SRI, we also use this kind of approach, but for different problems. So actually, yeah, I think it has huge potential. Yeah, because basically you try to leverage some human knowledge, right, from the web, additional information to help a problem. Yeah, a world scale problem. Yeah.
On that,
Uh.
is the inputs guide in GeoGuessr aligned with the query energies and training?
Okay. So that's a good question. Let me go more detail on that. Okay, so when you have that query image in, right, you don't need to give any information about that query image. Basically, the idea is that they have an independent text encoder that already try to extract details from different countries, different fields, right? So the will be a limitation is that if these ground images come from a country, they don't have any fields on that, right? Then they cannot do anything. So currently, we dig into this data set. So apparently, what they did is like from that web community, when they discuss this online game, right? They got the cues from some particular expert that is a popular user, hard user that keep giving information on that. So they didn't spend much time to really clean out all those information. So I believe if someone spend more time to collect more users from the information from the community and clean it, that those cues can be even better. They currently just take those one or two very popular users from the community, put all their what they talk that into the cues. Yeah. Yeah.
I have some kind of fundamental question about the benchmarking.
Okay.
You talked about classification, and if you train a method for classification, it doesn't care about nearby mistakes. You know, you can just take a photo from a very close region, and you know, the benchmarking, the top 1 or top 5, again, that's safe. What happens if you get a very close region that's something maybe it would be similar? And is it reasonable to think that close or nearby regions are going to be localized, or the model will likely to do those mistakes?
This is a really good question. So what you ask actually is a major problem in this field that people try to overcome it, right? So the thing is that originally there are many methods in this area that the return match that doesn't really consider those the spatial relationship, right, among so even you get like, okay, this is the wrong resource or correct resource, there's no relationship to the nearby region or not. So there are some approaches to try to address this problem. So for example, that one way is like what we just described. When they align the cell, they use more like the natural boundary about that, right? Like the mountain or something. So across the mountain, the scene can be very different, right, for different cells. And then the other way is like they use the scene types, right? So for example, this image maybe it's not these correct cells, but maybe the candidate will most focus on the similar things, although their geological region may not be so similar, so nearby, but it's from the same scene type. There are also some approach try to combine the geolocation information for nearby cells, right, also with the scene types. So there are some ongoing research, but overall, I would say it still is a area need more work on that. So still, I don't think there's someone can claim I fully solve this problem. No, it's still very challenging. Yeah, it's a very good question. Thank you. Okay. Yeah. Thank you. Yeah. Well, thank you. Yeah. Okay, let me come mute. Mute.
Newton. Okay, let's see if it's working. Okay.
Yep.
Yeah.
Yeah, okay. I guess you can share me too. Okay. Welcome everybody to the second talk in this tutorial. I am Carlo Massoni from Politecnico Torino. And today we're going to be talking this presentation about urban visual geolocalization. This presentation is divided into two parts. The first part, I will cover up some some details about how we can build a pipeline for urban visual geolocalization. I would like to share some tips and lessons we learned from our experience. And in the second part, my colleague Gabriele Berton will discuss what are the problems when you want to scale this pipeline to very large applications and what are possible solutions. But without further ado, let's start with a definition. We already had definition before, so I will be very brief here, but just to be on the same page. What do we mean by urban visual geolocalization? So in general, what do you mean by visual geolocalization? We talk about visual geolocalization as the task of estimating the coordinates where an image was taken, so for instance, GPS or EDM coordinates, from its visual content. So for example, this is an image from my hometown. Clearly it's the Colosseum, but unlike landmark retrieval, we want just to guess what's the landmark. In visual geolocalization, we want to estimate the coordinates, so put this image on a map, basically. And the accuracy we expect from this prediction may change depending on downstream application or task. So for example, as we've seen before, in a worldwide image localization, we expect accuracy could be in the range of tens or even hundreds of kilometers. In the urban scenario, where we may want to use this as a step in the pipeline processing for autonomous vehicle, for instance, we may want to have an accuracy in the range of meters. Again, there could be further next steps after this for post estimation, so this may depend. In practice, usually we use an accuracy of 25 meters in the literature. Again, this may change. So how do we do this task? How do we solve this problem? Traditionally, and this is approached as an image retrieval problem for this kind of setting. So essentially, we assume we have a database of images collected from the area of interest. And these images are also geotagged, so they come equipped with a GPS or EDM coordinates, sometimes even with a compass measure. So this database of images represents our map, our knowledge of the world where we want to localize in. So when we are given a new image, what is called a query, we want to localize, basically what we do is that we compare it to the database images, then we retrieve the most similar images from the database together with the metadata. And these results basically are our hypothesis of where we're localized. And to do this, what we need to do, as we've seen in the previous talk, we need to project these images into embedding space, or to essentially extract a vectorial representation from these images, what we call a global descriptor. And then we can compare these vectors one with the other using a nearest neighbor search. So this is all very intuitive, very simple, but in reality, there is a lot of nuances here. They're often neglected, and that's what I want to talk about. Because if you change some little things, some engineering choices, we can change the results drastically. So for example, here is a simple example where we use a very popular method. Network is one of the fathers of modern geolocalization. We take this model, we train on a data set called Pittsburgh 30K. We test it on top 24/7. And what do we see here is that when we take the vanilla method as it is, no modifications, then we get a performance score. I recall that one is 63.4. But then if we change some little things, for instance, the scale of the images, we change a little bit of the data augmentation, or how do we do dimensionality reduction, then the results can vary a lot. So this tells us that all these engineering choices that we often disregard, we don't care about it, they actually have a very big impact on the results we achieve. So this prompted us to go and do a very large benchmark. We want to try and test all these different choices and what's their impact, because this can give us some guidelines for how we build this pipeline for our applications. And the generic pipeline we consider for this study is represented here in this image. There are two main parts to it. There is a train time part where we basically want to train a model to extract these global descriptors from images. So essentially, we have a feature extractor, then we have an aggregation layer that takes the features and generates a single vector out of them. And then at this time, we use this model to basically extract these descriptors from the images. In the database images, we usually do offline, and then the query we do it online, and then we compare them with a nearest neighbor search. As you can see here, though, although it is quite intuitive, there are a lot of different things we can change. They are represented here as a blue blocks. So scaling, augmentation, how we crop images, and all these factors affect the results. And so what we wanted to do is to investigate individually each block of this, each of these engineering choices to see their impact. And how do we compare the results before we're going to look at them? In research here, we have probably a bad habit of comparing methods and results only based on some performance metric. So for instance, in visual localization, usually we use the recall at end metric, where we basically measures the percentage of queries where one of the first end retrieved results is an accurate match, essentially. So this is just pure performance, because what we care often in research is to show we have a better performance. However, in practical applications, this is not the only thing we need to care about. Actually, there are other factors that are extremely important. So for instance, what's your CPU and GPU constraints? How much budget you have in terms of memory? What's the latency that is required by your system? So if you need to have real-time or near real-time processing, that's extremely important. So we need to look at all these things together and then find perhaps a good trade-off between our performance and these other factors. Another important factor to consider when we want to build a pipeline is the kind of data set that we are working with. And in the urban application that we usually work with, these data sets are always built in a sort of systematic way, where you equip a vehicle with an onboard camera, you drive around, collect images. More often than not, you drive multiple times across time, as discussed in the previous presentation. So you collect images across different seasons, day and night, and so on, and then you build your data set. However, although all these data sets are more or less built in the same systematic way, there are a lot of differences from one to another. So when we need to verify how our pipeline works, we need to pay attention to how it works on different data sets. So for instance, here we select a selection of 6 data sets. As you can see here, these data sets vary in very different ways. So for instance, we have data sets which are rather small with 10,000 images, and others which go over 1 million images. So there are several orders of magnitude of differences. You can have different sensors, for instance, RGB camera or grayscale camera. You also can have a difference in the way the camera is mounted. So for instance, MSLS and San Lucia, they use front-facing cameras. So the camera only sees basically most part of the road, and then a little bit of the sides of the streets. Whereas you have other datasets where you can build they're built using panoramic images, such as PITS30K and TOP 24/7. So in this case, you also get side views. And in a urban scenario, this is very important, because in the sides of the streets, that's where you have buildings which are mostly informative to recognize where you are. Another thing you can notice from these maps, in some application may want to build a dense sampling of a whole neighborhood, so collect images on the streets. In others, like Einstein and St. Lucia, you may collect images only on a certain route. For instance, if you want to build an autonomous shuttle application, you only care about that route, so you don't go collect images all around. So when we need to evaluate our pipeline, we need to be very conscious about what's the data set you're working with. Okay, so now let's look a little bit about, as I mentioned before, how these different engineering choices, they affect our pipeline. And let's start, of course, from the feature extractor, from the backbone. And we know that in visual tasks and visual applications, the deeper the backbone, the better results you get, of course. But as I mentioned before, this is not the only thing we should care about. There are other factors. As you can see in this diagram, in these charts at the bottom. So here we plot on the vertical axis the recall at 1, which is our performance metric. On the horizontal axis, we have floating point operations. And then the different markers represent different architectures, so backbones and aggregation layers. And the size of the marker is indicative of the dimensionality of the descriptor, so of the global descriptor that represents the images, which is important because these descriptors, we have to store them in memory when we want to do a nearest neighbor search. And so the bigger the descriptor, the more memory you need. Again, this is another constraint which is quite important in real world applications. So if you consider all these factors together, then you see that performance is not the whole important thing, and you really need to find a good trade-off between what you can spend in terms of your computational costs and what's your expected accuracy. And we did a lot of tests, and for instance, we found out that ResNets actually work quite well in this sense because they provide a good trade-off between accuracy and the cost, particularly ResNet 50. But we also tested several different transformer architectures as a feature extractors. And we noticed that they are okay, they are viable choices, particularly compact convolutional transformers, which are quite lightweight. However, there is one more thing you need to be careful about when you choose your architecture, and that is when you want to obtain the optimal results, you need to investigate exactly, for instance, where to crop your architecture. And this may not always be trivial. So for example, with ResNets, we found that quite consistently, the best results were achieved when cropping at the 4 convolutional layer. These are across different datasets. With transformers, we didn't find such a recipe, so it was a lot more difficult. So that means for you, if you want to develop your pipeline, you need to plan in advance and keep in mind you need to do a lot of experimentation also to find the best configuration. And this configuration may not work when you change dataset, when you change your field of application. So that's something you really need to think about. Let's say we have chosen our feature extractor, so we move forward. We want to aggregate these features to produce a single vector. And let's say simplifying, you can say there are 2 ways to do this. So two families of approaches: clustering-based or pooling-based. Now, for clustering-based, for instance, let's look at NetFile, which is, as I said before, one of the most notorious approaches. The idea of NetFile is simply to cluster local descriptors and to form a global descriptors from these. So for example, let's assume we have a fully convolutional network as a feature extractor. The idea is that we can take the output tensor of this network and then interpret this as a set of H times W local descriptors. So in a sense, you can assume these are as a sort of extractor of local descriptors that are densely sampled over the image. So there is no key point detection here. So what the network layer does is that it clusters these descriptors via soft assignment with respect to vocabulary of visual words, which is built beforehand. And then you compute some residuals of these local descriptors with respect to the cluster centers or cluster anchors that you want. And then you basically aggregate these local residuals. And in the end, you get this vector, which is k times t, where k is the number of clusters and d is the dimension of your original local descriptor. So it's a little bit articulated as a method. It works quite well. On the other hand, pooling solutions are much simpler. So the idea is basically, as you can see this image, you have an output with different maps that you summarize each map with one value, for instance, with a mean pooling or max pooling. And then in the end, you get a vector that is dimension d. So not anymore k times t, but it's smaller. And the most popular method, for instance, used as a pooling aggregation is GEN, so generalized mean pooling, that generalizes both max and mean pooling. So let's look at how these perform. And we tested this and also other aggregation methods we are not going to report here. And we found that in general, clustering-based approaches, they tend to perform better. However, they are more costly. So GEN pooling, for instance, is much more efficient because, as you can see here, it produces natively global descriptors which are smaller in size, which means so you may need lower memory. But also we found out that when you train a method with a pooling solution on a large heterogeneous dataset, then the difference between pooling and clustering gets much smaller. And also we found that in many cases, GEN pooling actually performs better than a clustering-based approach. So you can see here, when we train MSLS, which is very heterogeneous, has 1.5 million images, then with GEN we can get results on several datasets like Pittsburgh, San Francisco. It actually performs better than using NetFile or other clustering approaches. So this tells us that when we want to go towards very large scale application with 10, hundreds of million images, probably we should look into a pooling solution. That's what Gabriel will tell in the next presentation. Then, of course, we have this model, we have to train it. There are different ways to train this model. But in general, let's say we resort to contrastive losses to train the model. There are many different ones. The attributed loss probably is the most notorious. It was introduced by NetFlood. The idea is quite intuitive. So we have a training query, and then for each training query, we also select some positive and negative examples. So positive example is an image taken from the same place, so it represents the same place. A negative example is an image taken from a different place. And basically what we want to do with these contrastive losses is that we want to basically force the model to push close together the representations learned for the anchor and the positive examples, and then push far apart the representations learned from the anchor and the negative examples. And usually you also might want to select a margin to spread this. So this is quite intuitive, but actually it is quite crucial the way you select these examples. Sorry. So you can see here on the left is a simple naive example where you have a query in blue and then the positive in green and the negative in red. So these are push selection because the positive and negative examples are already let's say, discriminated from the model, already far apart from margin. And so that means the loss here is zero and the model doesn't learn anything. So it is crucial to select these examples properly. And what's tricky is that this selection depends on the representations, which will learn and change during training. So that means we cannot just select these examples offline once for all and then don't do it anymore. We need to repeat this process of selecting these positive and negative examples during training, and that's what we call mining. And this is something which is quite expensive. So for example, let's consider here we are looking at an example where we are doing some negative mining. You can see that if we mine the examples on the full database, the complexity in space and time to do this operation scales linearly with the number of images in the database. So that means if you have a budget of time available for your training, when the database becomes very big, then you may not be able to complete the training in this time. You can see here, we couldn't complete the training on MSLS, which is just 1.5 million images. So what can we do here? Well, one mitigation solution will be to use a partial mining as introduced by MSLS. So it means you select only a subset of the images in your database, and then you only mine this subset of images. This, of course, the advantage that the complexity is fixed, doesn't change with the size of the database. But we also found out that this actually produces quite good results comparable to the full mining. So that means probably full mining is not really necessary. However, when we want to go to very large scale, so past 1 million, past 10 million, even hundreds or billion images, maybe we really need to look for other ways to this. There are other methods to, let's say, simplify the mining operation. For instance, GSV cities propose to, let's say, compute offline a sort of positive and negative examples of filtering the database. We are in this conference. There's another paper from Maria Levi Avellina and colleagues, which introduce some great similarity to perform this choice. And later, my colleague Gabriele will discuss also how we can avoid mining altogether with some other approaches. Okay, so now we have our model, we have trained it, and then at test time we need to do this nearest neighbor search. And this is something that in research we often neglect, because we tend to perform a exhaustive nearest neighbor search because we only care about the performance metric. But actually, this is quite an important step for practical applications, because as you can see on the plot on the left, here we are plotting the time required by an exhaustive KNN to perform a single match. These three lines, colored line, and the dashed red line is the time for the extracting the features. As you can see, the time for extracting the feature doesn't depend on the number of images in the database, but the matching time it does, and grows linearly with the size of the database. So it means this becomes the bottleneck in terms of latency when you want to scale up your database. And again, you can see here already with 10,000 images, this starts to become the bottleneck. So what can we do to improve on this? What you can do is that look at some, let's say, quantization and also indexing techniques in order to get some advantages. And I encourage you to experiment with this. So here you can see some examples where we tested several methods from the FICE library. And you can find some recipes to get, let's say, the results you expect with your budget of resources. So for instance, let's say you have a limited availability of memory and matching time. So we can see here, this dot here, the blue dot, represents the exhaustive KNN. And the number next to it is the memory required to store a single descriptor in megabytes. If you use, for instance, a product quantization with inverted file index, we end up having these points here. This tells us that using this simple techniques, which are already available in the library, so you don't have to implement them, you can get up to 98.5% saving matching time and memory space, using only a few points in recall. So again, this is quite crucial. If you want real-world application, you need to be careful and mindful of these things. Also, another example, let's say you don't have constraints in terms of memory, then you may select an inverted multi-index technique, which doesn't save memory at all, but it saves time. So you may reduce your matching time by 80%, only losing 0.9 points in recall. So be very mindful about this thing. And it's something, again, as researchers, we often neglect, but for real-world application, this is quite important. And then there are other interesting things that will be looked at. We're not going to look at all of them, but for instance, data augmentation. There's always the question, what kind of data augmentation works better? And for instance, we found that color augmentations like color jittering, they do not work well across all data sets. So its effectiveness depends highly on the data set chosen. So for example, Pittsburgh 30K or Enjam, it doesn't really help at all. These are data sets, for instance, Pittsburgh, where it is very homogeneous. So training and test data, they all look the same. On the other hand, on MSLS and Tokyo, there is a lot more variability in the illumination, so this helps improve the result. On the other hand, horizontal flipping and the size cropping are simple geometric transformation. They tend to improve consistently across datasets, albeit very slightly, but it's something so you can use rather freely, I would say. Another interesting point we may ask is it necessary to use full-scale resolution images? I mean, in general, in visual tasks, we know that it's better to use full-scale images because then you preserve all the details. So if you want to do object detection, something like that, probably it's better to use full-scale images. Counterintuitively, this is not really the case in visual visualization. So what we found out is that, okay, if you use a method like NetLab, something that uses clustering, then probably you get slightly better result if you use full-scale images. But on the other hand, if you use a pooling method, we notice that scaling down the images up to 40%, essentially you really don't lose much. Sometimes you get even better results. And this, however, has the big advantage that you drastically reduce your floating point operations, and also you reduce the space, the storage space required to store these images. Again, so this is something which is quite useful for practical application. And a bit curiously, we also found out that on this particular data set, Central Lucia, so if we take a model trained on Pittsburgh, it's 30K, and then we test on Central Lucia, we found out quite curiously that the best results by far were achieved when using 40% of the original resolution. We conjecture this may be due to the fact that these data sets are quite different. So the Pittsburgh and Central Lucia are very different. So perhaps in this case, blurring the details may help because they may distract from recognizing the darkness distractors. So this is just a conjecture, but it's something quite curious. As I mentioned before, this is quite counterintuitive with respect to other visual tasks. There are more things we can discuss. We don't have the time, but I want to show you how these simple things we have seen now, they could give you some recipes to obtain very good results. So for example, let's assume we want to use the net flood architecture, as we mentioned before. Let's say we select a ResNet 18 as an architecture with using resolution as 80% of the original size. So this way we have fast extraction, lower memory requirements. And let's say also we use the data augmentation recipes we saw before. So what we saw is that with such a simple architecture, let's say recipe, essentially what you can get, we get results that are comparable, if not better, to much more complex architecture. So for example, here we're comparing to APP-SPR and SRALNet, which are much more complex. They use APP-SPR uses a lot of different attention mechanisms. It's much more difficult also to train, and they have a feature size of the global descriptor higher. And still, with just some simple engineering choices, we can get comparable and not better results. So again, this is a demonstration of how it is really important to focus on this thing. It's important for your results, for your application. It is also important when we want to compare results from different research papers, from different contributions, to really pinpoint what's doing what. So what's causing really the better performance? Is it a new method or is it some other engineering choices? So that's something we really need to be wary about. And for this reason, we share also all this code and models, and the whole benchmark pipeline is available online. You can download it. This QR code, you can find the repository. And then basically you can find this architecture where you can play with these modules, implement your different module, and then give you a way to try and test different methods and compare them one with another. Okay, let's now move to the second part of the presentation. I will give the floor to my colleague Gabriele, who will discuss what are the challenges and going towards very large application and what are possible solutions.
Thank you, Carlo. So yes, again, I will talk about geolocalization for large scale applications. So first of all, we wanted to investigate how existing methods would scale to larger data sets, like to a whole city. And we found that investigating scalability was limited by the lack of large scale data sets. For example, here on the left, you can see the map of the Pittsburgh dataset, which is probably the most used dataset in literature. And you can see that when we map it to the city of Pittsburgh, it only covers a very small area of the city center, just a few blocks. And so it doesn't actually cover the whole city of Pittsburgh. So the first issue is that this dataset is quite small scale. Secondly, it's a single domain, meaning that training and test images, also database and queries, all come from the same domain of Google Street View, which only has daytime images, no rainy weather, no cloud, no night weather, so no night images. And this might be less useful for a real world situation where the queries might come from night images, for example. And the third issue that we found is that there would be non-overlapping sets. And what I mean by this is that the training, validation, and test set do not geographically overlap. So you can see here, for example, the training set is on the northern area of the map. And we found that this would not apply to a real world application, because if you imagine, like, if you are given the task of building a geolocalization software for the city of Pittsburgh, you would first spend weeks or months collecting images from Pittsburgh. And then why not using those images also for training, because you're going to use them as a test time database. So then with these ideas in mind, we came up with a solution. We created a data set called San Francisco Extra Large. So San Francisco Extra Large is a large-scale data set of more than 41 million images. As you can see in the map, it covers the whole city of San Francisco, more than 150 square kilometers. It contains a single database for training and test. So basically, you can use those 41 million images however you want. And the final goal is to geolocalize those unseen queries. And then finally, we provided a challenging set of queries, which we took from Flickr after visually analyzing the ground truth to make sure that the ground truth label is correct. As you can see, the images are quite challenging. There are some night images, some difficult perspectives, and so on. And we released two sets of queries. The first one is a set of very challenging queries. And the second one is a bit less challenging, but it also contains, the queries are also labeled with 6 degrees of freedom labels. So you can also use this for visual localization, like for pose estimation of the camera. So after building that data set, we wanted to investigate how existing methods would scale to such a big data set. And we found that previous methods could not scale to such a data set for 2 reasons. First of all, at training time, almost all existing methods require mining. And as Carlo showed before, mining is very important. The complexity grows with the size of the database, and so it becomes quite an issue when you have such a big data set. And the second issue is at test time, because previous methods would create very high dimensional descriptors. For example, the netlud layer creates embeddings that are even bigger than the images themselves. So if you want to have a geolocalization application on a whole city like San Francisco, then you would have millions of images as database, and the descriptors alone would require terabytes of memory to be stored. And also consider that you need to keep those descriptors in RAM memory for an efficient KNN. So you would require terabytes of RAM memory for an actual application. And so to overcome these issues, we wanted to see if we could apply best practices from large-scale image retrieval. For example, by using the methods that were used to win like the Google Landmark Retrieval Challenge. The winners of these challenges would use scalable losses like cos-phase or arc-phase to train on such a large amount of data. But these like the Google Landmark dataset has the images split into classes, meaning that there are millions of images, thousands of classes, and each class represents like a famous landmark, and each image belongs to only one famous landmark. Now, the issue is that datasets used in visual geolocalization have continuous labels. The labels are GPS coordinates. And so it is not so easy to split them into classes. So we made it our new goal to be able to split the dataset into classes, to be able to use those scalable losses to improve scalability of these methods. A naive approach to split the dataset into classes would look something like this. So here you have a map of a geolocalization dataset. All these triangles represent an image with the orientation, with the GPS coordinate and the orientation label. Here you can see an example. To split the dataset, we could simply do something naive. We simply cut the dataset into cells. Each cell is a class. Although this would lead to two issues. First of all, there would be intra-class scene variation, meaning that within a single class, within a single cell, there could be two images that point towards different directions, as you can see here in the bottom. These two images look totally different, and so they would be confusing for training a neural network. The second issue would be inter-class visual overlap, meaning that, as you can see, the two images on the left, they represent the same building, they show the same scene, but they belong to different classes. And this also would confuse a neural network at training time. So to solve the first issue, we did something super simple. We only kept images pointing towards one direction, let's say towards the north direction, and we removed all the images towards pointing towards other direction. And to solve the inter-class visual overlap, again, something super simple, we removed all the adjacent classes. So this means that we only keep, let's say, one every 4 classes, and then so yeah, again, we use only a subset of the dataset. Now we finally have the dataset split into classes, well-defined classes, and we can train our models with a loss like cos-phase. Here you can see, for example, just an example of the model. It uses a backbone. Any backbone would work. A fully connected layer, which produces our descriptors, and these descriptors are fed to the cos-phase loss. So the cos-phase loss is a weighted loss, so it has a number of parameters which depends on the dimension of the input, so on the size of the descriptors, and on the number of classes. And then at test time, we can simply remove this cos-phase loss, we can remove these parameters, and we use those descriptors for testing. So we found that this quite simple solution is able to scale to a big data set and would already obtain state-of-the-art results. However, you can see that it only uses a small subset of the whole data set. And so we thought, can we actually go even further? Can we use a larger subset of the data set? So we found that we actually can go further, and we can simply shift the grid, reinitialize the cos space loss, the cos space, its weights with the new classes, and we can train again with these new classes. And so basically we keep fine-tuning this backbone and the fully connected layer. And we can do this iteratively over and over by shifting the grid. And this is the idea behind the cosplays, which we presented last year at CVPR. Actually, cosplays is a bit more complicated than what I showed you, but that was the basic idea behind it. For example, how it actually works is that in yellow, you can see one of the subsets that we use for training. These subsets are defined by 4 hyperparameters. Obviously, we have the size of the cell, which we set to 10 meters. We found it to be a good solution. We have n, so it's not true that we actually keep 1 every 2 cells. We need a bit more distance between 2 classes of the same subset. And this again is to avoid any visual overlap, because 2 images taken even 20 meters apart could represent the same building. So yeah. And similarly, we found that we do not really have to keep only images pointing towards one direction, towards north. We can also use classes, for example, of images pointing southwest and southeast. And this would obviously lead to more images used, more classes, and better final results. So now let's have a look at some results. First of all, we found that previous methods do not scale to large data sets, as I was mentioning before. For example, SFRS scales its mining method would scale quadratically with the size of the data set. And this is training on San Francisco extra large. And we found that cosplays can actually be easily trained on the whole data set. Secondly, we found that cosplays is lightweight, or better to say that it works well even with small dimensional descriptors. As you can see here in this plot, on the x-axis, we have the dimension of descriptors. Sorry. So the dimension of descriptors, again, as Carlo was showing, is a very important factor in geolocalization and in image retrieval in general, because the KNN depends linearly with the dimension of descriptors. Like smaller descriptors are going to make faster inference. And here on the y-axis, we have the recall at 1. You can see in yellow, we have cosplays that is able to work to get very good results, even with a small dimension of 256. And this is when testing on the Pittsburgh dataset. So the other 2 methods were trained on the Pittsburgh dataset and tested on Pittsburgh, while cosplays was trained on San Francisco and tested on Pittsburgh. Third, we found that cosplays is robust to new cities. Like these are again results on Pittsburgh, and as you can see, cosplays does not outperform previous methods by much. But when we move to new cities, the gap is quite big. For example, here you can see on Tokyo, we are able to get good results, much better results, even with 256 dimensional descriptors. And similar results are on St. Lucia and the Mapillary SLS dataset. And this is due to a large domain gap between training and test sets. So for example, you can see here on the Tokyo dataset, these are some example of queries. Tokyo has also some night queries that look very different from the training dataset. St. Lucia also looks very different from the training dataset because it has a lot of vegetation. Now, again, you can say that these results are somewhat not fair, because obviously cosplays was trained on a lot more images, while previous methods were trained on a smaller dataset. But again, previous methods could not be trained on the whole dataset. So the goal was again to improve scalability at training time. And as a fourth result, we saw that CoSPlace is robust to backbone changes. Like you can simply switch the backbone from a VGG to a ResNet to a transformer backbone, and the results would still be good. While as Carlo showed before, when we use a NetLab layer, you need to crop the ResNet to not the last layer, but the one before to achieve better results. And so here again on the top you can see CoSPlace with different backbones, and somewhat surprisingly you can see that VIT achieves lower performances than even ResNet 18. And this is probably due to the fact that because CoSPlace trains on so many images, it is able to use all the information on the full resolution images, while which a ResNet like a CNN backbone is able to use. Like we are able to pass the full resolution images to a CNN, whereas when we use VIT, we need to resize the images to a lower resolution, and this probably leads to a small drop in results. So let's have a look at some advantages and disadvantages of CoSPlace. So CoSPlace outperforms previous state-of-the-art with 8 times smaller descriptors on average through all datasets. Training takes only 1 day on 8 GB of GPU, while previous methods would require, previous state-of-the-art would require more than 40 GB again for a day of training. And the code is open source and fully reproducible. We released all the trained models. Now, obviously, there are some disadvantages to CoSPlace. First of all, it requires heading labels, like to know the orientation of the training images, while previous methods would not require this, and they were trained in a weakly supervised manner. So they would only require GPS labels without the orientation. And secondly, we found that CoSPlace is not suitable for training on small datasets. Like the results are going to be quite poor if we train on a much smaller data set. And this is due to the fact that as I was saying before, we train iteratively only on a subset of the whole data set. And now, as conclusion, I'm going to talk about what we can achieve today with geolocalization methods and what are the open challenges. I'm going to show you some qualitative results on the San Francisco Extra Large. We're going to see results when using almost 3 million images as a database, covering a surface of more than 150 square kilometers. We're going to use small dimensional descriptors of 512 dimensional. This requires less than 8 GB of RAM, so it can even be used on a laptop. And one query, the geolocalizing one query takes about half a second, although this can be performed much faster, up to 1 millisecond per query when we use approximate KNN, and when we take a batch of queries and we geolocalize them all together. Here, so let's start with some correct predictions. As you can see here on the left, we have a query, and on the right, we have the correct prediction. We can see that CoSPlace is able to withstand occlusions, like here with these vehicles, here with this truck. It is able to geolocalize it correctly, even with some small perspective changes. And it is also quite robust to night images, as long as the perspective is not too different between the query and the positive image. And now let's have a look at some wrong predictions. Here are triplets of query, the positive image, like one of the many positive images that we have in the database. And on the right, the prediction of CoSPlace. As you can see here, the prediction looks something similar to the query, but it's a wrong prediction. So current methods cannot really handle well heavy perspective changes, as you can see here on the top left. Here you can see another example that is also quite challenging for a human, like these two places are not the same, although they look very similar. Also, CoSPlace doesn't work well with heavy vegetation, as you can see here. And again, when we have some strong perspective change and some obstruction, as you can see here, some occlusion. And now, again, some wrong predictions, something quite curious that we found is that when the query here on the left is an outlier, like some very unusual image, also the prediction is going to be something of an outlier. Again, this is the prediction. Obviously, it's a wrong prediction. And we can see this pattern repeating across multiple queries, like this quite challenging night image. And we, as a prediction, we are given this image that is somewhere taken inside a tunnel. This is probably due to the fact that when training, all the outliers are mapped to a nearby space within the feature space, and it leads to this unusual results. And we found this to be the case for basically any geolocalization method. So besides the challenges that I showed you before, we have some more open questions, mainly due to scalability. So the question is, how far can we actually scale with image retrieval? Like, can we go further and further to cities, to whole nations, when just by using compact descriptors? And so can compact descriptors discriminate between millions of places? Like we saw that 512-dimensional descriptor can work quite well when we have hundreds of thousands of places, millions of images, but what happens when we go to even bigger and bigger data sets? However, this is hard to tell today due to the lack of bigger data sets. And now let me share my guess on the future. I think that scaling up is going to require multi-step solutions, as said previously by Hampan Cho. I think that we're going to need classification plus retrieval methods, followed by some re-ranking, which will lead to better results. I think that we're not going to see bigger data sets for a few years, as San Francisco is already quite big. It takes almost a terabyte of storage. I think that CNNs are still going to outperform transformer in general. And I think that domain adaptation will be helpful, which is something that is not very well studied today. There are not many papers on domain adaptation for geolocalization, but I think we're going to require it to close the domain gap between queries and database images. And now let's see some more qualitative results. We're able to use cosplays to geolocalize some movies. I hope the video works. Okay, there's supposed to be some audio.
So we got to share audio.
Okay. Anyway, that was the clip. And we're able to geolocalize this image to this place in San Francisco. And if you want, you can check the correct coordinates, latitude and longitude on Google Maps. And let's see one more example. Okay. And again, we could geolocalize this image, even if there was a lot of blur in the back. It was quite difficult with a lot of occlusion. And obviously, these are very cherry-picked results. So these clips have a lot of frames. We could try to geolocalize all the frames, and at least one would work. And obviously, those movies were filmed in San Francisco. Here is again another demo. When using a 3D model to sample 2D images. As you can see here is some examples of the database. The query is on the bottom right. We also applied a ranking method, and this was done as a collaboration with a team from the Karlsruhe Institute of Technology, and on a data set from Berlin. And as you can see, again, we were able to geolocalize the correct prediction for this query. So Thank you for your attention on this presentation on the pursuit of scalable geolocalization. Again, we're able to geolocalize this image. No cherry picking here. And here on the bottom left, you can see the link to my GitHub page where you can find all the code for all these methods that we saw today. And if you have any question for me or Carlo, we would be very happy to take them. Thank you.
You showed a result of the previous slides on cosine place and all these different results you got. It was an earlier slide, you were showing an order of data sets, you were getting really good results. In each one, you were just training in the data for that data set and then applying it for the test data for that data set. Is that correct?
Yes.
There's no combination of all these data sets into one big data set and then
No.
each one is a separate experiment just with that.
Yes. Yes. We train only on the San Francisco data set.
But then you showed some results when you say it's robust to new cities.
Yeah.
You're still training with the new city. You're not training domain transfer.
No, it's not training with the new cities. It's only trained on San Francisco, and then we just apply image retrieval to the new cities without any fine tuning, any domain adaptation. Simply train on the San Francisco data set.
Which is good. That's what I should do. So how many meters, within how many meters you can geolocalize?
As a threshold, we followed previous works which have a 25 meters threshold. We didn't see how many of these are actually geolocalized within a lower threshold, like within 1 or 5 meters.
So you were showing the video geolocalization, you're just getting one GPS location for the whole video, right?
Yeah.
So do you think you can get trajectory how the frames are wandering with different GPS location?
I think yes. I mean, as I was saying before, many of the frames would be wrongly geolocalized, but of the ones that are correctly geolocalized, we can obviously draw a trajectory for the whole video.
Yeah, but are you guys working on geolocalizing the video?
We had
We're doing something with sequential sequence of frames, mostly for robotics application. We're doing something in that field, but we haven't tested yet cosplay in the case. We are working.
So other question I had, you mentioned that the CNN will win the transformer. That's a pretty provocative statement. Why do you think so?
I mean, with cosplays, we found that CNNs are winning.
I agree. CNN will win, probably.
Okay. Yeah. I mean, what I found as a big issue with transformers is that it's not so easy to apply them with bigger resolutions, or usually you require squared images. If you have rectangular images, you need to apply some pre-processing or post-processing. Perhaps these issues can be solved, but we'll see. Thank you. Any other question? Yeah.
Yeah, very nice work. You showed some errors in the ends that you obtained. I wonder, do you have any insights on identifying when your retrieve result is unreliable? So there are certain estimates, or if you can detect that what you get is not a good match.
We didn't really focus on that. There are some works on geolocalization that investigate that, try to get a confidence score. Like naively, you could simply use the distance in feature space. You say, okay, if these descriptors are far away, like the query from the first prediction is far away, then the confidence is low. But this doesn't work too well. There are separate works that work on this. Yeah.
Yeah, there are a couple of recent works, I don't remember the titles, where they try to perform uncertain quantification of image retrieval based visualization for that. Something it's something that I'm using.
Your main idea for cosine place is to split the training data so there's no overlap.
Yeah.
Right. So you basically have gaps and then you look in one direction. And
Yeah.
if you have different directions, you have different plots.
Yeah.
And so then if you have from the same location, different directions, then what do you do?
Like we simply remove those images. So basically what we actually do is that within a given moment, we are only training on 1/50th of the data set. So like, yeah, a small subset of the data set. And that is why then we do 10,000 iterations on that subset. Then we shift, we train again, we shift, we train again. Because yeah, otherwise we would use just a small subset of the whole data.
But at the test time, you have many directions.
Yes,
right?
yes. Yes.
To either of you, have you noticed any difficulties when the scale of the object in the image is very large? And can you speak about that type of challenge? So say, for example, in the top right, so you have the up close image of the arches, and then say you were 40 meters back, or you change the lens size on the camera. Are there any kind of situations that you have to talk about with that?
I mean, usually each query has a positive image within 25 meters. And these data sets are basically, they map the whole city, like they are collected from Google Street View. So like we have, let's say, one image every 5 to 10 meters. But yeah, obviously when we have some issues like that, that can be obviously problematic. Now, what you want to do is to find a prediction, like a database image that is within 25 meters. So sometimes we have, there's no example here, but sometimes we have the prediction to the query is something that looks very similar, but is actually, let's say, 30 meters away. And that is considered as a wrong prediction. And yeah, that's the metric used in literature. Now, we can debate as if that is a correct way to evaluate these methods, because two images might look almost the same while being 30 meters away. Yeah.
So any other question for this talk? Okay, let's thank the speaker again.
Thank you. Yeah. I'll stop sharing that.
Okay, so we are going to have a 15 minutes break. So we'll come back at 10:40.
Okay, I think it's almost time to start, and I think everybody will come back. My name is Jeju. I'm currently a research scientist in ByteDance, and before that, I finished my PhD in the University of Central Florida. I'm working with Dr. Chen and Dr. Mark Shah. Today I will talk about re-ranking based geolocalization, or we say place recognition, and specifically, I will introduce our recent work called R-square former, unified retrieval and re-ranking transformer for place recognition. And this work was finished during my internship in ByteDance. At that time, I was still a PhD student in PCF. And the poster session is on Thursday morning. If you are interested, you can come. So let's start from the problem statement. If we only consider the image level retrieval, then the formulation of the geolocalization, or we say place recognition, are almost the same. So, for example, if we're given the query image from an unknown location, we want to localize it by searching in a large reference database, right? And so the reference images comes from the known locations. So, for example, they may have GPS tags, right? And we want to retrieve the images from the same location, and as the output. So the previous invited speakers, they have introduced the global retrieval-based geolocalization. So here I will focus on the two-stage geolocalization that is called retrieval and re-ranking. So it's like a state-of-the-art methods. They all follow this two-stage pipeline. Typically, they will use like a CNN to extract local features first, and then we will use some kind of aggregation method once you generate a global feature to do a global retrieval, most likely in a very large reference database. And for example, we can use the Matplotlib or the GM pooling. Right? They have introduced it, and after we do the retrieval, most of the state-of-the-art works, they will do a re-rank on the top retrieved results. For example, maybe top 100 candidates. And the re-ranking will be using like a ransack-based geometric verification. For example, something like this. So they are not just doing image level matching, but also doing like a local patch level matching. And so why are we doing this re-ranking? So basically, as we can see here, the benefit is that you can easily improve the performance, like almost 5% on the macular data set if you do a simple ransack. But here, what are we doing in the ransack? So, for example, we have two images, and we want to do the local matching, right? So the first, the left image, if we select a local feature here, for example, the red dot like on a window. And then this local feature could be matched with any other local feature in the other image, right? For example, it could be like this, right? Any other feature could be matched. And then how do we select the good ones? So for the ransack, it just directly computes the similarity between the local features, and you select the best one, right? The one with the highest similarity. For example, maybe on the windows, and we can find this one is the best pair. And after this, for example, if we have 500 local features in each image, then we can do the same. So we may have a lot of pairs, like maybe 500 pairs. And apparently some of them are correct and some of them are wrong. Right? Some of them you can see these are like wrong match. And so basically what the ransack do, so ransack will take all the coordinates of the local pairs, like the X, Y, the coordinates of the pairs. They will take this as the input, and they will try to figure out which one of them are correct, right? So basically, they only take the geometric information as the input, only the X, Y coordinates. And after doing this, it works fairly well on most of the cases. They will find the correct matches, and they will compute the geometric transformation between those two images and try to verify them to see how many of them are inliers. And if there are not a lot of inliers there, then they see that, okay, these two images are correct match. So that is how to do the re-ranking. But basically, this is not optimal because there could be some other information that also useful for the re-ranking, but they are not using it. For example, the correlation or similarity information, that is to say, some of the pairs may have higher similarity than the other pairs. That information is not used. And also the attention information, that is to say, different local patches. Some of the patches may be more important than the other patches, but this information is also not used. So this is on the performance side. And also on the computation side, RANSEC is also not optimal because in terms of the latency per query, you have to do the re-ranking on 100 images. So the latency is very large. Sometimes, the state-of-the-art method may have more than 1 second to process for one query. This is not acceptable for large-scale applications. And also the memory footprint, you can see that for 1 million images, the local features, they have to save all the local features in the memory. And this may take like more than 1,000 gigabytes. And usually this cannot fit in any like normal servers. So basically for the conventional pipeline like the left side, the limitations that this RANSEC based is not end-to-end learnable, so it cannot benefit from large scale training. And also it only use the geometric information, does not consider other information. And also it cannot be like very well like deployed in real world large scale applications. So we want to address these three limitations by using a unified solution, like using only transformers on both of the global retrieval part and the re-ranking part. So that is the basic idea. And how do we do this? So here's our pipeline. And so for the global retrieval part, there's a quite standard, just following the standard pipeline, but we are using VIT as the architecture. But the different thing is that we want to mention that the previous talk, they are using VIT, they didn't change the resolution. But here we are using like an interpretation so that we can use any resolution. So we can use the original resolution, like just like the singing and base method. So here we take the two images as input, and we do just like the VIT, break it into small patches, right? And then we generate the patch embedding of each of the patches. We add the class token, and we also add the positional embedding there to have the positional information. And then we put them into global retrieval transformer encoder with the shared width for 2 branches. And after that, we want to do the global retrieval. So the previous methods we use like a net-valot to do the aggregation, but here we just directly use the class token. So we only use the class token, directly use the class token as the output, and we generate the global feature. We use a triply loss training. So basically, this is just like a standard global retrieval pipeline, except we're just using VIT and we have the arbitrary resolution. Here's the legendary. And as for the re-ranking part, it's a little bit different. So for example, here, we first apply a linear layer to do a dimension reduction. So we want to save some memory. So we don't want to use that large dimension for the local feature. We reduce it to only 128. So that it could be very small. And then we generate a attention map, which will be described later. And so the attention map is generated using the global retrieval model. So we generate a attention map in the transformer layer. And then this will indicate which part is important, right? And we only select the most important local features to be used for the re-ranking. We don't use all of them. So here, for example, we may select like 500 for each of the images. Originally, they may have more than 1,000 tokens. And after that, we want to compute the correlation matrix. So when we say correlation, you see each of the images will have 500 local features or patches. So if we want to pair them, just like the ransack, we may have 500 by 500 pairs, right? Originally, we have that, so like a 500 by 500. But our ransack only take the XY coordinates as the input. We want to use more information, for example, the attention information and the correlation information. So it has a dimension of 7. So what is in this 7? So the first dimension is that the cosine similarity of the local features. This is the correlation, right? Correlation information. And then the 2 is the attention value of the 2 local features in their original image, like in the 2 images. There are 2 dimensions. And also the XY coordinates of the 2 local patches. So they will be 4. So we add them together, that will be 7. And in order to have this attention value and the coordinates, we have to record it before. So this will be 3 dimension of 3 added to 128. So we have a 131. That is why we have there. And after this, ransack will select the pair with the highest similarity, only select that one, right? But here we want to keep more information, so we select the top 5, like for each of the image. So like for each of the patches, it will be matched with top 5 patch in the other image, and we also do the same from the other direction. So we have 2 metrics there, and after that, we use a linear layer to transform this dimension 7 to a 32, because 7 is not friendly to the transformer. If you want to use multi-head self-attention, you have to have a number that can like 32 can be easily divided by the number of heads. So here we have this 100, and we concatenate those 500 from the left and the 500 from the right side. Concatenate them together, we have a 1000. So we have the 1000 by 5 by 32 matrix here. Then it aggregates, it has all the information we want. And then we want to learn to re-rank. How do we do that? So we apply 2 transformer blocks to do this. So firstly, the first transformer block is trying to aggregate the information from the top 5 pairs to just 1. So it will take the top 5 pairs as 5 tokens as the input and add another class token. But in the output, we will only take the class token. So the dimension of 5 will be reduced to just 1. And in this case, it will aggregate all the information from the top 5 pairs. And then, yeah, here the 1000 is considered as like in the batch size, and the 32 is the dimension of the transformer. And then the second transformer block is trying to aggregate the information from the 1000 pairs. So the 1000 patches. It takes the 1000 tokens as the input and add another class token, and we take the class token as the output. So in this case, the 1000 will be reduced to just 1. So we have a vector of 32 as the output. It aggregates all the information we want. And then we apply the last linear layer just to transfer it into just 1 re-ranking score. So the score will between 0 and 1, it will determine like whether the 2 images are correct match or not. And this can be easily trained with a binary cross entropy loss, right? So this is the whole pipeline. We are doing it. And on the right side is the architecture inside the transformer. If you want to take pictures, you can do that. So after this, I will introduce how do we generate the attention map. So firstly, if we take the image as input, we will go through many transformer layers in the global encoder. But in the last transformer layer, we will take, as you can see, you can take all the tokens there, and the left one is the class token. And as we know that the self-attention map in the transformer, they will compute the correlation between each of the tokens. So just like this, it will give you like a n+1 by n+1 matrix here. And then we give the output for all the tokens. But only the red one, the class token, only the class token is connected to the final output. That is what we did. So we take the output of the class token. So for example, here the correlation corresponding to the class token. We take them and reshape to the shape of the image, and we use that as the attention map. So why do we use that? Because that will indicate the contribution of each token to the final prediction. So that will show the importance of each of the patches. As we can see, most of the objects like the lights here and the rows here, they are highlighted. And the skies, they are not very important. And we use this to select those important tokens. So how do we evaluate this method? So here we evaluate on this major data sets like the mapillary, the Pittsburgh, and the Tokyo. As we can see here, our method achieved significant improvement. And so the performance, especially on the mapillary challenge data set, the performance is significantly better, like more than 9 points better than previous method, and even better than this super glue based method. And also, currently it is still the top 1 results on the leaderboard of the mapillary challenge. You can see here, and here we also measure the computational efficiency in terms of the feature dimension, the latency per query, and the memory footprint. So here, as we can see, for the latency per query, our method is 4.7 times faster than all the previous method. And this is just using 1 GPU acceleration, but our method is, it's based on transformer, so you can easily use multiple GPUs to accelerate further and make it even faster. And also for the memory footprint, we only use like 22% of the cost as compared to the previous method. Even for 1 million images, if we save all the local features, they only cost like 200 gigabytes. It can still fit in a typical server. And as we also want to compare with other re-ranking based methods, not just our geolocalization. There are also some methods like proposed for landmark retrieval. So for example, this method called RRT, which is re-ranking transformer, but they are doing it in a very simple way. So they directly take the local feature from 2 images, they put them together and directly feed them into the transformer to do the re-ranking. And there is also the other work published last year on CVPR, but they are on landmark retrieval. So it's called CVNet. So they compute the correlation between all of the local features, and they use a 3D CNN to generate the final output. So we test this method on our mapillary data set and using the same local features and global features, but our result is still much better, and it's also better than RenSec. So here we did have some interesting experiment on the transformer tokens vs CNN local features. So as we know that transformer based architecture, they are very good at modeling global correlations. So basically each token has the access to all the other tokens. So it knows the global information, but we still don't know if it contains enough local information to do a local matching. But CNN has locality because the kernel size of the convolution is limited, so it has local information there. So here we use 2 backbones with the Witsmall, and another one is the ResNet 50 based. We use a GM pooling, and we have the similar global retrieval results on the mapillary dataset. And then we try to apply RenSec on both of them. And we figured that the results are actually similar. So basically the transformer tokens, if you just use RenSec, it can also perform well with the re-ranking. So basically they also have the local information, not just global information there. And as we see that, another finding is that even with the CNN-based backbone, we use our re-ranking transformer-based re-ranking. The result is also quite good. I can see that it's still better than the state-of-the-art methods. And so basically, it verifies that our re-ranking method can be applied to both CNN and the transformer, and or maybe other backbones. And another question is that as the other speakers say that if you use a larger model, you will get better results. But here, if we are using a large, like a read-based model, we didn't get much improvement. Like that is quite interesting. That basically on the top one, we didn't get much improvement, but on the R10 maybe a little bit, but still not much. So maybe that's a limit, or maybe we can explore in the future. And for the interpretability, yeah, we also want to explain our method. So not like as we know that RANSEC can be explainable. As we can see, we have an image pair. We have select those important tokens. And the RANSEC can have those local matches that is totally explainable. As for our method, we can also do something the same. So, for example, our re-ranking module is also transform-based, and we can compute the attention map in the transformer, and we highlight the most important tokens there that will highlight the most important pairs. And if we print out those top 20 important pairs, we can see that most of them are still also like correct local matches. So some of them are maybe not perfectly, but perfectly matched, but still most of them still make sense. So we think it's still kind of explainable. So here's another case study: is that the query is collected on the sunny days, and the reference images from different weather, like the cloudy. But we can see our method still like generalized where here. So to summary, we propose a unified retrieval and re-ranking framework for place recognition, employing only transformers, which demonstrate that vision transformer tokens are comparable and sometimes even better than CNN local features in terms of the re-ranking or local matching. So not just global retrieval. And also, we propose like a novel transformer-based ranking module to learn to attend on the correlation of informative local feature pairs. So it can be combined with either CNN or transformer backbones with better performance and efficiency than the other ranking methods. For example, the rank. And the code has been released here, and you can also scan like the QR code to get the link. So thank you for listening. That's all. Yeah.
Can you go back to your architecture slide where you had to pull up?
Yeah, sure.
So your as a chemical math which you're taking, have a lot of tokens, right? Well, 500 is the number of attacks. What is 500?
Yeah, 500 is the number of tokens that we selected. So originally the 1,000.
Then when you say top 5 pairs.
Yeah. So here I might explain what is the. Oh. It's kind of weird that let me show it. Yeah. We can show it here actually. So basically, for each of the local feature from the left image, right, it could be paired with any of the other tokens, right? So when we say that RANSEC only select the top 1, we select top 5, like with the highest similarity here. So it's just like this, but we select top 5. Yeah, that's the way we go. Yeah, kind of like.
The 500 by 500.
information matrix, right?
Yeah.
That's between what are you interpreting?
So this is between these two images. So if we have 100 images, we have to do it 100 times. But basically, this is because this pipeline is like based on I mean you can implement this PyTorch and you can do like acceleration. You can just if you have 100 images, you just put them into a batch. You can do in one network forward pass. It's just yeah. Yeah, so the 500 by 500 is the original one. Is each of the patch here can be matched with 500, right? Can be any other. So
But the gradient of fit loss, within the retrieval, within the inference, right? You compute the embedded. You do this for looking right across every image in the database. Or how do you do it?
oh yeah, I got it. Yeah. So we just follow the standard pipeline. So for the global retrieval, you can search in a very large reference database like 1 million. And for the re-ranking, it is only applied on the top 100 candidates.
So it's like the transact.
Yeah. So I mean, this pipeline is the same. We have one query. You can match it with 100 candidates, top 100. But
You're saying this is competition with people?
yeah,
Transact?
yeah.
But for this ranking part in inference, I think on the rank is, I would say, right part of the computation, because this left part can be pre-computed works for every time, yes? So the ranking, in a rank, when you go to rank 100, let's say, potential responses, we don't need to run the pipeline 100 times. Yeah?
I'm not sure if I get the question. Can you so do you mean we don't have to do this 100 times?
To make it efficient for inference, to make the ranking efficient in inference, we can, I would say, pre-compute the what's on the left side of the picture. It has this.
Yeah.
You can store in the database.
Yeah. Yeah, that's what we did. Yeah, actually, all the methods, they have saved the local features in the memory. That's why they cost a lot of memory. But our local features kind of have a very small dimension here. So we save a lot of memory, and we also select important tokens. We don't save all of them. So that's why it's memory efficient. But I cannot say that this is more like computational efficient than Ransack, but it's just running faster because Ransack is mostly implemented on the CPU, and you cannot do like multiple GPU acceleration like very easily. But you can apply some of the recent repo, maybe you can do that, but it's not straightforward. But if you're using this kind of transformer-based model, it's straightforward to use multiple GPU to accelerate it. Can be extremely fast to finish the re-ranking of 100 images. Yeah.
If you have a large computer.
Oh yeah, you have to have a GPU there. Yeah.
Do you train them separately, the re-ranking and global retrieval?
Yeah, that's a good question. So our pipeline is framed end-to-end in an end-to-end pipeline here. I think I hide one slide, but maybe there are some results.
You can train them actually separately or.
Yeah, we are actually. Oh yeah, I can. I think maybe hard to find it, but yeah, I can explain that. So it's we can train this end-to-end in an end-to-end manner, but the result is not the best. So it is still the best that we first train the global retrieval part and then fix the global retrieval part and train the re-ranking part. And then maybe you want to fine-tune them together in the other stage, then that will give you the best performance. Yeah, we did that. So fine-tune them together and give the best result. But yeah, but if you train it in an end-to-end manner, it still give you good performance, like a 87 or more. Yeah, on the map theory, it's almost like still can be considered as state of the art because previous method like AT.
You start from scratch in the global retrieval or from some kind of initialization?
Yeah, so the weight of this initialization is the I think it's the delta from Facebook, the delta small initialization. Because to be fair, as we can see, the original VIT, they are trained on a very large data set, like the ImageNet 100K. Maybe I forgot how. Yeah. So it's a very large data set, more than ImageNet 1K. So but if you train a VIT on ImageNet 1K, the performance is not as good as ResNet. So we are using DELT. So it's another, yeah, data efficient VIT. So basically it's just a different training pipeline, but it can get state-of-the-art result on ImageNet 1K with VIT small architecture, but the training pipeline is different. So they have better result as initialization. So it can be comparable with CN. That's why we use it. But if you directly use the original VIT trained on or extremely large data set, you can also get I think you should be able to get a better result. Yeah. Yeah. We save them more in the memory because it's kind of take only small space. Yeah, the three additional dimensions. The first one is the attention value. Only take one, and the XY coordinates will take two. So basically the three. Yeah. Thank you so much. If you have a further question, you may ask it later. Okay, yeah.
You want to use the first one?
Yeah.
Oh, okay.
Okay.
Yeah, yeah.
So,
Share the screen, yeah. Select the slides.
You can just say share screen.
You can just share the screen. Okay, yeah, it's fine. You know, it's okay.
oh, sorry.
You can, yeah. So, okay.
Okay, so can you guys see now?
Yeah.
Yeah.
The Zoom, you're getting dual screen, so it's,
Okay, so how about now?
yeah, now,
Yeah.
yeah.
It's good? Okay, very good. Okay, so good morning, everybody. Happy Father's Day. If you are fathers, happy Father's Day. We are going to be fathers. Again, happy Father's Day. If you are very young, just call your father, say happy Father's Day. You know, this is the CVPR. I think every year we have this tutorial on Father's Day. So my two sons, they send me texts, so I'm happy. So it was a great talk CJ gave. It's great to have students like him. So we are very proud of him. Did a great work at UCF. He's working in bike dance, and if you know anyone student like him, please let me know. I'm recruiting lots of students. It's very hard to find good students. So I'm going to talk about this paper. We have this CVPR where we say where we are and what we are looking at. So as you have heard so far today, that the geolocalization means that given an image, we want to find out the GPS location of that. Okay, and it has these two main techniques: retrieval-based method. That's what he talked about. Most of the methods are retrieval-based method, and the other one is the classification-based method. Okay, so the retrieval-based method, as you know, that we compute features of an image, and then we compute features of the reference image, and we save those features. Then we just give an a query image and get your model, and we get query features, and we already have offline computed the features of the reference images. And once you have those, then we match it and we find the best match, and that's the traditional way to do the geolocalization. Okay, now classification based method is a little different. So what we do, we take the whole Earth and project on a cube, and with each side of a cube become a class. Okay, so that's kind of more similar to the ImageNet classification kind of thing, because there's a lot of work on that. And we take that, divide in 4 smaller classes, and then we can have some threshold. If it's too large, we can divide further, and we remove the classes which are too small, and so on. We can keep going there. So it will look like this. These are little classes, these in the whole Earth, and we can split and remove, and becomes like this. We can keep going that, and we can have very fine classification, find small cells. So that's kind of classification approach. So now when we are given a query image, we predict class it belongs to. So we just have like a classifier, take the image and classify which class it belongs to. So that's the idea. Now, advantage of classification-based approach are this very immediate prediction. Just run one forward pass, it tells you which class it is. It can cover the whole Earth. Okay, and then we can introduce different hierarchies. Hierarchies can be like continent, country, state, and city, and county, and so on. So there's some work in this area. Most of is the retrieval-based approach. So there was I think one of the first paper, ICCV 2017, which use this approach, and it divide the Earth in multiple partitions like this, and essentially it computes these features. They actually had these 2 classes. They were also doing the retrieval-based method and also this classification-based method like this shown here. There was another interesting paper in 2018 by Muller, and they actually combine these probabilities from different classification level, hierarchical levels, and they found improvement. So the idea is that if you know the image in Europe, then probability that's in France increases. Then if it is France, the probability that it's Paris, you can utilize this facts in Paris and Eiffel Tower and so on. Okay. So they call this individual scene network. So in addition to this hierarchy, they introduced the three scenes, indoor, urban, or natural, and they train these model like that, and they have these different scene classifiers, and then we combine these output to actually do the classification. One more method, which is a very recent method last year from Ramachandran's group, and they call it translocator, and they essentially use the image and at the same time semantic segmentation of image, and they do this the attention between these two, and it seems to help, and they have pretty interesting results. So now, given this context, so our approach is that we want to use transformer, as I said earlier. I think transformer is the right way to do. And our approach is a decoder-based architecture, and we are introducing this new notion of geographical query. So query's idea is very similar to data object detector, which was pretty interesting paper from my point of view. So we extract features for each hierarchy and each scene within a hierarchy, and using that queries. So we have 7 hierarchies, and the 16 scenes. And so in addition to that, we introduce a new data set, which is fair and which covers the whole Earth. And also we have results which are state of art. Some cases we have 40% improvement. Okay, so now previous work only gets one set of features for each query image. Our approach accepts features for every geographical queries. So we have 7 hierarchies, and we did actually ablation on different hierarchies. We found 7 to be good, and these are the hierarchies. As you see, as we go down, then we have smaller and smaller cells, and then we have 16 scenes, and we did actually ablation on different number of scenes, and these scenes are shown here. Sports field, transportation, cultural building, and workplace and hotel, homeland, home, and so on. So then model is simple. So it has the encoder, then we have these learnable queries, and then we have a 2 decoder. And then once we get these output queries, we select the maximum one that goes to the classifier. And we have these classifier for each of these. So let's go in detail. So our encoder is the SWIN encoder, transform encoder. It works pretty well. And that has, it's pre-trained ImageNet, and that output is 7x7 by 1024. And then these are the queries we have. So we randomly initialize, and we have these scenes, and each scene has these 7 queries. Okay. And each query is tasked to extract the specific features. So we have total 112 queries, and each is a 1024 dimension, and we randomly initialize. And then in that, the 0th channel is trained to be seen confidence when we get output queries. Okay. So then we have this hierarchy dependent decoder. So where we have the encoding of image comes in, and then we have queries, and we have these standard self-attention and layer normalization and all this thing. So they are basically extracting the features, relevant features from the encoded image, which are relevant to queries. Okay. And so this is a standard thing that we take the previous layer of the query, do the layer normalization, multi-head self-attention, skip connection, and then here we are doing a cross attention. So this encoding of an image, okay, which is coming from here, and then the feed forward network, so standard transformer. So after that, then we have this hierarchical dependent encoder. So in the previous one, we were using all of these together, all the hierarchy, but here we're going to separate the hierarchies, okay? and we found out, that to be helpful. So, so the idea is a self-attention and feed forwards specific to each hierarchy. And so only thing will be, we'll have this change here. Now we have H, we only use the queries for that particular hierarchy to get the self-attention and cross-attention. Otherwise, it's the same thing. Okay, so after that, then we get these output queries, and then we select the queries which has the highest performance, highest value, and that goes classifier. And the way it's trained is the 0th channel is the actual scene level. So average of 0 channel for each scene and highest value selected scene. And the last part is a classification. So that, as I said, that we will use select queries to go to the particular specific classification layer. And this is the idea that we are using this different hierarchy. So given an image, particular hierarchy, what class it is, then, next hierarchy, what class it will be, multiply these probabilities and get the maximum one. So that's it. So that's your model. Okay. So now we train it using the 6-layer hierarchy independent decoder, 2 layers hierarchy dependent, and these are all the hyperparameters. I'm going to skip that. So now how do we train this on the this network? So training data sets typically use the MP16, the Media Evaluation Places 2016, and it is about 4.7 million images with GPS from Yahoo and Flickr, and it's shown here the different areas where these images come from, and it's a subset of YFC, say 100 million, and it's not really curated data set, but it's widely used. So these are examples of the typical images from this data set. Now the testing data set is important, that you train on one data set and test on other data set. That's the important point here. So there are several of these data set, image to GPS, which is one of the earlier one, only 300 images. Then image to GPS 3K, which has 3K images. And these are the kind of distribution of these. As you see, most of these is North America and Europe, and all the rest of the world is not really covered. Okay, so these are the images, and they're mostly landmarks and so on. So that's the problem. And then there's the other one, YFCC 4K. Again, it's a 4K images. Then we have YFCC 26K, 26K images. But as you see, it's only North America and Europe, and not other rest of the world is empty. Okay, so these are the typical images. So what we did, we wanted to address this problem with the existing data set, test data set, so that it's not just simply iconic places, but it is more general, and also this Flickr images are taken from random locations, and it's not really uniformly distributed. So that's a problem. So in order to fix this, we collected random images from Google Street View, and so we want to make sure that geolocalizable and it can distribute all over the earth. So this is the distribution of our data set. It's a small data set, but it takes a lot of effort to do that. Otherwise, they also charge money. Google is charging money, and actually they don't want us to release it. That's another problem. Even though we contacted them for research purpose, still. So, but the good thing is it covers the whole earth. So it's very nice. As you see, we cover everything. So the way we did it, we pick a country with probably based on the surface area, and then pick a town or city in that country, and then pick a random coordinate within 5 kilometers of the town, city. So these are the images. As you see, we have images from all over the world. We have Denmark and Iraq and China, Indonesia, Brazil, and Peru and Myanmar, and Colombia and Mongolia and Sudan and all those things. Okay, so one thing is, in order to have a fair data set, what we did, we sorted the city based on number of images. Okay, then we took the bottom 10% of cities and plotted a percent of total images on the y-axis, and that is Lorentz curve. So here is this 10% of the representation for certain data set, and it's a percent of images. So ideally, to be fair, you want to be diagonal. And this is our data set, and these are the other data sets. So I think we are getting close to this. Still, we have a long way to go. So now let me show you the results. So results on the image to GPS. So now this is a whole, Earth. So we want to localize within street level, city level, region, country, and continent, and within this threshold. And we compare with other methods, and we get pretty good result. As you see here, we have a state of our results. This is on 3K. Again, we do better. In a couple of these places, we are tied, we are not as good, but it's still, we are getting good. This is YFCC 4K. Again, we beat the state of art. And this is 26K. We beat the state of art. And this is our data set. As you see, this is a very complex data set. It's a very, very small percentage, less than 1%. So this is a long way to go. And we'll provide the URLs of these images, and people can, take those images and, use those. So this is like a distribution of these. This is the original data set, and within 250 kilometers, we can localize these areas. And as you see, different levels, we can show that how well we can do. So then we also did, how many layers in the decoder we should use, and we found out 8 to be reasonable on these different data sets. We also did how many, whether scenes are helping, when no scenes, and scene prediction and hours, that helps in both data set. Also number of scenes, we did ablation on whether no scenes or 3 scenes or 16 scenes. 16 were helpful. And these other data set here, we also did the number of hierarchies on the different layers of this dependent decoder. And that this is on the ablation encoder type. So we did it with VIT, swing, and hours VIT and swing. The way we use, we do better with swing. It's more ablation here. And this is kind of thing, kind of qualitative results. It shows you that, this is the image and different hierarchy. What are these, different scenes being highlighted? I mean, these are nice pictures, and some of them are meaningful, but not all of them are there. But just wanted to show you a nice picture. I mean, this is a deep learning, right? So as far as works, that's good. So there are more of those. Okay. So and these are the images within 1 kilometer and 25 kilometer, 200 kilometer, 750 kilometer, and so on. So in summary, we presented this first transformer decoder based architecture, which is a very different way to solve this problem, because this idea of queries is that you randomly initialize, you ask what is the relevant information from an image, which is, very nice idea, actually came from the transformer data object detector and so on. So these queries extract the features for each hierarchy. and how many hierarchies you want to use and how many scenes and so on. And so we propose this new data set, which covers the whole earth, and also we get pretty good results. So conclusion, we started with geographic queries and we showed that it's actually doing the job, and it shows significant quantitative improvements, and our quality results show the model works as intended, and our new data set solves the limitation of other test sets. So the future work will be that you can try this on other data sets, like there's this BDD data set, which is more localized. There were, I think, 4 cities. One can extend this idea to video, which would be interesting. I'm always interested in that. And one can combine the retrieval based method with classification based method, that you can have the cell, because these cells cover bigger areas, not a one GPS location. Then within that you can do the retrieval, and that can improve maybe performance. And finally, as a joke, so how about ChatGPT? Maybe we can use that. So that's it. Thank you. Yeah.
Are your data sets, you have to give the data set you created or any other data set you use, did you have to give a training data for each scene, or did you automatically generate the scene classification for the training data? Like you had 16.
Yeah. So we of course during training we know the scenes, and because one of the loss the scene label after we get the queries, and during the inference it's just queries. We don't have to know the scenes.
So when you were applying it to other data sets, not the one you did.
Yeah.
You had to go and manually add the scene to all of them?
No. It extracts that information. That's an interesting thing, right? So because we have trained these queries are randomly initialized, that they are learned. So we just input an image, and these queries actually extract information.
When you were training on a different data set.
No, we just train on one data set. We only train on MP16.
Okay.
And then we use it on all other data sets.
And for MP16, you had the scene data.
Yeah, it's available. People can use it. Yeah. Yes. Can you speak louder? I think it should work if all these things we are doing, right? That if these are, we have trained this on outdoors, right? MP16 outdoor. So if you have data set for indoor, you train it, then the scene levels is different there. So probably you have to have a notation of those that in principle it should work. But we haven't tried that. If you are specific.
And so you train it to on some data set with certain granularity. And what happens if the test set has a very different granularity? So is it transferable? And another question, can you use the features for retrieval? Now, can you go and take the features and like any image classification, and you take the
Yes.
and use it as retrieval, then you are depend on the classification or granularity.
Sure, yeah, good question. So see, the one thing is, as I showed you, that the data set we train is this MP16, right? So this is a distribution of this data set, yes? And we test it on these data sets, so, and I showed you result, it works. It's pretty good. So that answered your first question.
But do you assume that there's the same number of hierarchies in the test set, or you just?
No, we don't. We don't assume anything. We don't assume. See, that's the thing, that we only want to know the hierarchies and all this thing for the test, training data set. Then once it trained, we just give an image and give us these Yeah, of course, hierarchies are fixed. We have 7 hierarchies as we have trained, and it will give you within those. Yeah.
So if it's trained on a city, can you test it on a I don't know, jungle or something like that? Or
Yes.
village that doesn't have any buildings, just have an intuition.
Yeah, of course. I mean, there has to be, as he asked Christian, the indoor versus outdoors, right? So, if it is completely different domain, then they will have a problem. But otherwise it'll be fine. I think second question you had, that if you can use these features for different, for retrieval basis, right? Retrieval method. So in a way, yes, because we have these classifiers, right? So these features are coming to the classifier. So you can use, if you want to, that one of those hierarchy. Yeah. Yes.
The training set, like MP16 is obviously biased towards famous locations,
Mhm.
while
Yeah.
GSV is more fair and
Yeah.
homogeneous.
Hmm.
I wonder if, do you think that training on a subset of MP16, like a more homogeneous subset, without too many images from famous landmarks, would help to
Mhm.
improve the results on GSV?
Yeah, maybe that's a pretty good point. Maybe, yeah, can be done. I think in general we need a much bigger data set and cleaner curated data set. But yeah, that one can do that, because MP16 is not, a lot of errors in that.
Okay, so let's thank the speaker again. You.
Great. I hope people can hear me. And okay, I'm Rakesh Teddy Kumar from SRI International, and I'm going to talk about cross-view and cross-modal course search and fine alignment for augmented reality navigation and other applications. Thank you for coming to listen to this talk. This is the afternoon session. In the morning, all the talks were on cross-time matching, and the afternoon we'll have talks on cross-view matching. We have 3 talks, and then we'll have a coffee break from 3 to 3:30, and then 2 more talks after that. So I'm going to introduce the problem. Then I'm going to talk about cross-view matching, and I'm going to talk about 2 different approaches for cross-view matching. One is trying to get invariant features, and the second is to use bird's eye views for doing the matching. Then I'm going to talk about cross-view matching. So the first set of approaches assume you only have 2D overhead reference. In the second set of techniques, I'm going to talk about where you have 2.5D reference. So you both have the 2D reference and you have 3D point cloud or terrain data. And then I'm going to talk about cross-modal matching, where you're matching 2D ground images to LiDAR reference. So just to introduce the problem of image-based geolocalization again, actually every talk has been introducing it. So given an image, you want to know where the image is taken. Actually, ideally, you want to know its full 6 degrees of freedom, location, and orientation. And you search for it, it gives you a location, and then you can compare it with another image taken from the same location. So one of the, there are many applications for this problem. One of the applications which I was excited about was in 2021, there was a hiker who was hiking near the LA area mountains, and he got lost. And he only had a little bit of cell phone coverage on his battery, and he texted this image to his friend, who gave it to the police, and the police spread the image around with people whose hobby is to do geocoding. So the folks who do geocoding were able to find him, and an helicopter was sent to retrieve him, to rescue him. Of course, image-based geolocalization has many applications. It has applications in autonomous vehicles and robotics. It has a lot of applications in augmented reality. It has applications in building 3D models, and just for geotagging images too, as needed. As I said, the focus in the afternoon is in cross-view and cross-modal, we're just going to get into that. So now for cross-view matching, you want to match 2D ground images to 2D overhead reference, where you have invariant features. And there are 2 types of views over here, approaches here. One is you're trying to do invariant features, and the second approach is you're projecting the reference image to look like the ground image. So it's a very challenging problem because there's a large viewpoint change. This is the ground image. And these are the satellite images, so there's a very large viewpoint change. And then in many applications, you'll also have a limited field of view. When people work on autonomous cars, they assume they get a large field of view because they have 6 cameras, but when you're doing something like augmented reality, you may not have the luxury of having, you won't have 6 cameras looking all around for that. So there have been some benchmark data sets collected for this problem. One of the earliest ones was CVUSA, which was published in 2015, ICCV, and they have about 44,000 pairs of panoramic images from the ground from Google Street View, and about corresponding aerial images. And these are images collected across the US. There was another data set published in CVPR 2019, CV Act, which is similar to CVUSA, but is collected in Australia. Both these data sets, CVUSA and CV Act, have reference image locations which are the same, reference image locations are the same location as the ground image. While, and also in all these, both these images, the images are not aligned, right? There was another data set actually collected by CJ and Chen, who are sitting here in the first row, called Vigor, where they did not assume the images are. You got to mute your thing. So they did not. You got to also not connect your speaker. Okay, so they did not assume the images are collected at the same location as the reference, and also so they have overlapping images. For any ground image, you can have 4 overlapping satellite images. And then this is a slide from one of the other presenters, Florio Purvers, who's going to present next, where there are a lot of autonomous driving applications, data sets collected by all these different companies like Argoverse and Kitty and Ford and things like that. And Florio also collected Google and Street View and Bing satellite images and created a data set for it. And he'll talk more about it in a few minutes. So these are some of the data sets people have been applying to these problems. There are actually even more. So this is a challenging problem. When you think about it, you can take the overhead reference data, you can extract terrain 3D semantic features. You can have semantic labels, you can have skylines, you can have texture segmentations, building signatures, and then you can use these to match, right? And actually, there's a large history of people doing work not using deep learning methods where they were applying these kinds of techniques from before. Nowadays, with deep learning, the new set of techniques, and this is a slide from Masone and Caputo, who presented this morning. The goal is both given the query image and the database of images. Here, we are showing both in this slide, ground images for both query and database. But imagine the database of aerial images. The goal is to come up with some kind of embedding for the query image and then match it to the database images. And then you get a list of candidates and then you refine them, right? So the first, and to do this retrieval, the types of ranking losses you minimize are like pairwise ranking, where you have positive pairs and negative pairs. So here you have Steph Curry, you have positive pair matching for Steph Curry and negative Klay Thompson for matching with Steph Curry. And you can be doing the Siamese network, be training with positive and negative pairs, or you can train it with a triplet ranking loss function where you have both positive and negative at the same time, and you have a function which combines the both. So people typically have been using these methods to do retrieval, and the triplet ranking loss is actually quite popular. But as you'll see, there are newer techniques which also perform better. So one of the first papers for doing this was this paper of CVMNet using deep learning approaches, where they use the CNN for cross-view matching. The CNN was the base architecture to get the embedding, and then they use NetBlad to extract global descriptors. And then they did this, they trained it using a Siamese network on this problem. One of our presenters, Yujo, she actually had a breakthrough in this area, and she's going to talk much more about it. I just wanted to mention it briefly to talk about my parts. One of the breakthroughs which she had was instead of matching the aerial image directly to the ground, the idea was to do a polar transformation to the aerial image and then match that to the ground image. And when you do the polar transform into the ground image, it creates transform the aerial image to a polar transform aerial image and add some distortions. So then she also had a technique to do spatial aware position embedding, where she's does feature max pooling to decide which channels have the more information, and then also importance generation based on attention to decide what to pay more attention to. And she had multiple of these spatial aware position embedding modules. And this technique is called SAPA, and it was published in Europe 2019, and she will talk more about it. And I just wanted to mention one more work of hers, and again, she will talk more about them, but where she did both joint location and orientation estimation by cross-view matching. So previous techniques were just matching for trying to retrieve the best image. Here, she was also solving for orientation by actually doing a correlation across different orientations between the embeddings and choosing the best one for the triplet loss. And this technique is called DSM, dynamic similarity matching. So in the work which we've done, we built on this work, and that's why I wanted to talk about these two techniques before. And the work which we have done in my group has been, what we did was, we take the satellite image, we apply a polar transform to it, and then we are matching it to the ground image. And again, we are trying to find the best orientation. We don't assume the orientation is known, but we did two changes, two additions to the work done before on DSM and SAPA. And one was we used a transformer instead of CNN. And the second thing was we changed the loss function. So in our application, we really want to know the orientation very accurately. And one of the things which we did was we have an orientation loss, which is given by this term over here, the orientation weight factor, and we multiply the triplet loss with that. And so we minimize this new loss, and I believe that actually improves the results quite a bit. And in subsequent work, we've also separated these loss terms, and that increases the results even more. So this work was published in VR 2023. And you can see the results over here. This is on CVUSA ranked at top 1. SAFA had 89.84%, DCM was 91.96%. And these techniques like L2R and Transgeo that we worked on by CJ and all using transformers had 94.08. And with this, you get 94.89%. And similarly, there was an improvement on CVACT. Then we also wanted to see how well this does for calculating orientation. So on CVUSA, we changed the embedding size to be 360, the final embedding size, which is predicted, so we can look for accuracies up to 1 to 2 degrees. And then using this technique for CVUSA, we are able to get about the orientation within 2 degrees to be at 93% of the time. So we weren't happy with just training with CVUS and CVACT. For us, our real application is to do outdoor augmented reality. And for outdoor augmented reality, we need to know exactly where the user is and where they're looking, so we can insert icons accurately. As you can see over here, we're inserting these dots on these antennas and this bulldozer over here. So, and we also wanted to test it when we don't have GPS and we don't have sensors such as micrometer. A micrometer doesn't work because you're near some metallic thing. So for doing this, we built an augmented reality system, and we have multiple versions which we built in our lab. Here we're using a real sense for tracking a user as they're moving around, and we have a video see-through GeoVis visualizer. So given, in the real sense, there's both video streams, IMU, and a GPS, right? So we have a visual inertial odometry module, which gives you both camera frame and initial pose. And then that camera frame is sent to a geostationary module, which is trying to match to this reference satellite image database. And then we're trying to calculate the best orientation. The tilt and the rotation along the camera axis, we can just get from the IMU. So for the global orientation, we're just trying to get the heading, and the location we are getting by just from the filter which is combining the visual initial information with the geostationary module heading information to keep track of where you are. So to handle the real world sequences, we had to do two things. First, as I said, our camera only has 70 degrees field of view. So we had to fine tune the neural network to work with smaller field of view data. And then we explored both CNNs and transformers to build the base model. Now, CNNs have an advantage when you go to different fields of view images over transformers, because transformers, when they're trained, are trained with a position encoding. And CNNs don't require that, it has an implicit position. So you can apply images of different types without having to retrain them. So I could train on, say, CVAct and CVUSA, which has 40, 50,000 pairs of images, but then I can use that now to fine tune on a smaller network, which has a smaller field of view, right? So I can apply it for different things. That's one advantage of CNNs. And then again, in an application, we wanted to run on processors with the users wearing. He's not or she's not connected to a cloud. It has to run in real time on what they're wearing. So CNNs are more efficient for that. The second thing which we want to do, as you'll see, the results improve a lot with the larger field of view. So as you're moving, you're only getting a 70-degree field of view image. So we have to update the data. We want to combine data across multiple frames to get a larger field of view, an effective larger field of view. And this is while you're moving. For the cold start situation, we can build panoramas where the user can just stand still and rotate the head, and you can build a panorama, and that will show you. You can use that to the cold start when you're starting off. But when you're moving, you've got to combine them as you're moving. And then finally, we wanted to have a confidence metric so that the filter can decide when to use the solution and when not to use it. So, so what we do is to handle multiple frames and to produce a high confidence and stable estimate, we calculate the similarity scores for each frame. For each frame, we do the retrieval and get the best scores. And then we combine them. And the way we combine them is we have a very accurate visual odometry. So from the visual odometry, we know how the subsequent frames you've moved. And so with that, we can shift the subsequent frames orientations, estimates to be able to line them up and then add them. So, so this accumulated data over multiple frames is what we use to then calculate the final match and also the final orientation. We also, for our outlier rejection, to decide if we want to use it or not, we do a ratio test between the first and second matching scores. So the first and second matching scores are very close together, then we say we should not use this. And then secondly, we also want to get enough field of views. So we have this trade-off. You can, as you walk, your head moves around some, and so we can collect data over multiple frames, and then we can say, okay, we've got enough field of view now, so we're going to use this. So this is a sequence which you're going to see. In the beginning, you can see red is the ground truth, green is the predicted, and you can see in the beginning it's not matching. This is the aerial image on top. That's a polar image in the middle, and the video frame in the bottom. So as I play the video, you can see the green will match with the red, and that's what's happening over here, right? And this is the kind of accuracies we are getting. We trained the data set on CVUS, CVAct to begin with. And when we tested in Mercer County, New Jersey, if you have 180 degrees field of view effective, we were getting about 69% to be within 2 degrees orientation. And if we fine-tuned it, then we went up to 0.94%. Right, and then similarly in this other data set on Johnson County, Indiana, we, it was 71 and 85 after fine tuning. And actually, in our paper, we have results on more data. And then this is actually using it for navigation. We want to know how accurately can we locate where the user is with this whole system. Not only where are they looking, but where exactly they are. So in our data, when we collected it, we had both GPS and magnetometer available for the whole sequence. If we just use that with the visual inertial odometry, then an RMS error for locating the user is about 2.15 meters. We are comparing it to differential GPS. If we use the GPS magnetometer available for the whole sequence, and then also did the cross-view registration, then the RMS error went down to 2.08 meters. And if we did the GPS challenge case, that only the GPS was available at the beginning, and after that it's not available, then the RMS error is about 2.51 meters using this technique. And this is the augmented reality. So you can see when you insert something, it's got to be very stable. It should not jitter, it should not drift. And you can see we're inserting these bulldozers and tractors and those dots. And as the user is walking around, it's very stable. Okay, so there's been a new paper, which I'm not sure has been published at a conference. It's an ARC-XIV. And actually, this paper has the best results so far that I've seen in this problem. And this paper is called Sample for Geo. And you can see the link below in ARC-XIV. And this paper has three innovations. The first innovation is that instead of, in this field, we started off with CNNs and we went to transformers, and this paper goes back to CNNs. And they use what's called a convex model. And this was a paper published, it's a ComNet for the 2020s. And this is a very nice paper, it's actually from UC Berkeley. And what they did was they looked at what works in transformers and what works in CNNs. And they came up with a CNN architecture which has elements of both. And they show in their paper they actually get better results in transformers by using this. The second thing which this technique does is they sample hard negatives. So they have a lot of focus on sampling hard negatives. They use geographical distance to sample hard negatives, and they also use visual similarity to sample hard negatives. And then thirdly, instead of just using a triplet loss or a Siamese network, they exploit all the available networks in a batch. So in this slide over here, so say this is a batch where you have a query image and you have a bunch of reference images in that batch and you're training it. So in their loss function, they'll take for every row, and if you have a symmetric one, and for every column, they take all the negatives. So they will, the numerator is just the positive error term, and the denominator is all the negatives which are there, and they do that. And in their paper, they go through the ablation studies about how each one of these things helps. So they have, as I said, the best results that I've known in the CVUS, CVAC ones. Previously, remember in our paper, we said we were getting like about 95 something. So they've jumped up to 98.68 for rank at 1 at CVUSA and 90.81 for CVACT. And they also tested on the VGOT data set. And again, they have the best results for rank 1 on the VGOT data set. So those were the approaches, one set of techniques where we were matching invariant features or doing things like polar transforms to match to ground views. There's an alternative set of approaches which are also there, where you're projecting the ground image to an overhead view or a bird's eye view and then matching that. So the idea here is and this is actually coming from lots of people working on autonomous cars. So in autonomous cars, they have cameras looking in all different directions. And so you have front, left, front, right, back, left, back, right, things like that. And you're trying to create a bird's eye view over here, which is talking about what's drivable, where there are vehicles and things like that. It's like a semantic bird's eye view, right? And there was a nice survey paper on this, which was published this year in ARC-XIV. You can search for it, which talks about all the different techniques being used for creating perspective views to bird's eye views. So there are techniques based on just doing point-based transforms or voxel-based transforms. or techniques based on transformers and doing network-based, the geometry-based bird's eye view or network-based. On a network-based, transformer-based methods. So one of the papers, which is a very nice paper, which appeared last year, and actually this paper won the best paper prize at ICRA 2022, is called Translating Images into Maps. And here, what they say is that if you look at any column in a ground image, it will match to a ray, a polar ray in the bird's eye view. And that's what this animation is showing. And if you remember how when transformers were first published in 2017, their first application was translation, right? And so what they're saying is this is just a translation problem where you're translating from a column in a ground image to a polar ray in the bird's eye view image. So they use a transformer to do that. And they do that for each column. But the weights for each column when they do it are the same. So if you think about it, this technique actually becomes convolutional along the rows and a transformer along the columns. And you can see that more over here, where they take the image, they have multiple layers of the embedding over here. They encode it into a transformer, and then they decode it to a bird's eye view. They resample the bird's eye view from polar to rectilinear, and then they have different heads. You can have a head for segmentation, you can have a head for object delineation, things like that. So in their technique, they weren't using it for doing air-to-ground matching. They were just using it for doing this kind of the semantic segmentation of the bird's eye view. So they're saying over here, like these are the different semantic classes which they're getting, and they show that they were getting state-of-the-art results. Like for drivable surface, they were getting 74.5% accuracy for IOU. Things like motorbike, which is very small, the IOU would be small. They still detect the motorbike, I think, but the IOU would be much smaller because it's a very small region. Okay, so that was a nice technique. There's another paper which appeared in ECCV 2022 called BEFFormer, which is also a very nice paper. And what it's another way to create these BEV images. So you have these multiple view images, and they do it over time. So the previous BEV image from the previous time is as one input to the transformer, and the BEV query, which you're trying to generate right now, is the other input. And then they're doing both temporal self-attention and spatial cross-attention. The temporal self-attention is for any new, at this time, you pay attention to what was there in the previous time at that location. And the spatial attention is for any cell over here, you pay attention to all the ground images you can see. So you take a location over here, and you can form a pillar of heights, and then you can project each of these to these ground images and say, would this location be visible in this ground image? And then you get, and so you get different inputs, and then you combine them to produce an embedding. So they have a transformer to do this, and they have very nice results with it. So one of the talks you're going to listen to next is this talk on uncertainty-aware vision-based metric cross-view location by Rory Furvers, and this is a slide from him, and he's going to talk about it, where he gets very nice results using these techniques. And I was particularly impressed by his results, so I invited him to give this talk. And he'll talk about it in a few minutes. The next set of techniques I'm going to talk about are cross-view matching, 2.5D ground images, 2D ground images, 2.5D overhead reference. Here, I'm going to talk about work being done in Ohio State University under Professor Rongjoon Quinn's lab. And they are experts in satellite image processing. So given satellite images, they can generate all these 3D maps and things like that. So the technique they developed is they take the overview images and the street images. From the street images, they find building segments, both in the aerial image and the satellite image, and then they match these image segments. And after that, they match these image segments. They have both frame to frame between the video sequence and the ground images. They have matching between aerial and ground segments, and then they solve for the pose and they do a bundle block. And they do a bundle adjustment, and they get very nice results. So this is, they just driving around with one GoPro camera, which is what you see over here. Oh, yeah. So this is a sequence. This is in Columbus, Ohio, around the university, and they're driving around with it, and they're matching to the bird's eye view images. So I remember talking to Ramjun and asking him, how come you just, the only edges you use are the building edges and not, you have other edges there in the scene too. And he was saying one of the things which are most stable in the satellite images to get at the edges are the building edges. So you're finding in the ground image, the building to road or building to pavement edge, and then by doing semantic segmentation, and then in the satellite image, you're also finding that, and then you're trying to match those graphs, and then combine it with the SLAM. This is the technique and animation of the technique, where you can see the street view segments are being matched, and then this is the final result. And then after they match it, see, when you did the visual odometry just by itself, it wasn't closing the loop, but after they do that, they're able to close the loop and make it all match together. So, and here, after doing that, you can overlay the one point cloud on another point cloud, as you can see over here. Okay, so now I'm coming to my final set of techniques, which is cross-modal matching, matching 2D ground images to LiDAR reference. So here, what we want to do, the first set of techniques we did here was by matching skylines. So given an input image, we can do semantic segmentation. You can use your favorite semantic segmentation technique and come up with different semantic classes. And from the semantic classes, then you can find the skyline boundary. And now you can do the same thing in the 3D terrain data to find the skyline boundary. What you do is you render the reference image to be from where you think the ground image is, and then you can find skyline boundaries. You render it for different locations, and then you match those. And that's what you can see over here. So here, as we are driving, you can see we're driving in Princeton, and in the middle column, you can see the skyline matching to as you're driving. And in the bottom, you can see in a rural area. So in the urban area, the skyline is mostly building roofs. In the urban area, it's mostly tree lines, right? And this technique works really well, and as long as the skylines are visible, and you can get to about half-degree heading accuracy using this technique. So another technique we developed was cross-modal vision-based geolocalization, where we're trying to match the ground image to different modalities. It could be radar, it could be LiDAR, it could be IR, right? So how can we do that? So what we do is we train joint embedding between the modalities. So we have geotagged cross-modal pairs between, say, image and LiDAR. And what we're doing is we're taking the LiDAR and actually rendering it from different viewpoints, right, on the ground. So we're projecting it, taking the aerial LiDAR, projecting it from the ground, rendering it from different viewpoints, creating a library of rendered LiDAR images. And then we're learning a joint embedding between the image and the LiDAR. And you can do it in a symmetric sense, where you given an image, you can have positive and negative matching examples for LiDAR. And given a LiDAR, you can have positive and negative examples of matching images. And so you can have this symmetric error function to learn this joint embedding. To create the data set for training this, The state of New Jersey provides LiDAR for all of New Jersey, probably old, but it's there. And so we use Google Street View, and we made about 550,000 cross-modal pairs around across 143 kilometers square area in New Jersey. And then we use that to train it. And this data set is available in the paper also on this topic. So then to match it, to do the error terms, we do two things. We have the ground image, we have the LiDAR image, we do appearance and semantic segmentation. So we have error terms, we do the embedding ground image to LiDAR appearance, ground appearance to LiDAR appearance, ground appearance to LiDAR semantics, and vice versa. So you get all four types of terms, and you're learning these embeddings, and then you fuse them to get the best result. And with this technique, we were able to basically, the average median rank is 5 for our matching over 143 kilometer square database. So testing over the whole database, the top answer will be within the top 5. The best answer, correct answer will be within the top 5, 50% of the time, right? Okay, so to summarize, I presented techniques for cross-view matching, 2D ground images, 2D overhead reference, cross-view matching, 2D ground images to 2.5D reference, and cross-modal matching, 2D ground images to LiDAR reference. So any questions?
You do the rendering from the 3D LiDAR images. So how do you deal with this different views and this specific view of the image?
Right. So we render it for, say, every 60 degrees, and for every location we are rendering it from
which one do you use as positive and negative? Is another view of the same image of the LiDAR is negative or not?
If it's in a different direction, it would be negative. If it's in the same direction, if it's an overlapping direction, it would be positive. Otherwise, it would be negative.
How many views of the same scene in the image do you have? On average.
I don't remember the exact details. It's in our paper, but we'd be rendering it every 60 degrees or so. The 6 from every location.
So although in the images you have
images, we don't know what we have.
views of the same
The images are just when we trained it, we used Google Street View. So whatever we got from that, right? When we test it, it's what we actually tested on real data. Right. Go ahead.
I think that let's say the source LiDAR point clouds were from overhead, like area.
Yeah.
So if you render it from the ground level perspective, is there not a problem with lack of walls and these vertical structures? It's possible to render them.
So when you render them, you have to take you would do occlusion reasoning.
Yeah, so you are right. Yeah, so there's a problem that if the reference data is aerial LiDAR, right? So you render from the ground viewpoint that some information will be missing. So we do use some pre-processing technique to fulfill some missing information. And also during the rendering that to adjust that how to render the different sample points that to make it look more realistic. Yeah. So there are some pre-processing need to be taken care of. Yeah.
You can also range gate the LiDAR when you render it. Any other question?
Regarding the satellite images or you notice like any difference in the resolution, like the resolution?
That's a good question. So typically in all these images, we've been using 1 meter resolution images. But it's a good question, especially when you have a ground image and you're looking far. And so then you have, if what we find is many of these data sets, like CBUS or CVPR, the satellite image is very small. And in many times, when you're looking far, you don't see what you see in the ground image, you don't see in the satellite image, right? So we've been thinking of techniques where you can actually have a more a way to represent larger images, have a multi-resolution way to represent the satellite image, so you can actually have a much larger satellite image effectively. You want the higher resolution close by, but you also want to take advantage of what you're seeing far away. Right. Any other question?
Okay, so let's thank the speaker, Teddy. Yeah.
Okay, so I'll give it to the next person.
Instead of Mac forecast.
There's something on my screen? No, I didn't see any. There's no share screen yet. Okay, yeah. Yeah, he hasn't shared the screen.
No, I'm just joining the.
Oh.
I just drop on.
Oh.
I think we need to approve each.
Oh, approve? Oh, okay. Oh, you join again. Okay, hold on. Okay, yeah, approve it.
Okay, thank you. Share screen. This one is the most even. Okay.
Okay.
Okay, all right. Good afternoon, everyone. I think here are echo. This is mine. Yeah, I don't have audio here. So can anyone online hear me?
Yeah.
Okay, cool. So, okay, my name is Chen Chen. I'm assistant professor at CRCV at UCF. For today's talk, I'll talk about towards real-world cost view geolocalization. So actually, this talk is mostly my PhD, former PhD student, Dr. CJ Zhu. He's here. So he's almost all these are his work during the PhD study. So first of all, I'll give a brief introduction about image geolocalization. Then I'll talk about the cross-view image geolocalization from 3 different aspects. So basically these our recent 3 papers, then I'll talk about some of the future research directions. Okay. So I know you guys have been heard a lot of these image geolocalization, but I'm gonna define it again here one more time. So you have an input image, right? So probably you took a photo at some of the tour place, and you want to figure out, right, what is the GPS location? So you can have a latitude and longitude, so you know where this picture is being taken. So how can we do the image geolocalization? So the general framework is that you have a query image on the left, so maybe a street view image. Okay, and you may also have a geotagged reference database. Okay, so this can be the same view, right? So you have a GPS tagged reference database. You consider of the same street view images. And what you do is you basically find the match, right? Which one in the reference database matched the best with this query image. And since this database is geotagged, we know the GPS location. So whichever the best match you find, then you will use that as the prediction of the query, okay? So what if we don't have the same view reference database? We can also go with different views, right? So here, if the query is the street view image, then for the geotagged reference database can also be a different view, right? So here we have aerial image or satellite image. So things have a more coverage than the street view. So we basically do the same. We find the best match, and we're using that GPS tag as the prediction, okay? So here, based on the pipeline, we see that, right? The most important ingredient is how can we find the best match, given a query. So, given this query image, we have all these reference images in the reference database, right? How do we determine the similarity? So we learned this kind of similarity via metric learning. So that's the common approach we do. So basically, we have a query image, right? So this is the input, and we go through some deep neural network model, right? Either CNN or transformer, and we generate a feature embedding, right? So a feature vector. So this could be denoted by this red star here, and we'll also have in our reference database, we have a positive match, right? So this is corresponding to the query. And we also have some other negative images, right? Which has different GPS location. We all go through the same process. We go through some of the model to do the feature representation, and we generate some feature embedding. And the goal is that in this feature embedding, right? So this positive and the query should be close to each other, right? Because they are a positive pair corresponding to the same GPS location. But for the negative pair, right, because they are corresponding to the different GPS location, in the embedding space, we want them to be far away. Okay, so that's the idea. When we learn this network, hopefully they're able to distinguish, this positive pair and a negative pair. So one of the most commonly used loss function is the triplet loss. Okay, so we have a anchor or query, we have a positive and a negative. Okay, so that consists of as a triplet. So why is image geolocalization important? I think Dr. Kumar has mentioned a lot of application, right? The search and rescue. So that's a very good example, right? How this geolocalization can be used in real world application. So just to give you a couple of more examples here is that we can using visual localization to do this kind of automotive application, right? Navigation. So here is, they are using the geolocalization to do the street navigation. And, if you have a UAV, you can also using cross view geolocalization to do the pose estimation. Okay, so here are just a handful of applications of using image geolocalization. So in the morning session, we have a couple of speakers talk about the same view, image geolocalization. Here in my talk, I'm gonna focus on mostly the cross-view image geolocalization, okay? So one of the reason for cross-view image geolocalization is that the satellite view or area view has more coverage than street view for some of the developing country, right? So maybe they don't have a lot of Google Street cars drive around to take the photos, but the satellite image has, pretty much the full coverage over those areas. So in this case, our reference database will have cross view, right? Assuming the query is street view, then the reference database will be satellite or area view images, okay? So the first work I'm going to discuss is we focus on the orientation alignment issue in image geolocalization. So this is the joint work with my former student, CJ, and my current student, Tao. And this work is published in WCV 2021. And we also have a follow-up work, touch upon some of the visualization that is published in IEEE transaction on image processing. But for this part, I'm going to focus on our WACV paper. Okay, so I think you see some of the recent papers, they have shown very accurate result, right, on CVUSA. But these kind of high accuracy depends on some of the assumptions. One is the orientation alignment, okay? So here's what I mean by orientation alignment. So you have a reference database, right, this satellite image. So you have also the street view panorama. So just let's consider CVUSA data set example. So this is, I took these kind of pair of image from that database, and this is the orientation alignment or setup for that data set. So for the street view panorama, right, so on the left, you always have these corresponding to the south direction, okay? On the satellite view, okay, so this south will be pointing upwards, okay? So that's for all the pairs of the images in CVUSA, they have this kind of orientation alignment. So when you train your model, right, so they can learn this kind of, based on this kind of aligned pairs, they can learn some of the geometric correspondence between the street view and the satellite view, okay? But in real world applications, right, image may not be geometrically aligned, right? So you may not have this street view panorama. Let's say you only took like a 90-degree view, right? Maybe just a crop of this image, when this alignment information is totally lost in this image, right? So we have to consider this kind of more realistic scenarios. So this leads to several research questions, right? So how would the alignment information affect the retrieval model in terms of performance? And second is, without assuming the inference image pairs are aligned, how do we effectively improve the retrieval performance? And finally, right, is it possible to estimate the alignment information when no explicit supervision is given? So these are some of the research questions we aim to answer in this work. So let's first explore or try to answer the first question, is how the alignment information will affect the performance. So we did some experimental exploration. So what we do is that we took the CVUSA data set, and we have the training and the validation set. So let's just take the the common setting, right? We're using the aligned image pairs, right, for training and the testing or validation. And we're using the simple Siamese network, using the VGG network, and we got the the matching the top one recall accuracy. And we also did an experiment that is for the validation set, we randomly rotate this area view image, right? So when we do this kind of rotation, the orientation alignment has been destroyed, right? Because not every image pair, the south is always pointing to this direction, like the previous slide I showed, okay? So we did this kind of testing, and we found out the accuracy dropped significantly, right? If we train with aligned image pairs, but we test with these kind of randomly rotated image, the performance drop a lot. So since based on this experiment, we see that the alignment information has a major impact on the performance, then without assuming the inference image pairs are aligned, how can we improve the retrieval performance? So we approach this from the metric learning perspective. Okay, so here is the very simple or straightforward network architecture to do the image retrieval or matching. So we have this panorama street view or query image, and we have this reference area view image, since we are doing the cross-view geolocalization. And depending on the data set you are using, so for the CVUSA, we have the street view panorama, but for some other data set, we may only have this cropped street view image, right? So it's not 360 degree, maybe only have 90-degree view. Okay, but anyway, either case, we'll just feed these two images right into these CNN model to do the feature extraction or feature embedding, and then we using some of the matching laws to pull the matched pair close in the embedding space and push the unmatched pair far away in that embedding space. So there are several common matching laws we can use in this problem. So the first one is the triple loss function. So this is very straightforward, has been used a lot, not just for image retrieval like person re-identification, face verification, those applications as well, right? So basically we have the DP indicating the distance between the ICE anchor or the query and its positive sample, and the DN is the distance between the anchor and the negative sample. Okay, so we need to we also have to specify a margin, a positive margin. Okay, so the basic idea is that we want the distance of the possible to be very small, right? So we want them to be close to each other, but for the negative one, we have to be far away. Okay. If doesn't satisfy, meet this margin, right? So we'll incur a loss, right? Because we have this max between 0 and maybe some positive or negative number. Okay, so that's the triple loss. So this, so there are other loss functions. For example, this weighted soft margin loss function. So which specify as here. So I'm not going to explain every of these loss functions, but these are the commonly used loss functions in retrieval. And here is another matching loss, this binomial deviance loss. So basically, they separate these positive and negative samples. So you have the soft margin loss function here, and you can also specify these margin parameter for the positive and the negative. So actually inspired by this binomial loss, we proposed a new loss function. So the basic idea is that instead of just, you can only specify this alpha, the same alpha for, or same margin for the positive and negative, we provide more flexibility for the positive and negative samples. You can, alpha P and alpha N, and also the margin P and a margin N here. And we noticed that in the cross-view geolocalization, we only have one positive match, right? So for one query, we have only one positive sample, right, in the reference database. So instead of pushing, the negative, all the negative samples away, it will be much easier if we can just pull that matched sample to the anchor, right? Because we only have one positive sample in the reference database. So in order to achieve that, we can assign a much smaller value of alpha P than alpha N. Okay, so that's how we achieve this mechanism. So for more details, you are welcome to check our paper, how we derive this loss function. So we'll show some of the experiment result. So we test our approach on the CVUSA and this VO data set. So this one is a panorama for the street view, but for the VO data set, it's just a cropped view of the street image. So as compared to some of the existing approach, we have achieved the best accuracy in terms of either top 1% accuracy or top 1 accuracy. So this is the same for both of the data set. And we also experiment the method, our method, proposed method and the baseline, which using the soft margin loss. under two settings. One is with alignment. As I mentioned, the CVUSA, they have the alignment information, or we use without alignment information. That means we can, rotate the satellite image at random degrees to destroy that orientation alignment information. So based on the result, we can see that under both settings, our proposed method is able to consistently outperform the baseline. Okay. And here are some of the visual examples, right, of the retrieval examples, right? So on the upper is the street view query image, and on the bottom is the top 5 retrieved aerial image. Okay, so in this case, the top one is actually corresponding to the ground truth, right? So this is the positive matching of the area view. So this is another example. So we are able to correctly retrieve the top one as the ground truth for the VO data set, which is only a cropped image as a street view query. And we also show a failure case. In this case, the ground truth in our ranking is like almost 6,000, so which is way behind, right? But the top one, although has a very high similarity, but it's not the ground truth. So this is a failure case. But if you look at the street view, it's kind of do not have a lot of information, or maybe if you look at the area view, the reference database, right? So they bear some similarity with the ground truth. Okay, so we are able to show this kind of retrieval example, so that's great. But we also want to do some explanation, right? So why this network is make such decision, right? What kind of information the network is based on to predict this is the top 1 or top 5 ranked image, right? So we're using this GradCam as the visual explanation tool. So I think most of you guys maybe know this GradCam, right? So basically, it's a gradient weighted class activation map, right? So it's originally proposed for image classification. So if you predict this is a cat image, then you can this gradient cam will show, right, which pixel contribute the most to the prediction, right? So the higher color code here indicating those are the most important pixel contributing the prediction of a cat, right? So if you predict this is a dog, you can see that the activation map switch to the face of the dog, right? So we're using this gradient cam technique and trying to visualize, right? If the network predict this is a matched pair, we want to see, right, what kind of information the network is based on to make such prediction. So in this example, so this is the ground truth aerial image corresponding to this query. So the gradient cam shows that the most highlighted region are on this house area. So in the query, there's a house object, right? And also the area image, this gradient cam also highlighting this house, although from the top view. And we also show some other examples here. So this is another query example, and this is the correct match. So it's also highlighting on the house here. So that comes to our last question. So is it possible to estimate alignment information when there's no explicit supervision? So we did some experiment by rotating the original area view image, right? So here we are rotating the image into random degrees, right? 25 degree, negative 34 degrees, right? Basically, we are rotating this area image. And we're using the same trained network. We see that, even if we are rotating these aerial image, these activation map also will consistently highlighting the same object, right? So in this case, the most informative is focused on the road, right? So if we rotating this image, the gradient cam also highlighting the road region, right? This is original one. Even we rotate in different degrees, they're still highlighting the road. So this kind of, indicating that this grading cam activation map has this kind of rotation invariant property. So we can actually using this to estimate the rotation angle if we don't have an aligned image pair. So this is how we estimate the rotation. We have this grading cam activation map, right? Based on the activation map, we can do some set up a threshold to generate this kind of binary mask, right? So this yellow region indicating the most high, activated pixels, and we do this for the street view as well. Okay, and then the angle distribution of these activated pixels from two views would be similar, right? If the pair is well aligned, right? Because the activated region will mostly corresponding to the same object, right? In the previous view, in this example, we show this is a road, right? Maybe another view, another example, the highlighted region will be corresponding to the same house, right? Or same, maybe another different object. So, then we can basically, with this kind of angle distribution, we just find the cross correlation, right? The highest cross correlation, we can actually shift the distribution map, right? Trying to find the highest cross correlation, then we can calculate the rotation angle, which is the phi here. So here is the example to demonstrate this rotation estimation approach is able to estimate the rotation angle very accurately. So this is the ground truth rotation angle, right, 126 degree. And based on our approach here, using the grading cam activation map, we're able to find the predict rotation angle around 125 degree. Okay, so we also did some quantitative experiment in our paper. So we have some result there, but here we'll just show a qualitative example here. Okay, so in summary, in this work, we did some evaluation study and a visual explanation. That leads to a key observation, that is the orientation alignment has a great impact on the retrieval performance. And we show that the improvement on the metric learning technique can boost the retrieval performance, even if there's no orientation alignment information. And we also discovered that the orientation information between the cross-view image can be estimated when the alignment is unknown, right? By using the visualization technique, grading cam. Okay. So we, for the visual explanation, we also have a more detailed explanation. So here shows the animation is that when you actually have a, identify a single pixel, right? We are able to show the activation map, right? So how the network is predict, this is a corresponding match, right? On which region that is mostly related to this pixel. So since we have limited time, I'm not going to dive deep into this one. So if you're interested more into this kind of visual explanation, so you can refer to our journal paper here. Okay. So the next aspect of image geolocalization, cross-view image localization I want to touch upon is the spatial alignment issue. Okay, so this is the work vigor we published in CVPR 2021. So this work deals with the spatial alignment. So the existing work simply assuming that each query ground view image has one corresponding reference area view image whose center is always kind of aligned at the center of the query image. But this is not practical for real world applications because the query image can be generated at the arbitrary location. So here's what I mean by arbitrary location of the query image, right? So assuming you have a reference image, right, satellite image like this, and you may have a query, right, maybe placed on this location of the road, right? Maybe you also have another query image, right? So this is on the other, direction of the road, right? So indicating by this green star. So in other words, the query is not always going to be the center of this reference image, right? It can be any places for this reference image. So motivated by this observation, we proposed this bigger data set, right? And the one of the setting of the data set setting is that given an area of interest, the reference area image are densely sampled to achieve a seamless coverage of this area of interest, so that the query street view can capture any arbitrary location. So previous data set, they sample the GPS location not very densely, so the aerial image may not have overlap, right? So here is a non-overlapped case, right? So this is a one aerial view image. This could be another one. But if you have a query image, for example, this red star here, then there's no reference coverage for this GPS location, right? So you are not able to find a match in the reference database. So when we're creating this bigger data set, we do this kind of overlap sampling with 50% of overlap. So to ensure that there's a dense coverage of this area of interest, so any of the query location, they will have a reference image in the database. Another setting we consider when we create this bigger data set is that we are not like the prior setting is one-to-one correspondence, right? You have a one query image, you have a one corresponding match in the reference database. That could be one-to-many setting. So here's the example. So if this is the query location, right, the green star here, and this green rectangle square, which is like the center, the green star is the center of this green square. So this is definitely a well-aligned image. But we could also, because of the dense sampling, right, we could also have a this red square here. So this query location is still within this red square, but it's not center. So in this case, we still consider this as a positive match, right? Because they still cover the information of the query. And this is another example, right? We call this, semi-positive. So here's how we define positive and semi-positive. So if we consider this reference area image has the length of L, and we have like an inner square, half L, right? So if the query location is within this center square here, we consider this is a positive image. But if it's just outside this inner square, but still within this larger outer square, then we consider this a semi-positive, right? So here it maybe more visually makes sense, right? So this one is like barely on the edge, right? You can have some information from this query, but not a lot. Okay, so that's why we call this semi-positive. And we sample, we do this kind of image GPS sampling from 4 cities. So one is the Manhattan area in New York City, and the other is Chicago, San Francisco, and Seattle. And this is a comparison with the existing database. So then notably, we have not the one-to-one correspondence. So for each of the query location, we have 4 reference image in the database, okay? So to do the image retrieval on the bigger data set, we'll propose this coarse-to-fine cross-view localization pipeline. So for this street view image, right? So this is like as before, right? So this is the input. And for the area of reference, this could be either a positive image or the semi-positive as we show, right? So only cover maybe a small portion of the query. And we using the CNN network to encode the feature. And we also using the popular SAFA block to do the feature aggregation. And then we using the normal metrical learning loss, like the triple loss. And in addition to that, we also have a branch called the offset prediction. So that is, once we using the metric learning loss, right, we can find the top one retrieved area of image. We can using the offset prediction to kind of regress the GPS coordinate to refine the coarse GPS location we found by using the matching loss, right? Remember, we are not talking about the where aligned input. Here, this could be semi-positive, right? So that's why we need to do some GPS refinement. So if we find this is the top one match, then this is definitely not the accurate, right? Because the street view location is going to be on the center. So we have to figure out a way, how can we get from here to here, right? So we want to do some of the refinement. And since we are considering this semi-positive image, we propose to using this using the ratio of the similarity in the embedding space based on the IOU, the ratio of the IOUs. If we simply just considering the semi-positive as positive, we found out that the performance will drop. So here's the experiment we did, right? So if there's no semi-positive, and this we consider this is a baseline, this is the top one and the top 5 retrieval performance on the same area. And we only consider the semi-positive as a positive, we found that the performance drop. So this is kind of, makes sense, right? Because we force the semi-positive, which contains some of the information which is not corresponding to the query location, right? If we consider that as a positive, it may confuse the network, okay? But with the proposed IOU loss, right? We are using the ratio of the similarity based on the ratio of the IOUs is able to adjust that similarity based on the IOU. That kind of helps the performance. So compared to the baseline, and this proposed IOU loss is able to further improve the performance, both for the same area and across the area setting. Okay. Okay, so that's the retrieval part. So here we also have the offset prediction. So basically, once we have the retrieved top 1 area image, right? So we want to do some offset prediction regarding the GPS coordinates. So what we do is we're using the ground truth GPS coordinate and using this kind of offset loss as a regression loss to refine the GPS location. So our final method is called L hybrid, right? Because we have 3 different loss terms. We have the usual triplet loss, and we also have the LIOU considering the semi-positive. We also have the offset loss to do the GPS refinement. So with all these 3 loss terms, we have the best performance for the same area and across area setting. We also, besides these retrieval accuracy, right? We also do this kind of localization accuracy in terms of meters, okay? So on the horizontal axis, you will see this is the threshold in terms of meters, right? 5, 10, and 15 meters. So this means if your prediction, the distance of your prediction and the ground truth is less than this threshold, you consider that's a positive, prediction, right? Because the arrow is less than the threshold, okay? So obviously, right, if you relax this threshold, right, you allow for more arrows, your accuracy will be higher. But if you just look at one particular threshold, let's say 50 meters as the arrow, and our approach, right, this red line here is significantly outperform the other approach, right, the baseline and the SAFA method, okay? And so this is for the same area testing. And we also did the cross area. So cross area means we're using one area as the training data, but a totally different area, maybe a different city for the testing. So across the board, the accuracy will be lower than the same area because there's going to be a domain shift, right? Because the cities may have different buildings, styles, right? So the performance will be lower. But again, our method across this kind of threshold spectrum, our method is able to consistently outperform the other competing methods in the baseline. Okay, so here we also do some ablation study to analyze the effect of this offset prediction, right? If we only have the retrieval only, right? removing the offset prediction, that's the blue line here. But if we adding the regression, the offset prediction, we are able to further improve the retrieval, accuracy. And this is a visual example. See, show you how this offset prediction works, right? So this green circle is the ground truth location. The red square is without offset prediction, means you're just using the retrieve the top one image, the center as your GPS prediction. But after we do the this blue diamond here. But for the red square here is actually with our offset prediction, right? So we are able to get closer to the ground truth location if we do some refinement. Okay. Okay, so we also did some other experiment as noisy GPS refinement. I don't know if you guys have the experience, like you are using your phone, maybe in the New York City, they have those tall buildings, right? So your GPS prediction could be very noisy, right? So there could be an error, maybe 50 or 100 meters of error. So here, we want to apply this kind of visual geolocalization to do GPS refinement, right? So we want to see if our proposed method is able to, improve the GPS localization accuracy under a certain search scope. Okay. So here, the search scope, we have a couple of them. One is the 1,000 meters, which means in the training, we know the GPS ground truth, right? So we just, limiting your search scope to as the 1,000 meters at the radius, okay? So we're assuming that we know the ground truth is gonna be around this area, okay? So this definitely will reduce the search space, right, in the reference database. So the performance will be improved. If we further reduce the search scope, right, because that means you're narrow down the number of images in the reference database, the performance will further improve. Okay. So this could be used in this kind of noisy GPS refinement. Okay. So basically, you can using your noisy GPS as a rough location, right? Then you do narrow down the search, rather you search the entire database. Okay. Okay. So in summary, this work, we propose a new benchmark for cross-view geolocalization beyond the one-to-one retrieval, which is more realistic setting for real-world applications. And the method is able to significantly improve the 10-meter level accuracy, right? So for the same area evaluation, we are going from 11.4% to 25.5% accuracy. Similarly, we have considerable improvement for the cross-view evaluation. Okay, so the code and the database for the Vigor database are available. So if you're interested, you're welcome to go to this GitHub link to download the data set. Okay. Okay, so the last work I want to talk about is the vision transformer for image geolocalization. So this is the work we published in CVPR 2022. So we are using the transformer as the network to do the geolocalization. So as we see all these examples, right? So the cross-view image, the big challenge is the domain gap, right? So if you look at the visual appearance, there's very different from the street view and the satellite view. So all these existing approach, they suffer from the domain gap, right? So the top one retrieval accuracy is pretty low. But the recent breakthrough is brought by the Polo transform. So basically you can do some, using the Polo transform to basically you can using this equation to do some geometric transformation. So you have the area image and you have like a rough estimate of the polar transformed area image, right? It looks much closer to the actual ground view image. So in this case, you can alleviate the domain gap between the area view and the ground view. Okay, however, we did some experiment using the polar transform on our vigor data set. And unfortunately, we found out that some of the examples, this polar transform doesn't work well. This is one example we show. This is because the spatial alignment is not always like the center, right? So we have this semi-positive, and the query location can be arbitrary on this reference image, right? So in this case, if we do the polar transform, the transform image does not look very close to the street view image. And we also did some of the experimental result, right? Directly using this SAFA baseline, and we applied polar transform, actually kind of decrease the accuracy a bit. So how can we bridge the domain gap, right? So we resort to the vision transformer, which can model the global correspondence of the image. So here is just animation showing you the figure show the VIT block, right? So you have an input image, you split this image into small patches, and you do some linear projection to encode the patches, and you add the position embedding, right? So because here we are kind of, the position information has been is lost. So we added the position embedding with the patch embedding, and you go through the transformer encoder. So that's the basic of the vision transformer. And for our transgeo framework, so this is the input, right? So we have a street view image, and we also have an area view image. So we first, follow the VIT paradigm. So we divide this image into small patches, and we go through this kind of linear projection to do the feature embedding, and we add the positional embedding. And we go through some of the transformer encoder block, right? And finally, we have a embedding. One is for the street view image, and we also have one embedding is for the aerial image. Then we're just using usual triple loss. So this is, we consider this first stage, right? Nothing new here. Basically just, maybe switch out CNN with the vision transformer and do this kind of Siamese network using the triple loss, okay? But the second step is, we call this attend and zoom in, right? So basically kind of like a human, observe, right? If you want to see, right, is this image corresponding to this area image, right? You first do is, okay, let's find out in this query image, right, what are the most important objects, maybe the building or maybe some other notable landmarks, right? Then we kind of zoom in, right? So, enlarge the image to this area and, take a close examination, right? What's this object? So we follow the same idea is that on stage 2 is we have this attention map, right? So we get this attention map, then we go to this zoom in version of the aerial image. The reason we have the zoomed in version is because the in a lot of these cross-view image data set, the aerial image has a very high resolution. So typically what we do is we kind of resize the aerial view image into a smaller resolution for, to cope with the memory and computation resource. But we still have the original high resolution version, right? So that's why in the second stage with this attention map, and we can, using the attention map to find the most important region, right? Has the high activation. And we using that to go to this high resolution original input, aerial image input, and we can find the corresponding high resolution patches, okay? And in this case, we again are using these high resolution patches and go to this transformer encoder to generate the feature embedding, and also using the triple loss with the street view image. So you can consider this is the second stage is like a refinement. So here is just explaining how we do this like a non-uniform cropping or patch selection. You can say that based on the attention map, right? So, you have an attention map, we can do the binarization, generate this kind of binary mask. and we can go to this high resolution satellite image input, and we, based on the binary mask, we can select those high resolution patch, which is our most important, for the retrieval as corresponding to the query input. Okay, so we did that, and this is the retrieval performance on the Vigor dataset. So here we are able to outperform the existing approach across different evaluation metrics. Especially on the top one, retrieval accuracy, we're able to significantly outperform the existing approach. And we also did the meter level evaluation because the Vigor dataset has the meter level evaluation metrics. So again, across different thresholds, we are able to consistently outperform some of the previous approach. Okay, we also did another experiment on the CVUSA. So the query exactly located at the center of the reference area image. And again, our approach is able to achieve the best accuracy with these 4 different retrieval evaluation metrics. We also did some of the evaluation, not just in terms of retrieval performance, but we also measure the efficiency. So here, the efficiency, we're using the flops, right? The floating point operations, and we are has much lower G flops as compared to SAFA with polar transform. We also have less GPU memory. We also have some advantage in terms of inference time per batch. We also did some experiment with unknown orientation, right? So as we talk about in the first work, we can either rotate the aerial image into random degrees, or we can just do this kind of circular shift, right, of the street panorama, so that the orientation alignment is destroyed. So with this unknown orientation information, we also compare with our previous work with Vigor, and this transgeo approach is able to outperform Vigor significantly. Another experiment or ablation study we did is the limited field of view, right? Previously, we're considered the street panorama. So here we're using a 180-degree field of view, 90-degree field of view, and do this retrieval again. And under these 2 limited field of view evaluation, Geo again is able to outperform other existing approach. And here shows some of the qualitative result on the Vigor dataset. So the first column is the street view query, and the second column is the ground truth, and the last 5 columns are the retrieved reference image. So the red box highlight the ground truth, right? So the first example, the top one is actually the ground truth, and the second example, the top 2 ranked retrieved image is the ground truth. The third one is a failure case, because the top 5 does not contain the ground truth. But if you look at closely, it's actually not considered a failure case, but it's just the setting. In this example, we do have a ground truth that is located at the center, but the located image is not the center image, but you can consider this as a semi-positive, okay, as compared to ground truth, right? Because the location is still corresponding to the same location, but it's just not cover the exact the query location as the center. Okay, so we have other qualitative result on the CVUSA, so which is a well-aligned, spatially well-aligned database. Okay, so in summary for this work, so some of the previous work for the CM-based approach, they highly rely on the polar transform. So that does work well, but for the Vigor data set, we found out that with polar transform doesn't always work that well. But for our proposed transgeo approach using the vision transformer, it is able to achieve consistent better performance. And we can using the attention mechanism to remove a large portion of the patch from the area view. It does not degrade the performance. And with this kind of consideration, we can actually using the higher resolution of the original input to further improve the performance without sacrifice additional cost. Again, the code is available, so if you are interested, you're welcome to try that out as the baseline approach for comparison. So those are the three works I talk about, address different aspects for cross-view image geolocalization. Finally, I'm going to briefly talk about some of the future directions. One is we can consider same view and a multi-view cross view together, right? So you have a query, you have a reference. Maybe you can construct a multi-view reference database, not just a single view. You can have both street view and a satellite view image together. So you can do this, combine these two fields, right? Single view and a multi-view cross view. Another is the you can extend or generalize the image-based geolocalization to video geolocalization. So actually, we did this work. So this is a collaboration with Dr. Mubarak Shah on this video geolocalization. We actually proposed this gamma data set. This is published in ECCV 2022. So we have this dash camera for the street view. We also have the satellite view videos. So you can do video geolocalization. So maybe this is more realistic, right? If you have an autonomous driving vehicle, and maybe in the city, you want to do GPS refinement, right? You can using the dash cam, using this, train this kind of network to refine the GPS location using the videos. So for the video, because you're not considering a single image, right? You can consider multiple frames, right? So these temporal information can further bring additional cues to improve the geolocalization accuracy. So you're welcome to check out this database and use it for research. Okay, so these are some of the reference I talk about in the talk. And finally, I just want to, we have a work at CVPR here. So if you're interested in same view geolocalization, you're welcome to the poster session and talk to CJ. Okay. All right. Thank you.
So actually, we have an online question here. Yeah. Okay. You want to display it? Okay, maybe I should. Okay, on page 17, you rotate the. Yeah, page 17. Yeah. On page 17, we asked to
17, this one?
asking to unmute and yeah, I think he's unmuted, but we cannot hear.
Can you hear me?
I'm actually muted. Do you want me to open the volume? Okay.
Can you hear me?
Yeah, I can hear you.
Yeah, thanks for the great talk. Yeah, on this page, I'm wondering, did you ever try to rotate the ground panoramic image by like appending the leftmost columns to the right? And
Yeah.
Did you observe a similar performance drop? I'm asking because I wonder if this performance drop because of the black area introduced by rotating the area image.
Yeah, that's a good question. So yeah, if we rotate this panorama, the satellite view, right, you see this kind of black region, right? Because we can do some padding or we just ignore this. Yeah, you describe another way we can kind of destroy this kind of alignment, orientation alignment information by, because this is a 360-degree panorama, right? So we can just do this kind of shift. I'm not sure if we tried. CJ, did we try this?
Yeah, I can say this, but basically we also tried this in the bigger data set shifted. But here we didn't using the shifting because we also want to do limited field of view. In some of the data sets they don't have the panorama, so you cannot do the shifting So at that time, we didn't try it in this work. But for the performance drop on the left side, that is because the during the testing, the image is randomly rotated, but during the training, it's not. So that's why it's
Yeah,
But
yeah.
On the right side, if you do the rotation on the training and the testing, then the performance is actually there is no drop.
Yeah,
Okay.
so yeah, so I think you are kind of questioning is because the performance drop is because of this kind of black region, right?
Yeah, I guess partially, I'm
Yeah.
just guessing.
Yeah, yeah, but I think CJ just answered your question. So if we have another setting right here, we have this rotated training and rotated testing, right? So the performance doesn't drop. That kind of says this black region is not the main contributor or doesn't contribute the performance drop. Is because of the orientation alignment information. But definitely you can try, do this kind of disturb this alignment information by shifting this street view panorama. Yeah.
Yeah, thanks.
Yeah. Yeah.
You talked about this semi-positive,
Yeah.
the samples, and you showed an example that there is a wrong actually retrieval because of that. So how clean are these data sets or test sets that you really benchmark on them? Can you say something about the vigor of the data set and others? Question is how many semi-positive there could be there, that can actually, argue the results or give you some acidic results. Maybe they are much better.
So you're asking about how many semi-positive for each of the query in the reference?
Yeah, in the reference gallery or in the reference set, how many semi-positive do you believe that there are? I don't know. Did you go on clean this data set or, other data set? What can you say about how clean they are?
Yes, so maybe later CJ you can add. I'll just know what I tell you what I know. So we have, if you look at the data set comparison, we have provided each of the query, you have 4 reference image in the reference database. So maybe CJ you can answer how we have the reference database.
Yeah.
Those 4
so,
images.
For each of the location we collect, like we have at least 4 reference images that could be correct. And one of them will have the center, cover the query in the center area. So that one was positive, right? That's the most information. But the other ones may be semi-positive. But I have to say that semi-positive is not wrong. They are just contain less information than the positive. So if your prediction is a semi-positive sample, it's okay. So it still have a very close GPS location. And our final evaluation, if we were using meter level evaluation, then this would be no problem. But the problem shows that is because we only use it retrieval performance, then it will be a problem.
But statistically, how many semi-positive gonna be? Is it always gonna be like 2, 3 or 4? Okay.
Not real 4, but there are.
Yeah.
You can have nearby, but in the measure, if you are going to measure the errors in meters, so.
Yeah.
You just give
Yeah.
Those ones.
Yeah.
Not interesting.
Okay. Is there any other question? Yes.
Yeah, in your transformer, have you noticed any special pattern of the attention map? Like, for example, it focuses on the street pixels.
Oh, you are.
And if that's so, like, that also could be like leveraged in the offset estimation point that you found earlier. Because by definition, in a street view image, well, the vehicle has to be in the street, so.
Yeah.
So the street pixels should be kind of the major factor of correspondence on. So for in other words, like you cannot have the center in a non-street pixel. So this condition is that with something to itself, the offset estimate.
Well, I think in the bigger data set, you can always using the offset prediction because as we just mentioned, we have the semi-positive. So if the top one retrieved is the semi-positive, you can always, refine that. But, like for other data set, like CVUSA, is always assuming, or when they collect data set, the query or the reference is going to be set as the center aligned. So I don't know, that's considered the ground truth. I don't know how, if you do some offset prediction, then because you're using that center as the ground truth to the evaluation, but if you do this offset, then you're gonna mess up that accuracy. So, but I think for the realistic scenario, right? So, yeah, you can always using this kind of offset prediction or use some of the cues to kind of correct or refine the GPS prediction. Yeah. Does that answer your question or?
Yeah, and regarding did you notice that like there's a specific pattern like regarding the street pixels and the adventure app or?
Yeah, I mean, it depends on the example you have, right? So. Yeah, I don't think there's there must be some examples that focus on the road. I think when I showed this CVUSA, they, especially it's not in the city environment, you only have the road and the trees, then most likely the attention will be focused on the road, right? The layout of the road, the direction of the road. So in that case, but for the cities, maybe most likely will have those buildings because those are considered like more prominent features for localization. Yeah.
But yeah, like the roof of the building.
Yeah.
It's not visible in the street, so most probably not find there. And it's more paying attention on that the case or.
I don't think so. In this case, we do have, right? So here we actually locate this. We actually find this. This is a building. Like part of the building. I think this is also another building. Right? So, correctly. This is another building. So the attention also select this side. Yeah. It's really hard to to tell what exactly they're based on. Yeah.
I have actually a follow-up question. How does it depend on the angle of the viewing angle, from the top? If you take ortho photo images, so do you think that the performance will drop or how will it?
So the auto, you mean 45, like a bird's eye view? 45, you have some facade of the.
Actually, it's like you're taking a picture from 90 degrees from this.
This is the top one.
This is the top one.
Yeah, this is.
But this is it for photo?
Yeah, this is the top one. But like the 45, like the bird's eye view, like 45-degree, definitely there will be input. We actually have one paper on the street view and bird's eye view, 45-degree from the Bing map. So because in the 45-degree, you can still see like a facade, the side of the building, so much more visible. Here you can only see like the roof. So there's a much larger appearance gap compared to the street view image.
It's also other states, but the main thing is what the orientation of physically compared on. And you have some results on that orientation, right? In this paper.
Yeah, the orientation is not the tilt. Yeah, it's just the alignment information, but not the viewing angle. Yeah, but the viewing angle, we have this the CVPR 2017 so we have the bird's eye view and the street view that could be doing this data. Yeah. Yes.
So for the matching experiments, your training results, is that matching against the entire database data set, or is that matching against already reduced subset based on GPS?
So in most of the cases, or the regular setting is we consider the entire reference database. So I did one experiment is the noisy GPS refinement. That's a reduce the search space because we want to simulate you are driving or you are using a cell phone, you have a noisy GPS, you have a rough location, right? So it's no point you search the entire city if that's your reference database. you can just build the proximity of your GPS, the core GPS location and reduce the search space to get maybe a better retrieved result. Yeah. Yeah. Yes.
I think it would be beneficial to some of the constraints that you have between streaming and copy. It's a longer list, the rigid transform of viewpoints, so that doesn't seem to be included in the network. So, some of the false positives, I wonder if they're actually like mixing up left and right when that shouldn't be possible.
Yeah, so I think that's a good question. Did we do that in the same view? Like considering the R2 former, you also did that. I don't know if you consider like the direction left and right and the depth, maybe something. Or maybe.
Or like, in one of the earlier papers, you estimate the angle after
Okay.
you've gotten the heat maps, right? But if the correspondence included the physical constraints on the fact that you're actually going to get it here, then the angle would naturally come out of that.
Yeah,
You know what I mean? Like,
yeah.
like there's certain physical limitations on these two images that don't seem to be included in how that. So I'm curious if that would help.
Yeah, do you mean that the heat map, there could be like two objects like that, even like, and they're both matched and angle would be wrong or?
No, I mean, like, rather than having the network learn, like, the fact that physics means like the left on the right on the street means that the area is the same thing. You know what I mean? Like, there are certain properties of the scene that would be variant, but we look at it from street or top down. And I'm wondering if you can make that explicit. With help. And I'm also in the question, I wonder if some of the false matches you have are because the network isn't, making nonsensical basically matches between corresponding pixels.
Have you thought of that heat map, which you can use that for the future?
Yeah, the first one we have the.
Well, yeah, like there's it's a rigid transform from one camera to another, right? And if you include that constraint in the learning chart.
Compute the global script of image, so I can set up when you compute the global descriptor of the image, so to have these constraints which take place when you match two images. And set the global this is global descriptor, so it's difficult to take into account these, I would say, local descriptor matching constraints.
Yeah, so yeah, I think it's worth to try. Yeah, it's interesting. Yeah. Thank you for the comment. Yeah.
I have a question about the. No, final question. I have a question about the bigger architecture.
Yeah, bigger, right? Yeah.
Yeah, so with the bigger data set, you relax the assumption about the location of the big query, so it's no longer necessarily in the center, right?
Yes.
But the Sava block is translation variant, I would say, because of the MLP. While the ground truth location can appear everywhere in satellite image. So I wonder whether have you tested anything like an translation AP variant descriptor network instead of the Sava block?
Well, yeah, you mean like those like a net lot kind of thing?
Yeah, so what I mean is if you would slightly translate for a satellite image, so also the ground truth location translates, for example, to the left, and you are using an NLP in your Sava block for your descriptor, then you lose your translation AP variance because of your NLP, while your ground truth location is just shifting. So I wonder if you tested anything like a translation AP variance descriptor network.
No, I don't think we test that. So here we just want to building this kind of multi-level kind of feature aggregation. Yeah, but I think yeah, that could be something unique to the bigger data set because of the center is not always aligned. yeah, we can definitely try those and see if that can give better performance. But again, the point of this, we are not trying to building a specific like a novel feature extractor. But definitely the question you raised could be something particular to this data set. We can definitely try that out. Yeah.
Just to add it, we use Sapa block because Sapa was the state of the art when we built this data set. So we just want to show that, okay, the state of the art method performs like this, and we can improve this on that. That is what we want to show.
Yeah.
But definitely we want to using better architecture may get a better result.
Yeah.
Thanks.
All right. Thank you.
Okay, it's great. We have a lot of discussion. Yeah, that's great. Let's thank the Professor Chen again.
Thank you.
Mute. Yeah.
Okay. I think so. Yeah. Okay, finally. All right. My name is Florian. I'm a PhD student from Germany. I'm currently starting my third year. And I'm grateful to have been invited to this tutorial to share some of my work. Yeah, I will talk about the topic of metric cross-field geolocalization and our latest paper on this topic, which we published at this year's CVPR. And I will talk about some related and historical works. So first, the problem of cross-field geolocalization. I guess we've already heard a lot about it, but just to summarize real quick, we have some vehicle or person on the ground that is equipped with some sensors, like for example, cameras or range scanners. And then we have an orthographic map of the region that our agent is in. For example, like a visual map from Google Maps or semantic maps like building or road maps. And we want to find the location and possibly also orientation of our vehicle in this search region. Now, this is a very general class of problems that can further be divided into two subcategories: large area CVGL and metric CVGL. So in the first case, we consider very large search regions, for example, the size of a city. And a typical approach is to use image retrieval to solve this task. So we divide the large image of our city into smaller patches, and then want to retrieve the target patch that our vehicles are. Now, in the metric CVGL case, we have a smaller search region, for example, up to 100 meters large, and we want to directly estimate the pose of the vehicle in this smaller search region. For the large area CVGL dataset, there already exists multiple public datasets, like for example, CVUSA, CVAct, and bigger. But for the metric CVGL task, it isn't so clear which data we should use to evaluate our method. But I will talk about that more later in the presentation. So in this talk, I will focus on the second task, that is the metric CVGL task. And as a small teaser of what current methods are capable of, here are 3 papers from this year's CVPR. all of which did some kind of metric cross-field geolocalization. And 2 of them used RGB images, the first and the last. And in the middle, they used semantic maps from OpenStreetMap for the matching. All right, so generally, methods that do metric cross-field geolocalization can be categorized based on the types of features that they extract from the input images and that are then used to perform the cross-view matching. So the first category of features here uses rather low-level features. So for example, local feature descriptors like surf or sift, or they work directly with the raw input data. As an illustration, let's look at this example from 2011. Here they use surf features to match a ground camera to an aerial image. And of course, surf features aren't invariant enough for the viewpoint change that we have here. So from perspective view to bird's eye view. So the natural step then is to first project the camera view into a bird's eye view. And in this case, they simply use a homography for this. So they're making a flat ground assumption and then just geometrically projecting the front camera into a bird's eye view. One can, of course, use different methods here as well. For example, running a visual SLAM algorithm for reconstructing a point cloud of the environment, and then using that to do the projection from ground sensor view into the bird's eye view. Once we have the data in the bird's eye view, we can then perform the matching with the aerial image. So this paper here uses surf features for that. Other papers, for example, also do dense matching via a mutual normalized information approach. So this gives us a little overview over this first category of methods, but it also points us at some of the disadvantages. So even when we project our ground data into a bird's eye view perspective, these surf features still aren't invariant enough to the kind of changes that we have in cross-field geolocalization. So for example, changes due to seasonal and daylight variations, or something like vegetation growth, or the presence of dynamic objects like cars and pedestrians. Another problem is that we often have surface areas in the scene, like the walls and roofs of buildings, that can either be only seen from the ground perspective or from the aerial perspective. And therefore, there we, of course, can't use local feature descriptors for the matching. And lastly, we need an explicit method for the transformation between perspective view and bird's eye view, which in this case was a homography, but this has the drawback of making the flat ground assumption. And running a visual SLAM algorithm is often prone to errors and only also gives a sparse representation of the environment. Now, the second category of methods addresses some of these drawbacks by using higher level semantic features. So for example, buildings, roads, lane markings, etc. As an illustration, this is a small prototype I hacked together a while ago to kind of show how that would work. So here in the bottom, we can see a scene from the Kitty dataset. And in the top, we can see building outlines from OpenStreetMaps. So what's done here is we first apply a visual SLAM algorithm on the ground images to reproduce a 3-dimensional point cloud of the environment. This point cloud, we then apply a semantic segmentation on the input images to filter out those points that belong to the building class. And we can then project those building points into a top-down perspective to match them with the actual building map. And this is used to find the pose of the vehicle. Now, many variations of this kind of semantic approach are still quite popular today and are still being published, which is, in my opinion, due to one important property of semantic features, and that is that they are very invariant to the kind of changes that we see in cross-field geolocalization. So, for example, the semantic class of an object is going to stay the same, whether we look at it from the perspective view or the bird's eye view. It's also going to stay the same over seasonal and daylight variations. And we can specifically pick a class that is known to be temporally stable, as opposed to, for example, dynamic class like cars or pedestrians. Now, this high invariance of the semantic features comes at the drawback of having a low discriminance on the other hand. So the only way in which we can discriminate feature points from the ground and aerial view is that they have different classes. And this is, of course, not a lot of information to work with. And this is even further problematic when we are in areas where the given semantic class isn't even present. So for example, in a highway scenario, there usually isn't that much semantic information that we could get, for example, from OpenStreetMaps. So these kind of semantic features don't really work in those scenarios. Another disadvantage is that we also need the explicit method for transformation between perspective view and bird's eye view. And we depend on the quality of our semantic segmentation model. So the worse the semantic segmentation, the worse the cross-matching results. All right, so the semantic methods address some of the drawbacks of the lower level methods, but they also come the kind of layout of semantic classes that we get from typical data sets, like for example, cityscapes. These kind of classes aren't really made for the cross-view matching task. So we are kind of misusing the semantic features here. Ideally, we would like to have high-level features that are at the same time specifically tailored toward this cross-view matching task. And this is what leads us directly to the third category of methods, and that is the end-to-end learned methods. So here we build a model that takes as input both the ground sensor data as well as the orthographic map, and then directly outputs the geopose of the vehicle on this orthographic map. Now, since this is end-to-end differentiable, the only supervision we need are the actual ground truth geoposes of the vehicle. And when we train a model in this way, it can actually achieve a good trade-off between invariance and discriminants of the features. A second advantage of these methods is that we can include the transformation between perspective view and bird's eye view as a differentiable step in the model itself. So we can simply train this transformation using only the supervision that we provide from our ground truth geoposes. On the flip side, of course, when we want to train a model, we need large amounts of data and good ground truth. And I'll talk about that more later in the presentation. So to summarize a couple of end-to-end metric CVGL methods, generally, one can categorize them based on whether they require range scanners or whether they work vision-based only. The first ever end-to-end metric CVGL method was RSLNet from 2020, where they localized the radar against satellite images. And in a follow-up work, they showed that it is also possible with the LiDAR scanners. We published our work in this category in 2020, where we use a LiDAR and camera and achieve state-of-the-art performance there. Now, for the vision-based methods, there were some early approaches that applied the image retrieval paradigm from large area CVGL to the smaller search regions of metric CVGL. But what I think is the first dedicated method for metric CVGL is beyond cross-search image retrieval from last year's CVPR. All right, in this year's CVPR, we published our work on this topic, where we achieved state-of-the-art performance, even in a zero-shot setting, and we show that we achieve sub-meter accurate localization. All right, so in the rest of the presentation, I will talk about this paper of ours. So here we take the full surround view cameras of a vehicle, match them against an aerial image, and then predict the pose of the vehicle on this aerial image. Now the contributions are that we propose a novel end-to-end trainable model for this task that achieves state-of-the-art performance, even in a zero-shot setting. And we combine multiple public data sets and improve the inaccurate ground truth poses via a pseudo-labeling approach. We make the code and our ground truth publicly available. First, to explain the model that we designed for this task, on the right, you can see a flowchart of the model with the input images at the top and the output probabilities at the bottom. And in a first step, we first extract pixel-wise features from all of the input images using a simple encoder-decoder network based on the Confluence architecture. We're using one such model for the aerial image and then a second model for all of the ground images with shared weights. In the second step, we then project the features predicted for the ground images into a top-down perspective, so into a bird's eye view. Here we're using a transformer architecture with cross-attention, where the bird's eye view features cross-attend to the perspective view features. And this is done iteratively to build the bird's eye view map. And this final bird's eye view map is then matched with the aerial features, the features predicted for the aerial image, to find the actual pose of the vehicle. Now here we consider every possible pose hypothesis in the search region. And for every such pose, we first transform the bird's eye view map into the coordinate system of the aerial image. And then we compare the two maps and compute a likelihood score. And this then determines how likely the given hypothesis is. And when we formulate the hypothesis likelihood this way, we can actually jointly evaluate multiple hypotheses using a cross-correlation operation. And this can be sped up even further by computing it in a Fourier transform. And this joint evaluation of hypotheses is what enables good performance, even when we are exhaustively evaluating all of the hypotheses in our search region. So this entire model is end-to-end differentiable. Therefore, we only require supervision from the ground truth poses. And as a loss function, we simply compute the cross entropy between the predicted probabilities and the ground truth. All right, next to the data sets that we considered for training and evaluating our model, we generally considered sources, two different sources. The first source were large area CVGL datasets that we've already heard about. And the second source were datasets from the autonomous driving sector, like, for example, Kitty, Ford AV data, news scenes, etc. Both of these categories have camera images, but only the autonomous driving datasets also have LiDAR scans and continuous trajectories. The large area CVGL datasets have aerial images already, but this isn't a problem for the autonomous driving datasets, since we can simply fetch aerial images from other sources, for example, Google Maps or Bing Maps, or some local state provider like MassGIS. The main problem comes up when we consider the accuracy of the geo-registration. So typically in all of these data sets, the geo-pose of the vehicle is measured using GPS and maybe some post-processing. But in all of these cases, there usually might be some error of a meter or more. So the geo-poses of all of these data sets might not be that accurate. And even the geo-registration of the aerial images isn't always accurate. And lastly, it's hard to verify how accurate the geo-registration is just by looking at the images themselves. So for example, here we have an image from the Ford AV dataset on the right side. And then we have an image from Bing Maps on the left side, which is centered on the geopose of the right image. Now, just by looking at the images, it's very hard to say whether it's accurate or whether we're off by a meter or something. And this is actually where the first key insight came into play. And that is that the autonomous driving sector datasets also contain LiDAR scans. And when we project these LiDAR scans into the image, we can actually see how well they match up with the structures in the image. So for example, for the fence in the lower right, we can clearly see that it matches quite well with the LiDAR points. So we know that in this case, the geo-registration is accurate. And here's an example where it's off by a couple of meters. Additionally, we can now create a tool for manually creating such ground truth by moving around the LiDAR point using the arrow keys until they match up with the aerial image, and then deducing the actual geopose from that. And this is actually what we did in our paper. So given that the autonomous driving datasets contain LiDAR scans, we can use that to manually label individual frames in these datasets. Now, these datasets contain several millions of frames, so the individual labeling isn't viable. And this is where the second key insight comes into play. And that is that they also contain continuous trajectories. So that means that for a given trajectory, they always contain the translation and rotation between every subsequent frame. Now, these trajectories might not be that accurate over the long term because they're usually determined using some SLAM or odometry method, but they're often very accurate over the short term. And what we can therefore do is, instead of labeling every single frame in the dataset, we can label, for example, every 100th frame, and then interpolate all of the frames in between using the known short-term trajectory. And this allows us to label entire trajectories quite rapidly. Now, the dataset still contains several thousands of trajectories. So at this point, we decided to go with a pseudo-labeling approach. And pseudo-labeling means that we manually label a small subset of the data, then train a pseudo-labeling model on the smaller subset, and then predict new geoposes for all other data using the pseudo-labeling model. Now, as pseudo-labeling model, we didn't choose our vision-based model. That is what you can see here. If you remember, the center block was responsible for projecting the ground features into a bird's eye view. And since all of these data sets contain LiDAR points, and since the pseudo-labeling model isn't constrained to be vision-based only, we can actually replace this entire block with a simple geometric projection using those LiDAR points. Now, this new model actually converges a lot faster during training and requires a lot less data to train. So it's basically a perfect pseudo-labeling model. So to summarize the steps of our pseudo-labeling, we first manually label a small subset of the data. Then we train our pseudo-labeling model on the subset, predict labels for all other samples. At this step, though, the labels still aren't that perfect because the model might still make some mistakes, of course. So we need a fourth optimization step. And here we build a large post graph, and we include both the interframe transformations from our vehicles as well as the model predictions, and then just run a large least squares over the post graph to find the final optimized geoposes. In the last step, we then verify the accuracy of the geoposes using for a small subset of the data. So looking at our dataset considerations again, given that only the autonomous driving datasets allow for manual labeling and for pseudo labeling, this is why we decided to use those datasets, even though CVTL datasets already exist. Here are some examples of the pseudo labels. So here is the original labels, and then here when they are aligned. The second thing we can do with the pseudo labeling model is that we can remove invalid data samples from our data set. So, and we do that by looking at the prediction confidence of our pseudo labeling model for a given data sample. So for example, when the vehicle is going through a tunnel, which you can see in the left, as long as it's in the tunnel, it of course can't make an accurate prediction. Therefore, the prediction confidence is very low. And we color this trajectory based on the confidence of the prediction, and red means very low prediction confidence. And we can clearly see that this prediction confidence delineates the case where the vehicle is going through a tunnel and where it isn't. On the right side, we have a similar example where we have out-of-date data. So the aerial and ground data don't match up anymore because the road has been reconstructed at some point. And we can see that the driven trajectory doesn't align anymore with the actual road in the map. And what we do in practice is we just take the worst 1% of data samples based on this confidence metric and just remove them from the data set. Here's again a list from one of the data sets that we considered. So we combined a total of 7 public data sets, which in total had several millions of frames and over 2,000 scenes. And we collected also images from Google Maps and Bing Maps, as well as some local state providers. All right, so finally we can get to the results of the method. This is evaluated on the Ford AV dataset with a search region of 28 meters radius and 20-degree uncertainty in the orientation. And in the table, we are showing the recall, that is the percentage of predictions within 1, 3, and 5 meters. We're evaluating lateral and longitudinal locations separately. In the first setting, and that is the setting that prior works evaluated in, we are considering only the single front camera of the vehicle. And we are also testing and training on the same aerial images and on images captured using the same vehicle setup. And in this setting, our work outperforms the previous state-of-the-art by a large margin. Now, ideally, we would want our model to generalize to unseen aerial images, so unseen test areas, as well as to unseen vehicle setups. And this is what this second setting is about, which is basically the zero-shot setting. And even in this more challenging setting, our method outperforms the previous state-of-the-art. And lastly, we show that when including all of the full surround view cameras, this even boosts performance further by a large margin. So here are some qualitative results. In the first 2 rows, you can see the front and back camera of the vehicle from Ford AV data. In the bottom, we can see the predictions for 4 timestamps. The predictions are, of course, done using the full surround view of the cameras. As we can see in the first, second, and last column, the model can quite clearly predict where the vehicle is. And the third column is quite interesting because it has this repeating pattern in driving direction. But that is, of course, due to the scene itself having a repeating pattern in this driving direction. And this also highlights why often the lateral location is easier to predict than the longitudinal location. Here we integrated our model in a tracker setup. So we're using a Kalman tracker that integrates inertial measurements from the vehicle, as well as the model predictions, and use that to continuously predict the trajectory of the vehicle. The lighter points here, again, are shown only for visualization to kind of check out how well they match up with the aerial image, and they're not used by the model itself. We can also visualize the features learned by the model. So here we can see the aerial features learned by the model, where I reduce the channel dimension to 3 channels via a PCA and then map that onto RGMP. And we can kind of see what features the model chose to use for the matching task. So for example, we can see that it uses lane markings, which are shown in green. We can see that it uses vegetation shown in orange and red. We can also see that it sometimes uses building outlines, which are sometimes shown in green. And on the right side in the center, we can see that it actually learned to be invariant to the presence of cars. So as you can see, there are cars in the aerial image in the center of the right image, and they don't really disturb the feature map in those locations. So they're basically given the features of the ground below them, meaning that the model learned to be invariant to these objects in this case. All right, to summarize, I talked about some previous and historical works that use low-level and high-level semantic features. And I talked about the more recent works that use high-level end-to-end trained features and how they achieve a good trade-off between invariants and discriminants. I talked about our latest publication, where we introduced a novel model for this task that achieves state-of-the-art performance even in a zero-shot setting. And I talked about the multiple public data sets that we combined and improved and created improved ground truth for using the pseudo labeling approach. Lastly, we make the code as well as this improved ground truth publicly available. All right, thanks for your attention, and we can get to questions.
There is a question on Zoom. So
yeah, sure.
Maybe you can unmute and explain. You open the microphone. Can you explain the question to me?
Hi, can you hear me?
You open your
My power is on.
yeah.
Oh.
Is he speaking? No, maybe I can describe it. So his question is that you can click the chat. Did you evaluate the orientation prediction? How large are the mean and median orientation errors in degrees on 4 AE data sets when there is no prior orientation information?
Yeah, so the orientation error was basically almost always very close to 0. So we didn't really evaluate that, but we also found that the translation error is a really good proxy for the angle error. So we didn't include the orientation in our table there. If that answers the question.
We cannot hear from him, so
yeah.
Answer. Okay. Say yes. It's a yes. It's a yes. Yeah. Yeah. Actually, I just want to add some. So I think in the related works, you kind of missed some of the work from Zoom. So he's also working on this metric localization, cross-view localization. His work is published last year. Maybe you can add it here.
Here?
Yeah, maybe you can add it here. It's published in the ECCV last year. It's also, I think it's an uncertainty based or some metric, cross-view metric localization. And they also have a recent work like called slice match. I think it's accepted this year, CVPR geometry.
Oh yeah. Yeah, I see what you mean. I was mostly just trying to show which one was the first in this topic, and then just ours for. But just to add. Yeah. There's many more at this year's CVPR that also address. I think slice match actually is at this year's CVPR.
Yeah. I had a question. You said you did. You have results on zero shot. Which ones were those? So you trained it where maybe you can get it in the chat. Is it X?
Yeah, I'll show you. Here. So this was this was without zero shot. So basically the setting where we've already seen the test aerial images, and we get images from the same vehicle in test and train split. And then this is both cross area, meaning generalized to unseen aerial images, and cross vehicle, meaning generalizing to unseen vehicle setups. And this is basically the zero shot setup in this case. And the same setting is also down here when we have multi cameras. The So this is basically the line that's most interesting because we are in a cross area and cross vehicle setting, which we want to be. And we also use all of the cameras, which gives us the best performance. So this is kind of the line that shows us the performance we can get mostly. Yes.
Stable. So you are using the LiDAR, right?
In this table, I'm not using LiDAR. This is just the vision-based methods.
Showing some points, what are the yellow points?
Yeah, so in the visualization here, the model doesn't use the LiDAR points. They're only shown for visualization because the LiDAR points are basically the best kind of thing you can have to qualitatively assess how well the geo-registration matches up with the environment. So that's why I include the LiDAR points as a visualization, but they aren't being used by the model.
Oh, okay. So, I mean, many steps in your method. It's not clear what's in summarize with the main steps. So you're solving geo-localization problem. One is from top view, other is from the ground. And what are the main steps?
Well, the main step is, I mean, we can disregard the data thing for one. So the main step then is just our model, which we can see here. This is basically the model that we designed for this task. And this is the main model that can do cross-view geolocalization. The only problem is that we need data to train this model on, and this is why the whole other stuff came into existence. But this is basically the model and the main contribution in this regard.
I was not clear what exactly is this presentation about. We talk about old method, but the new data set.
No, new method, new data set.
New method, new data set.
This, we don't publish any data, though this is public data here. Yeah, we're using these 7 public data sets, so we don't gather those, we just collect them from and combine a common interface and then data from the aerial image providers.
The new data is the combination of combination.
Yeah, combination of existing public data.
Okay, so image-based geolocalization, and if I want to implement your method, what do I do? What are the main steps? Is it a global, like I compute features, one feature vector for each image, match them, or points?
No, this is not global, or this is not a global. Yeah, this is for the case. This is not global as in where we would do image retrieval. This is for when we already know roughly where we are, up to, let's say, for example, 100 meters. Like when you have a bad GPS sensor on board and you know you're like here, but not exactly where. And then you can apply this model, because in your local search region, it gives you the exact pose of your vehicle. So location and orientation. So that's the aim of the method. And the input, of course, then is the surround you cameras as well as the orthographic map.
We are finding the orientation.
This is for precise location. This is for precise location, not like within a meter kind of accuracy.
But I mean, you can compare with the bigger thing, right? That's just.
But it's in the bigger is for retrieval more.
Yeah.
Actually, so basically it's region based, and you do like a metric localization. Like you already know that it's in 50 meters. Then we just want to know where exactly in the 50 meters. But yeah, I mean, because you have, I see you have requested the orientation information from bigger data set.
Yeah, I tried actually on bigger ones.
Yeah, I guess since it's a pure vision based, they can actually try on bigger. So
I have tried, so I trained that on bigger.
Yeah, but didn't show the result.
Yeah, well, that's the problem I talked about earlier, is that you don't know how good the geo-registrations in Vigor are up to less than a meter.
Yeah.
So I mean,
Vigor has ground truth from GPS.
Yeah.
So that's not that accurate.
Maybe the errors can be like 2.5 meters, but it should be fine.
But I mean, it
depends. Typically, only GPS and accuracy is not highly accurate.
But
it feels like I close inside to people. So it depends on how accurate it is, right?
Yeah. I mean, as there are still some methods like evaluating on the bigger for the metric localization. since you have the result, I think maybe you still put it there. Maybe
It was,
not.
I got it after publishing
Yeah,
everything.
yeah,
I just-
yeah,
yeah.
I understand. Yeah, I was just saying. Since you
Yeah,
asked another.
Yeah, so thanks for the talk. So two questions. So explain a bit more about the last one. So this is the core comes down to this precise illustration.
I mean, this part?
Yeah. So explain this.
So first of all, we choose a search region where we want to find our vehicle in. That is three-dimensional because two translation search dimensions and the rotation angle as well. So 3 dimensions. And then we pick a grid of hypotheses in the search region. So we get like, let's say 1,000 hypotheses that we want to test on. And for every such hypothesis, the first thing we do is we transform the bird's eye view feature map using the known hypothesis into the coordinate system of the aerial image. So then we have an overlap between them and can just compare the features to find out, to determine the likelihood score for this given hypothesis. This is what we basically do for all of the hypotheses, determine the likelihood scores, and then those basically give us the output probabilities. The only important thing here is that we can jointly evaluate multiple hypotheses using the cross-correlation operation in the Fourier domain. That's what makes it work very performantly. Yeah.
You rotate every image before you do the cross correlation.
Yes, the cross correlation covers only different translations. So we repeat the cross correlation for several discrete rotation angles.
You could solve for them together too, right? Instead of just relying on discrete steps.
I'm not sure.
If you only rely on discrete cross rotations,
Yeah.
then there'll be some inaccuracies.
Yeah, it is a discrete output. So of course you can say that since it's discrete, there might be some inaccuracies, but even for the translations, but I guess once your angles are close enough together, or the translations are not close enough together, then the error that you can get from that is like really small from the discretization error. Yeah.
It's very nice work.
Thanks.
I really like the visualizations as well, where you can see the location between the center lane markings.
Yeah.
The accuracy of the methods. I was wondering, so you've used the LiDAR basically for the manual correction, but then the task is image-based visualization, right? So of course, you cannot really compare them, but based on your experience, what would you say is maybe for the future the more interesting connection? Should we actually be using LiDAR point clouds because that's what you use visually yourself?
So LiDAR points work a lot better. Like this serial labeling model that I'm using, I don't have exact numbers, but it's far less than a meter in accuracy. And the vision-based one, I guess there's more work to be done to improve it to get to far less than a meter. So,
what would you consider for the future doing a sort of a similar approach, but then using the LiDAR from the vehicle sequence?
Well, that is what the serial labeling model is.
Well, exactly, it's making that your key methods. Right?
Oh, I see what you mean. Yeah, I might at some point. Yeah.
Makes sense, maybe.
Yeah.
Thanks.
I thought they say they're very expensive.
Yeah. That's actually what I want to add that. So the work he did is so valuable because the LiDAR actually, the self-driving car company, if you look at the PD, those LiDAR, when they create that, those LiDAR is very expensive. So although it's more accurate, but using the camera-based approach, right? Now the research direction moving closer to accuracy wise. So you actually can provide local solution.
Yeah,
That's why this work is very valuable. Okay, final question. Okay.
This.
So wondering why on the upper side, you see this huge gap between your 1 meter to 3 meter result. And then suddenly 3 meter to 5 meter. Is it some form of because you're mixing up the data sets, right?
This is evaluation only on port AV. So
Is there something to do with the type of GPS they use and accuracy of the ground truth? Because you could see immediately from 1 meter to 3 meter, is a huge jump. And 3 meter to 5 meter, the same gap in terms of meters, in terms of GPS ground truth, but there's not that much of a change in the network. Is there something to do with the ground truth of the board data set that is a bit less than 3 meters, kind of jumping around?
So the longitudinal direction, that's where it looks very similar along the street, so it looks very similar, and that's why.
Might be one.
Yeah, but I'm wondering why, when you look at 1 meter recall, it's 6% accurate. When it goes to 3 meters, suddenly it jumps up and this, the delta.
Yeah, because
is very small.
it's longitudinal, it's along the street.
Yeah.
So when you go along the street, similar nearby, when you go 3 meters or 5 meters, it looks very different. I think that's why.
Might be.
I may be wrong,
Yeah.
but that's why.
I don't have an explanation for it.
Okay, so let's thank speaker again. Yeah. We'll have a coffee break. We'll come back and see.
Yeah. I didn't mean to
Yeah,
rob you of the citation, but
Yeah, I was just asking because you requested like the orientation information. I was just
Yeah.
asking, so what's the result? Maybe
Yeah,
I
yeah.
just,
if I recall correctly, it's like between one or 2 meters or
yeah,
something.
yeah.
So
I
that's
mean, yeah, because if you're like you can have an error like less than 2 meters, then maybe it's hard to evaluate on bigger. But if you got a error higher than that, because right now I'm seeing that the current papers are still have errors like higher than maybe 4 or 5 meters. Yeah, maybe that's, yeah,
Siemens now is roughly 1 meter
roughly 1 meter now.
in this new paper.
Okay,
So I think the location accuracy for the ground truth of figure is less than 2 meters. I think it's quite accurate.
yeah, because it's I mean that's collected by the Google.
I think Google
car.
did some pre-pros
So
or
basically-
post-processing.
But the thing is, we don't know, right?
Yeah.
This is the
That's,
hard
that's the
part.
point.
Yeah.
And with the lighter
Uh,
points, you do
no,
know.
actually, yeah. So I just provide the GPS, but we didn't know how did it generate the GPS. But basically, it's from the Google, the car driving on the street. Right? Their GPS should be pretty accurate.
You could do some landmark annotations to verify the accuracy. If you annotate in both
Yeah, we
views
can
some
try it.
landmarks for like 50 images and do some projections, then you could estimate the location in the satellite image using the ground truth or using the ground image, and then you can check whether it's really accurate or not.
But I think there's even with the Google car, there's the problem like what location are we measuring there, right? Is it like the base link of the car? Is it the GNSS module inside the car or the camera itself?
Yeah.
And once we get to this sub-meter accuracy,
Yeah.
these kind of differences start to matter.
Okay. Okay, thank you very much for coming. My name is Yi Jiaxi, a research fellow from the Australian National University. During the past few years, I have been working on ground-to-satellite image-based localization. So today I'm excited to sharing our works with you. The topic today is autonomous vehicle localization by leveraging off-the-shelf satellite images. And the works are collaborated with sorry, I have problem with it. Yeah, it doesn't work. Okay. Yeah, the works are collaborated with Professor Hongdong Li, Dr. Xin Yu, Dr. Dylan Campbell, and Dr. Liu Liu. The task we have been discussed many times today. Just let me have a brief recap of the task. Given a ground image captured by a camera at a ground level, and we want to localize where this image was taken with respect to this large satellite image. Based on the application scenarios, we can divide the cross-view image-based localization into two categories. The first one is cost-level city-scale localization, and the second one is how to increase the localization accuracy once a cost, location, and orientation has been determined. For the cost-level city-scale localization, we will describe two scenarios. The first one is an easy scenario, localizing orientation-aligned panoramas. And the second one, we will discuss a challenging and more practical scenario, how to localize images with unknown orientation and a limited field of view. For the increasing the camera pose accuracy, we will first discuss two progressive works from our group, exhaustive search and pose optimization, and two works from TU Delft, localization with uncertainty estimates and geometry guided slash match. Okay, let's first look at cost level city scale localization. The task is usually formulated as an image retrieval problem. Namely, given a large satellite map covering the whole city, we will first sample grids on the satellite image, and then split the large map into small patches centered at the grids. In this way, we can construct a satellite image database covering the whole region of interest. Given an image captured at the ground level, we call query image. We compare its similarity with every database satellite image and retrieve the most similar one. The GPS information of the retrieved satellite image is then approximated at the query camera's location. Since this task is formulated as an image retrieval problem, it is usually solved by deep metric learning techniques. Namely, we first employ two branch CNNs to extract global descriptors from the ground and satellite image separately. And then a triplet loss or a contrastive learning loss is applied to train the neural network by maximizing the similarity between the matching ground and satellite image pair, while minimizing the similarity between non-matching ground and satellite image pairs. Okay, since the viewpoint differences are too significant, there are some, the task is very challenging. The challenges include significant domain differences, and also different imaging modalities, and so also unknown orientation and limited field of view of the ground camera, and limited localization accuracy by the image retrieval formulation. In this talk, we will discuss our works to solve this challenge one by one. Let's first consider the easy scenario, localizing orientation aligned panoramas. This is a ground and satellite image pair. Can you recognize these two images are from the same place? Okay, now let's describe the clues. The query image is a 360-degree panorama. When the orientation of the two images are aligned, let's use the red arrows to denote the aligned orientation. We can find that The ground image tells us there are trees along the 0-degree orientation. And also when we look on the satellite image, we also observe trees on the 0-degree orientation. When we rotate our heads to positive 90 degree and negative 90 degree orientation, we can observe roads on the ground view image. And correspondingly, we can also find roads on the satellite image. When we continue looking at other correspondences, we may also observe the 2 small white roads on the ground image and on the satellite image. Those information we have talked about is the spatial layout information of the seen objects, and they are very useful for the cross-view image matching cross-view localization problem. Sorry. This is our first work, optimal feature transport that tries to encode the spatial layout information of seen objects and also handle the cross-view domain differences. Similar to previous works, we first employ 2-branch CNNs to extract deep features from the 2-view image separately. However, the extracted features are different from each other. When we backpropagate these features to the original image, we can see that they highlight the same scene in the 2-view image, the road part. How can we address the cross-view domain differences? We introduce a cross-view feature transport module. This cross-view feature transport module maps the ground view features to the satellite domain. And after this transport, the ground view features are much more closer to the satellite features. This is a high-level idea. And the cross-view feature transport module is designed inspired by the conventional optimal transport theory. The optimal transport is proposed to find the optimal transport plan between 2 probability distributions. The optimal transport plan P is the transport plan, corresponds to the minimized transport effort when transporting from source distribution samples to target distribution samples, and the cost matrix C measures the transport between each source sample to each target sample. In this cross-view image-based localization task, we want to expose the relationship between the ground view features and satellite features. Thus, we generalize this optimal feature transport from distributions to features and define the transport plan P and cost matrix C to be between ground view features and satellite view features. As seen in this equation, the cost matrix C is the most important thing. Instead of handcraftedly design a cost matrix, we resort to neural network to regress for the cost matrix C for each ground view image. And the regression network is learned statistically from training. And we employ an entropy regularized optimal transport plan because it formulates the objective function strictly convex, and thus it can be solved by a sinkhole normalization efficiently. The sinkhole normalization applies row normalization and core normalization iteratively, and the final obtained matrix corresponds to the optimal transport plan P. According to the computed transport plan P, we can transport ground view features to the satellite domain. This is a cross-view feature transport. Let's continue in discovering other correspondences between the 2 views. Interestingly, we found that a circle on a satellite image approximately corresponds to a horizontal line on the ground view panorama, when the depths of the seen objects in this circle are similar for all the points. And the inner circle corresponds to bottom lines on the panorama, and outer circle corresponds to top lines on the panorama. Inspired by this, we introduce a polar transform by unrolling the concentric circles to horizontal lines and obtain a polar transform satellite image. It can be seen that after the polar transform, the satellite image is much more similar to the ground view image. This is the overall architecture. We apply the polar transform on the satellite image as a pre-processing step, and then extract deep features. To further construct the cross-view correspondences, we also introduced a spatial aware feature aggregation module. This spatial aware feature aggregation module generates masks to highlight the correspondences between the two views. This example we show here highlights the road correspondences between the two views. This is a visualization of localizing orientation aligned panoramas. The first column shows the query image, and the following columns shows the top 5 retrieved satellite images from the database. Green border here indicates the center of the retrieved satellite image is within 5 meters to the query camera location, while red border shows the center of the retrieved satellite image has a larger distance than 5 meters to the query camera location. This is for localizing orientation aligned panoramas. And next, let's discuss how to localize images with unknown orientation and limited field of view. This is a satellite image and its 2 corresponding panoramas. At our first glance, the 2 panoramas are very different, but they are captured at the exactly same location. When we further restrict the field of view of the ground cameras, we can see that the captured content can be totally different when the camera orientations are different. For example, totally opposite to each other in this case. How can we embed features for the 2 totally different ground view images and mix them match to the same satellite image? To address this challenge, we introduced a dynamic similarity matching module. Recall that the polar transform has presented the satellite image in the street view panorama coordinates with its horizontal lines corresponds to the azimuth direction or the yaw angle direction. In this case, we can compute the relative orientation between the ground image and the satellite image by a spatial correlation. Specifically, we use the ground view features as a sliding window and compute the inner product between the ground view feature and the area feature across all possible orientations, namely the horizontal axis. This generates a similarity score between the ground image and the area image at each possible orientation, indicated by this red curve. And the orientation corresponds to the maximum similarity value corresponds to the potential orientation alignment between the query image and the satellite image. If the satellite image has a limit, if the ground image has a limited field of view, we then crop corresponding regions from the satellite features. This is a cropped feature, and we use this cropped feature for similarity matching or ground image localization. In this way, we can handle the orientation misalignment between the 2 view images and also limited field of view of the query cameras. This is the overall architecture. After extracting feature descriptors from the 2 view images by CNNs, we apply this dynamic similarity matching module, and the whole network is differentiable and end-to-end training. Here we show some qualitative visualizations on orientation estimation. For each ground image, we estimate a similarity between the ground and the satellite image at each possible orientation, and the orientation corresponds to maximum similarity is regarded as the potential orientation alignment between the 2 view images. On the right, we show the quantitative evaluation of the orientation estimation accuracy. It can be seen that when the ground image has a larger FOV, for example, 360-degree or 180-degree, the localization accuracy is very high. This ground to satellite image-based localization for orientation estimation actually has a limitation. It cannot handle scenes where large symmetry exists, for example, in those images. When a person standing in a scene like those images, they are hard to determine their orientation purely based on a satellite image, because the scene contents along both directions on a road are similar. Here is a visualization of localization result for orientation unknown image. For each query image, we not only retrieve its similar satellite image from the database, but also compute the relative orientation between the ground image and the retrieved satellite image. Thus, we can obtain 3DOF camera pose estimate. We have discussed different methods for image retrieval for city scale localization. However, this image retrieval formulation actually has a limitation, is that the localization accuracy of ground image is poor and usually based on the sample density of the satellite image. How can we increase the localization accuracy or the camera pose accuracy by ground to satellite image matching once a rough location and orientation has been determined? Okay, 4 works will be introduced here. And the first one is exhaustive search. Recall that in the image retrieval process, we can retrieve the most similar satellite image from the database. And based on the sample density of the database, we can determine a rough region of the ground cameras to be on the satellite image. And next, we densely sample every point in the predetermined region and determine which point should be most likely to be the query camera's location. Let's first show an overall process of this localization. For each point in the predetermined region, we project the satellite image to the ground view. And when the projection points are different, the projected images are different with each other. Among all the projected images, we find the most similar one with respect to the real query ground image. And the projection location is regarded as a query camera location with respect to this satellite image. In this process, we use SSM, the structured similarity, as a similarity measure because it is much more robust than L1 or L2 distances in handling the cross-view domain or color differences. When the query image has a limited FOV and unknown orientation, we apply the same dynamic similarity matching module introduced previously. Simply replace the feature maps to original image and the similarity measure here to SSM measure. Here is the visualization for localizing orientation unknown panoramas. The last column shows the orientation unknown panoramas, and the first column shows the top one retrieved satellite image. According to the satellite image center, if we approximate the satellite image center as a query camera location, we project the satellite image to the ground viewpoint. It can be seen that the projected images are different from the real observed ground view image, indicating the center locations are incorrect. By using our method, by using our estimated location and orientation, we project satellite image to the ground viewpoint. It can be seen the structures are much more similar to the ground view image. In this slide, we show the localization results for orientation unknown images with a limited field of view. The last column shows the query image, and the first column shows the top one retrieved satellite image. Similarly, we first project satellite image to the ground view according to the satellite image center. The projected image, the visual content are different from the query ones. By using our estimated location and orientation, the projected images are similar to the query ground ones. In this process, we use a satellite to ground view projection module. Actually, this work was conducted in 2020. At that time, we don't have a training data set with ground truth labels. Thus, we use handcrafted features. Thus, the projection is based on the ground plane homography. Also, we don't have an evaluation dataset with ground truth GPS. So, okay, here is an illustration. This is a matching ground view image and satellite view image provided by the dataset. According to the GPS location of the ground and satellite image provided by the dataset, we project satellite image to the ground view. However, the projected image is different from the query one, indicating the GPS location is incorrect. Thus, we resort to user study for the evaluation. However, given a query image and a satellite image, it is hard for our human to determine which pixel on the satellite image corresponds to the query camera location. But instead, if we are provided with a projected image at a given location, we are easy to determine whether this location is correct or not by comparing the similarity between the projected image and the query image. Thus, users are provided with a query image and a projected image at the GPS location and a projected image at our estimated location. They are required to determine whether the GPS location is correct or our estimated location is correct, or both are correct or neither of them is correct. Here are the evaluation results. The left two bars are for localizing for localizing panoramas, and the red three bars are for localizing images with a 180-degree FOV. The cyan color here indicates both GPS locations and our estimated locations are correct. The light green indicates GPS locations are correct. Light blue indicates our locations are correct. And the red bars indicates that users cannot determine which location is correct. It can be seen that our method can give a relatively higher accuracy on location estimation. This method has a limitation. It cannot handle severe occlusions between the satellite and ground view image. For example, in this case, this is the image projected at the GPS location, and this is the image projected at our estimated location. Which location is correct in this example? In this example, the GPS location should be correct. As seen in this image, the middle pixels corresponds to tree canopy, and those tree canopy occlude those road pixels underneath. When we imagine those are road pixels and also leveraging other surrounding visible content, we can find this image is similar to the query image. However, since the tree canopy pixels are green and they are different from the road pixels on the query image at corresponding positions, the SSM value between this image and the query image is low. In contrast, the SSM value between another projected image at a different location and the query image is high, because the middle pixels of both images correspond to road, and those pixels occupy a very large portion on the image. In this case, our method fails. Then some natural question arise. The SSM similarity measure is not very effective. Can we replace it by a better similarity metric? And the exhaustive search is very computationally expensive. Can we replace it by a more sophisticated search strategy? The answer is yes. The SSM value similarity measure can be replaced by higher level feature similarity, and the exhaustive search can be replaced by pose optimization. This introduces another work published in CVPR 2022, pose optimization. Let's first have a high-level idea of this work. Given an initial pose estimation RNT can be obtained from image retrieval or noisy GPS sensors, we first project satellite image to the ground viewpoint. Next, we can construct an optimization objective, the feature differences between the projected feature and the real observed ground view feature. We want to find the optimal pose RNT such that the feature differences are minimized, and we implement this optimization by an LM algorithm. The objective of the LM optimization is the feature differences between the projected image FS2G satellite to ground projection and the real observed ground view features. The LM optimization first compute a Hessian matrix and Jacobi matrix with respect to the pose parameter, and then update the pose iteratively. The whole process is differentiable, and thus we can encode it in a network feedforward path and train the network end to end. This is the overall architecture. We first employ feature extractors to extract multi-scale features from the ground and satellite images, starting from the closest level. Oh, there is some distortion on the symbol. Yeah, starting from the closest level, we first project satellite features to the ground view domain according to the pose, initialized pose. Takes into the feature differences between the predicted features and the real observed ground view image. And LM optimization is employed to estimate the relative update on the rotation and translation. And then this updated pose is sent to a final feature level. We project the satellite features to the ground view image, ground viewpoint again, and employ the LM optimization again and iteratively from cost to fine, and then loop until maximum iteration number or until convergence. Here we use a cost to fine update procedure. That is because when the initial camera pose is too far from the ground truth camera pose, the projected features according to the final feature level will be significantly different with each other. In this case, a local minima is likely occurred. Instead, features at the cost level have a larger receptive field on the original image, and thus is much more suitable for global search in the solution space. And features at final levels have a larger resolution and encode more detailed information of the original image, and thus it is more informative for fine-tuning local search around a local minima. Thus, we implement this cost to fine and then iteratively. This first cost to fine and then iterative procedure allows our network jump out of local minima during this optimization process. The network supervision is applied to the final predicted pose by the LM optimization, and the pose signal will be back propagated to the original image and update the feature extractors. In a whole pipeline, only the feature extractors contain trainable parameters. Other blocks are all trainable parameter free. This is the satellite to ground projection. We will not go to details of those equations. One thing I want to say here is that we don't explicitly estimate the height map of the satellite image or the depth map of the ground view image in the projection. And this is to ease the burden of neural networks and the main overlap between overhead view and ground view on the ground plane. So we try to use all features from the ground plane for this localization purpose. Also, instead of apply this projection on the original image level, we apply it on the high level feature level, because features have a larger receptive field on the original image and encode higher level semantic information, and thus can somewhat tolerate the height ambiguity of the scene objects. In this work, we also introduced we also supply satellite images for 2 autonomous driving datasets. It's Kitty, sorry, I have a typo here. It's Kitty and for the multi-AV. For Kitty, we also construct 2 test sets. Test 1 is a same area evaluation. Specifically, the images from test 1 are from the same area in the training dataset, while images from test 2 are from a region that is totally different from the training dataset. And the fourth multi-AV dataset contains 6 different trajectories. The training and testing images are captured at different dates. Here is the evaluation of our method on the Kitty dataset. Satellite image can only provide 3 DOF camera pose of the ground camera, namely the 2 DOF location and 1 DOF orientation. 1 DOF orientation refers to the azimuth angle or the yaw angle of the camera. To better understand the performance of our method, we decompose the location estimation to lateral pose and longitudinal pose separately. The longitudinal pose means the driving direction of the cars, and the lateral direction means the direction perpendicular to the driving direction. Here we can observe that our method performs better than previous works, and also the lateral pose performance is better than the longitudinal pose. Here is a evaluation on the Ford multi-AV dataset. And now I want to explain why the lateral pose is better than the longitudinal pose. Here are the two examples. The first one is from urban area, and the second one is from the highway area. In the urban area, the longitudinal pose of the vehicle can only be determined by the facade information of the buildings. However, this facade information is not visible in the overhead view. Thus, we have an ambiguity along the longitudinal direction. But the lateral direction pose can also be successfully estimated because the road edges are visible in the overhead view. And similarly, when a vehicle is driving along a highway, the scene along the driving direction is very monotonous, and thus it is hard to determine the longitudinal pose of a vehicle. We expect that this longitudinal pose can be combined with SLAM or view-based techniques. SLAM and view can provide a better longitudinal pose estimation, while cross-view image matching can function as a novel loop closer for SLAM and view techniques. Here we have some ablation study comparison between LM optimization and SGD, stochastic gradient descent, and ADAM. SGD and ADAM are well-known and effective optimizers in neural network training. From this table, we can see LM performs significantly better performance than SGD and ADAM. This is because LM is an adaptive second-order optimization algorithm. It is essentially guaranteed to find at least one local minima in the solution space. However, the SGD and ADAM suffers the usual zigzagging behavior. Thus, it is hard to find the global optima in a limited iteration. We also conduct experiments comparing LM optimization with a neural network-based optimizer. Interestingly, we find that the neural network can provide a better rotation estimation, but inferior translation estimation compared to LM optimizer. We have suspect the reason is that neural networks are not inherently to rotations. A small rotation on the network input will be magnified on the feature differences. Thus, the feature differences will give more power to the neural optimizer to find a correct rotation alignment between the two input signals. However, CNNs are inherently translational equivariant to translations. And due to the aggregation layers in the network, the small translation on the input signals will be absorbed in the high-level features inside the optimizer, and thus it cannot provide a promising translation update. This actually should introduce our another work. It's an ongoing work. We can obtain very high performance on the rotation estimation, about 100% here. I hope that I can share that with you in the future. Yeah, it's an ongoing work. Here are some visualizations. The red point and arrow here indicate the camera location and initialized camera location and orientation. And the purple dot indicates our intermediate updated location by LM optimization. And the final green dot and arrow indicate our predicted location and orientation. The blue dot and arrow indicates the ground truth location and orientation. Next, I'm going to introduce two works from TU Delft, supervised by Julian Kui. The first one is visual cross-geometric localization with dense uncertain estimates. It is published in ECCV 2022. The high-level idea is that given a ground image and a satellite image, the network produces a probability map of the possible camera locations with respect to this satellite image. Compared to the previously deterministic pose estimation, this probability map actually can be multimodal. It highlights all possible camera locations on a satellite image. And this probability map can be used for temporal verification or fused with other sensors to achieve a more robust localization performance. This is the architecture. After feature extraction, we can split the satellite feature maps to n by n subvolumes. And for each volume, For each volume, we can embed a global descriptor for the subvolume. And similarly, we can embed a global descriptor for the ground view image. Then the query descriptor of the ground view descriptor is matched against the n by n satellite descriptors. In this way, we can create a coarse location matching score of the ground camera. Next, we concatenate this coarse matching score with the original satellite features and pass it to a decoder. This decoder upsamples this coarse matching score to a fine-grained localization heat map. The training loss is a combination of a triplet loss on the bottleneck and a cross-entropy loss on the final network output. Here we show some visualizations. For each ground image, the network produces a probability map of the vehicle locations. When the scene is ambiguous or contains symmetric scenes, the model highlights all the possible locations. For example, the roundabouts in the second image. And in the third image, the model is unsure where the camera is, but it is sure the camera is along a road. So pixels, all pixels along the road are highlighted. Another work by the same group is slice match, geometry guided aggregation for cross-view pose estimation. This work, the previous work only estimates location of the ground camera, but this work estimates 3DOF camera pose of the ground camera. The underlying idea is to explore the geometric or angle correspondences between the two views. Namely, for centered at the ground camera location, each triangle slice in the satellite image corresponds to a vertical slice in the ground view panorama. It's angle correspondences. Then the model extracts slice descriptors for each slice on the satellite image and each slice on the ground view image. The final descriptor is a concatenation of the slice descriptors. During the inference or network feedforward pass, the model first sample a set of candidate locations. The points indicate candidate locations and a set of candidate orientations. For each candidate pose, the model extracts a feature descriptor of the satellite image. And then compare the ground view descriptor to all the satellite descriptors corresponding to different pose candidates and find the most similar one. Yeah, this is the overall architecture. The network takes input as a ground image, its matching satellite image, and a set of pose candidates. For each pose candidate, we first generate a mask on the satellite image and highlight the region inside the camera's field of view and extract a global descriptor for the highlighted region. The network output is a global descriptor for the query image and a set of global descriptors for each of the selected candidate pose. The query global descriptor is matched to the satellite descriptors and find the most similar one. The corresponding pose is regarded as a query camera's pose. This is the poster information. It's a CVPR 2023 paper. If you are interested, please go to their poster session, and their authors are here. So if you have questions, welcome to ask later. As the last of this presentation, I want to present a work of satellite to street view panorama synthesis. The task is that given a satellite image and a precise camera location, can we synthesize a panorama as if the camera is on that location and looking around? Yeah. Once this task is successfully solved, it can be potentially applied to many other downstream tasks. For example, cross-view localization we have discussed. However, this task is very challenging. The challenge includes severe occlusions between the satellite image and the street view panorama. Seeing objects that are visible on the satellite image may not be visible on the ground view panorama. And also different imaging modalities the satellite image has a parallel projection, but the street view panorama has a spherical projection, and also the seasonal or weather differences. To solve this problem, we propose a geometry-guided GAN. The geometry is to model the 3D information of the world, and GAN is to handle the seasonal weather differences. So here we show the correspondences of the two-view image. The satellite image, the projection between the satellite camera and the satellite image plane is a parallel projection. It maps all points at the same spatial location but different heights to the same pixel on the satellite image. The street view panorama has an equirectangular projection. Its horizontal lines corresponds to the azimuth angle phi, and its vertical lines corresponds to the pitch angle theta. When a 3D point in the world is visible in both views and its height is determined, there is a determinist mapping between the satellite view image and the ground view image. And thus, we want to estimate the height of the satellite maps. For this purpose, we introduce a new representation, multi-height plane image. To be specific, we model the scene as a set of planes parallel to the ground plane, but at different heights of the scene. This multi-height plane is actually inspired by the multi-plane image in the conventional novel view synthesis work. Each plane has 4 channels, including 3 RGB channels and 1 density channel. Density channel indicates whether the point or the voxel here is opaque or not. To leverage this representation for satellite to street view projection, we introduce a geometry projection module. Specifically, we first estimate a height distribution from the satellite image across the sampled height planes. However, pixels on the satellite image usually corresponds to the topmost points on the scenes. If we only use these points, we cannot handle the occlusion problem at the street view. In order to handle the occlusion problem, we also model the points below the top structures by set them also opaque. And this is achieved by accumulate the height probability distribution from the top planes to the bottom planes. And in this case, the bottom plane, the ground plane, will always be opaque. And then we convert this overhead view MPI to a cylinder MPI because the panorama, the horizontal axis of the street view panorama corresponds to the azimuth angle. And this cylinder MPI can sort the points from near to far to the camera. And then we stretch the concentric cylinders to planes to convert it to a street view MPI. And then we can render a street view image from the street view MPI from far to near. This projected image or rendered image accurately recovers the scene geometry from the satellite image. However, the details, the appearance details are missed because of the discretized sampled height planes and also the resolution difference between the satellite image and the street view images. And then we use a generator to solve for this problem. The overall pipeline is that given a satellite image, we first estimate height probability distribution from it using a U-Net architecture. Given this probability distribution and the satellite image, our geometry projection module models the 3D scenes and render a street view image. This street view image is then used as a condition to be fed into the generator, and the generator synthesizes realistic street view image. The supervision is a reconstruction loss and a GAN loss. We don't have explicit supervision for the height probability distribution. Instead, it is learned statistically from the training examples. Here we show some visualizations. The second column shows our estimated height maps. The wider, the higher. It can be seen that the road is lower than the trees. The third column shows the projected satellite image by our geometry projection module, and the fourth column shows the synthesized image by our network. The last column is the ground truth image. Here we show some estimated height visualization on urban areas. It can be seen that the buildings has been estimated as higher than the ground plan. This demonstrates that our model is able to learn a statistical relative height among thin objects. Here we compare our model with or without height estimation. The second column shows an ablation variant without height estimation. It can be seen that in that case, sometimes the models ignore objects with higher height, for example, those trees, and don't synthesize them in the ground view image. Instead, by using our whole model, we can recover the trees from the satellite image. This is a comparison with other works on another data set. This column shows our estimated results. It can be seen that the geometry by our method has been successfully covered, and even for the learn line, which occupy a relatively small pixel on the target image, we can successfully recover them. And this is a comparison with previous works on complex things. Our method can generate more faithful results. We actually have another work for video-based localization. The idea is that a single camera contains less information, while a video can contain more information. That is likely to have a better localization performance. But due to time limit, we will not go to the details here. And also there are many other related cross-view localization works we haven't covered in this tutorial, but some of them are covered in other tutorials. And we encourage interested readers to read their original papers. For the future works for satellite image-based localization, I have several thoughts. For example, currently, most works using a single camera for localization. We can extend it to a multi-camera system, which is a common scenario in recent autonomous vehicles. And also we can use sequence continuous video as a query image. Also, we can enrich our database. We can not only use satellite image, we can also use ground image. And we can combine the cross-view localization with other modalities, techniques like LiDAR, radar, SLAM. And also the cross-view localization task is challenging is that it is hard to obtain very, very accurate ground truth pose for the ground camera. So it may be deserved to research for self-supervised learning or weakly supervised learning, unsupervised learning to solve the camera localization task. Yeah, that's all. Thank you. Any questions? Yeah. Yeah. Yes, our result is on Kitty. It's not Kitty 360. Oh. Sorry. Cool. Maybe let's stop share and we. Sorry, 1 minute. It should be okay. Maybe let's stop share and then restart it. From current slide. Yeah. Okay. Yeah.
Right. So here D plus 1 is 5%, right?
Yes.
And 5% on the KPA. You were doing without which was in the 90s, 70s, 80s, pretty high numbers. Right? I'm trying to understand what's the difference between the two techniques. In his technique, he was looking to a bird's eye view.
Yes.
And he was learning 3D.
Yes.
Right?
Yes. Yeah.
You're taking the bird's eye view. The network. In your case, you were doing a projection method, but you're doing it flat and just using essentially data on the ground plane.
Yes. Yeah.
That's why there's so much difference.
It's one of the differences. We only consider the ground plane, so it somewhat ignores the objects higher than the ground plane. And the other is that we use a optimization algorithm. So optimization not usually, is likely to get stuck in local minima. But in Florence's work, they synthesize an overhead view and densely search every possible location of the ground camera by a special correlation between the synthesized BEV feature and the satellite feature. Thus, it is a dense search algorithm. Thus, it can guarantee higher localization accuracy.
It's very fair to go
Mm-hmm.
ground to bird's eye view, or from satellite to
Ground view. Okay. I think, from my understanding, when there is a relative larger distance between the initial pose or costly estimated pose to the ground camera satellite image center, we suggest to use ground to satellite projection because the dense search can quickly restrict the camera to be in a local region of the ground camera. But once in the local region, we suggest satellite to ground projection because scene has a relatively larger resolution on the ground view image, but smaller resolution on the overhead view. When conducting ground to overhead view projection, we actually absorb or missing some details of the scene in the overhead view. But when we conduct satellite to ground projection, we can magnify the detailed information on the image, and thus satellite to ground can provide a higher localization performance. Yeah. Yeah. You mean the number of training images? Oh, okay. The channels in the overhead view multiply image. We use 32. Yeah, 32. The hole is 20 meters. We model 20 meters height. Yeah, and actually we found that when we use different numbers, 32, 64, 96, the performance is similar. Yeah, so we suspect that this even 96, there is the gap between two plans are also high. So from the network perspective, it can handle those. Yeah, or let me say, if we can increase the height plan to very, very dense, the performance may increase. But due to the GPU memory, we cannot increase that. So at the current level, GPU accepted sampled plan number, there is not much difference. Mm-hmm. Actually, our baseline is pixel to pixel. It's no geometry projection, just input a satellite image and output a ground view image, and use GAN training to train the network. The second column shows the result. Yeah, since there is no explicit geometry formulation, it usually hallucinates the things on the ground level. Yeah, by using the geometry, we can recover them faithfully. The second column actually use semantic map as additional guidance. Thus, sometimes it can achieve better performance compared to the baseline. Yeah. Yeah. Yes. Okay. Yes. Okay. Our method doesn't have the ability to handle the weather. We don't have an input. If you tell it is sunny or is cloudy something, we don't have this. We don't have this ability. Instead, the network tries to learn a statistical weather of the target image. I mean, if the training image contains all sunny images, it will likely to produce a sunny image. Yeah, yeah, mean weather. Yeah. Uh-huh. Actually, this is a weakness of this task because only from the satellite image, we cannot determine the elevation of the ground views. Sometimes it can be small mountains, but from the overhead view, we cannot recognize this. Yeah, so our model always produce a ground plan, similar to the ground plan, but yeah, it cannot handle that. Yeah. Yeah, Ted, I think Ted can answer that. Mm-hmm.
But the idea was to say that they use a transformer. Yeah. But yeah, they do explore the relation why the ground is corresponds to why it's from the ground to the idea that it was one of our inspirations. And you use informatics, they didn't use informatics. They used informatics for different. We used the web problem.
Yeah, relates also to the question that was earlier about extracting the geometric information and using that in the matching. Yes, that's at least the same idea that we try to use in the question it was sort of exactly these things where how do you capture that information, include it in your feature description. But I think there are now quite a few works that are trying to do something. Right. It would be interesting to compare the other does. Yeah, so I think you're a big all these works, right? Is that we have these data sets and they're still not really converged standard benchmark. Yeah. So I think bigger was for us at least a very important starting point. But also with comparing the results, we found it was, I don't know, I used to think about it, but it's very depending on the data set, what kind of results you get. So we thought bigger would be easier with 360 degrees than Ultra Robocar, which is a big field of view. Yeah. Ultra Robocar is actually way simpler because it's a smaller area. So it really depends. It's hard to compare results across data sets.
Yeah, I think so. Different data sets have different challenges. Yeah, the Vigor, we usually think Vigor is relatively easier because it concerns 360-degree panorama. It contains much more information, but the geometry projection is not really. We don't know the actual geometry projection because we don't know the camera parameters of the ground view camera. So this is a difficult on the bigger data sets. Yeah, for the autonomous driving data set, we currently have 3 or 4. So Kitty and for the multi-AV, Kitty is relatively easier because the scene is very diverse. It has highway, it has residential area. Yeah, but for the 4 data sets, the scene is rather ambiguity along the highway and usually have multi-lane line. Yeah, it's very ambiguous. And also for the 4, we also have an Oxford data set, right? Yeah, the Oxford. Yeah, go ahead. Yeah. Yeah. Yeah, and also for the TT360, Lauren may have some idea. I haven't researched this data set. Okay. Yep. Okay. Thank you.
Yeah, let me okay. Let's try this. No, okay, got it wrong. Yeah. And can ask him to share. We'll also test the audience. Okay, I think he's sharing. But how do I can change the
Can you see your screen and my voice is clear?
To which view is the best one? Speaker?
No, it's okay as long as people can see it. But I want
here is
make sure that we can hear from the speaker. Not here. Is your audio on?
Yes.
Yeah. Make it. Yeah.
Can you hear me?
Let's see here. Okay, he's speaking, but I cannot.
You cannot hear, right? That's
I'm not sure, but my microphone is actually on.
okay.
Yeah, maybe change another one. Maybe I can up here.
Did you hear me?
Yes, I can hear you.
Oh, okay. Now it's working. Yeah. Hold on. I'm going to put you on the projector. Hold on.
Sure.
Okay, so you're on the projector.
Okay.
Okay, we can see your slide.
Okay.
I'm sorry about that.
Okay. Did you hear me?
So, yes,
Okay,
I
then
can
now,
hear you.
okay, yeah, I think now you can start. Yeah, I think now we put you on the projector and we can hear from you.
Okay.
Okay.
So thank you very much. So my name is Vikas. I'm currently assistant professor at Information Technology University, Lahore. And good afternoon, everyone. And I'm here in Pakistan. At the moment, it's 4:35 a.m. in the morning here. So I'm going to talk about some recent work about the learning disentangled geometric layout transformers for the cross-view geolocalization. Our team include Shozan and Shingli, Safan, and me. The three of guys are from the University of Vermont, and these are some pictures from our campuses. So I think you guys are already heard a lot about the geolocalization today, and as well as about it before. But I will just take a couple of slides to just for the purpose of completeness to go through the basic introduction. So given the query image, we want to geolocate, find the longitude, latitude of the image in the geolocation. So when we say visual geolocalization, which means that we are interested to design techniques which can be applied to locate an image or object at a large global scale. So usually we are interested in image geolocalization or the object geolocalization. Also, there is some work on the video geolocalization as well, but most of the work is about image geolocalization. So the image geolocalization, we have the two types of approaches, whether single view approaches and the cross view approaches. And the single view will basically have, again, satellite image geolocalization and the ground image geolocalization. So in the ground image geolocalization, we want to predict the global position of the ground images, and the satellite image geolocalization, we want to predict the global position of satellite imagery. Similarly, in the cross view, we have both availability of both ground and satellite images, and we want to predict the global position of the ground images. For the object geolocalization, again, there are two series of work, like ground view object geolocalization and the satellite view object geolocalization. And the purpose of both is to have the global position of the objects in the ground images and the satellite images respectively. Just for the purpose of completeness, when we say the visual geolocalization, we usually don't mean that we are looking at the large scale. We mean that we want, for example, for the object geolocalization, we want to predict the position of the object in the local neighborhood. Similarly, the camera pose estimation, we want to predict the pose of the camera locally. And similarly, the SLAM, where we want to construct the map of the surrounding, typically in the real-time environment. Okay, so in the ground view, we have the similar, ground view images where we want to locate, match the Curie and the reference images, and to get the geolocation. And the cross view, we have the drastically different views, and we have the Curie images, which are the ground view, usually the panoramic nowadays, and then we have the reference images with the satellite imagery. And similarly, for the object geolocalization, we want to geolocate these objects. And this is very useful for the autonomous driving, for the management, on the survey purposes, for the generation of automatic maps. And as you know, that there's a huge, there's a lot of challenges in the cross-view image geolocalization. And one of the few of the main are the drastic view changes, capturing time, and the resolution. For example, here, even this Curie images, the map and match should be done with this image, which is apparently quite different. Okay, so one of the few of the limitations in the recent work that we observe are that the performance of the cross-view geolocalization methods degrade drastically as we move from when we do the training and testing of the different data sets. So when, for example, training of the CV USA and the training and testing of the CV US CAT, then there's a huge drop in the performance. So we want to analyze that, why is this happening? And also we observe that there's a lack of ability to extract the spatial configurations of the visual features. And they usually in the model overfit the low level details, and that's why it performs does not perform very well across the data set. So but the key idea here was to explicitly disentangle geometric information from the raw features and learn the spatial correlation among the visual features from the aerial and ground pairs. And this was recently accepted in the AAAI. So, and basically we propose GeoDTR, which generates a set of geometric layout descriptors, which captures the relationship between the different features in the globally within the image. Also, we analyze the effect of the data augmentation from the improved cross area, cross view geolocalization. And we observed that the simple data augmentation can help drastically improve the cross view geolocalization. And finally, we used counterfactual based learning and an extra signal, and observed that it also helps improve the geolocalization, especially the cross view geolocalization. So here is the overview. So given the image, and we have the proper augmentations. So given the CNN, extract the features from the CNN backbone, for example, ResNet 34 or ResNet 18 or whatever. And then we have the geometric layout descriptors. So given the features R that we get from the feature map that we got from the CNN backbone, we got using the geometric layout descriptor, we got the feature vector P. And using the for performing the Frobenius norm, we get the feature vector F, and then finally we applied it the counterfactual learning paradigm to get the feature vector descriptor P, and we use it for the finally for the feature matching. So here are some details of the geometric layout descriptor. So given the raw features vectors, feature map extracted from the CNN, we applied max pooling across the channel, and then using the embedding layer, we actually map project this M into the K spaces. And then we get the using the index position encoding, we get the feature vector embedding vector E. And finally, we use the transformer encoder layer to explore the correlation between the E, and then following the embedding layer, we get the feature vector P. Similarly, given the R, we using the geometric layout descriptor, we get P. And what we did here is that we apply the Frobenius norm to get the feature vector F. So here is the thing that we try to generate a fake feature vector F, and in our experiments we did is that we sample it from the random distribution, and then we get this feature vector P dash, which is actually has no relationship with R. So here we have the R, which we are getting from the CNN, and it is passed through the geometric layout descriptor. We get P, so they both are related. But here we don't have any relationship because this is actually just randomly generated. And we do the Frobenius norm, and we do produce vector F cap. So this is actually the real feature vector, and this is a fake feature vector, and we use we try to maximize the distance between two, and this is basically use an extra signal to get the better feature map learning. So one other thing that we observe for the data augmentations stuff, that some of the previous work what they are doing in the augmentation, that they're applying the augmentation randomly between aerial and the ground images. So what we want to say here is that these aerial and the ground images have the geometric relationship. So the augmentations should not destroy that relationship. So whatever augmentation we are going to apply in the aerial images, for example, we want to rotate the aerial images, we should apply the ground images by the same rotation. And for example, we are going to flip the aerial images, we should apply the flip the ground images like the same. And the other thing is that if, for example, we are going to apply the augmentation like crop, so we basically want the network to to forget the low-level details here in specific example and to learn the global information. But we know that in the cross-view geolocalization, the low-level details are also very important because there's a very challenging problem. We don't want to, we really want to learn the generalized descriptor, but we, on the other hand, we also don't want to lose the low-level details. So for that, we basically name this augmentation like the layout simulation. Basically, we want to generate unseen layout by having the two observations, like generated aerial and ground pairs should keep the correspondence, and the generation process maintains the low-level information. So basically, what we did is that we, given the aerial images, and we had the polar transformed aerial images, and it is a ground image, we apply the rotation, the same rotation on the both images. So if we rotate these aerial images by the 20-degree, we rotate this polar transformed aerial images by the 20-degree, or the ground images by the 20-degree. And if we rotate it by the 90-degree, we rotate by the 90-degree, and so on and so forth. And also we flip the images by the same, we apply the same flipping to the both images, aerial and the ground. So we apply the, in the implementation, we actually use the combination of flipping and rotation. And we observe that if we keep the geometric correspondence during this augmentation process, it helps improves the performance across specifically in the cross area cross view geolocalization. Okay, and similarly, this is the traditional augmentations that we applied. So we applied different brightness, contrast, saturation, Gaussian blur, and the grayscale, and just to learn the robust feature vectors. So the main idea here, augmentation, while applying the augmentation, is that we should not destroy the the geometric information while applying the augmentation. If we do that, we will not able to get the very good accuracy, specifically when we have applying it across the data sets. Okay, so these are the training objectives, which are just like patients, and here the implementation details. So we have used the ResNet 34 as a backbone, and for the descriptors, we use the K8 descriptors for the geometric layout descriptors. For the dataset purposes and experimental purposes, we use the CVUSA, which contains 35,000 training pairs, and we use CVACT, which has the similar training pairs, but it is much more challenging because the number of the testing pairs is huge, which is around 92,000. And for the variometric, we use the traditional evaluation metrics, which is R1, R5, R10, R1%, which means that will consider it to be a correctly geolocate if the match image is among the top 1 or the top 5 or the top 10. So here are a few examples, and the leather here means that we applied polar transformation. So for the CVUSA, for the same area, the simple methods either have the state-of-the-art results or very close to the competitive method. Similarly, for the CVACT, we again without layout simulation, which means that without augmentation and with augmentation here, and you can see that here we have around 2 or 3% improvement. So this simple method where we have tried to capture the geometric layout of the scene and apply these simple augmentations, we get 2 to 3% improvement in the accuracy. But the real magic actually came for the cross area, cross view geolocalization, where, for example, when you train on the CVUSA and test on the CVACT, we get around 10% or 5% improvement in the accuracy. Similarly, when we train on the CVACT and the test on the CVUSA, we get the similar huge, like for example, 12% improvement or something like this across the data set. So since we observed that this simple augmentations helped improving the results, we applied that augmentations with the previous method like SAPA and the LPLTR, and observed that it helps, in the most of the cases, helps improves the results as compared to without geometric, without transfer augmentation. Here are some of the evaluation studies. We tried different, as I mentioned before, we tried a different layout segment, layout simulations, which means that we tried different augmentations, we tried different descriptors, we tried without counterfactual loss and with counterfactual loss, and we observed that all the components that we have are actually contributing to the accuracy, and this is more dominant for the cross area geolocalization. So we also observe visualize the learned descriptors, and we see that like when we have, for example, this is the ground image and this is the polar transform aerial images. So, and this is the difference between the descriptors, and we observe that there's a very little difference between these two descriptors, which means that the descriptor is actually learning some useful patterns and to learn to the cross boundaries between the ground and the aerial images. We applied the similar stuff like given the ground images, we have these descriptors, and then we have the aerial images, and then we apply the polar transform to the feature map, and we observe the similar pattern here. So in summary, what I discussed so far is that the geometric layout GeoDTR, which captures the geometric information from the raw features to better capture the cross boundaries between aerial and ground images. And we discussed that layout simulation and semantic augmentation, which means that while applying the augmentation, we should keep the geometric structure intact. So it helps improving the generalization, and also like the controversial phase learning mechanism helps better grasp the better spatial configuration and therefore produce the better results. So so one of the limitation here is that we are using the panorama, and if we see here the panoramic view is quite limited. For example, here's the pictures from the San Francisco and the images from the mapillary. You can see that the green area is the locations where the panoramic images are available. And the right side, you see the limited field of view images, which means they're captured by dash cam or the mobile phone or the other handheld devices, and the huge data is available. So which means that as of now, we want to geolocate some location. This panoramic images are not that much useful at the moment because they don't cover the whole area. And this thing is actually more prominent in the other developing countries. So for example, in several countries, you even with a very specialized engine, you don't get very good panoramic views, and the panoramic images are very noisy. Where available. So so this leads to the second part of my talk, which is actually about the cross view image sequence geolocalization, and that was published last year, perhaps this year in the backpage. So so the main idea here is that we want to locate the images, but the panoramic images is not that much available, so we actually rely on the limited field of view images. But but as we know that the panoramic images have too much information there because they're the 360 views, but the limited field of view images have very limited information. So to extend that, we actually use the sequence of images so that we can capture as much information as possible, and these sequence of images are readily available as is shown on the right side of the graph here. So we basically propose to geolocate the sequence of limited field of images instead of panoramas. So when we started working on this at that time, we were not aware of any other work for the video sequence geolocalization. So we collected our own data set from the state of Vermont, and so basically discovered the 500 kilometer road in the Vermont, and the various areas like urban, suburban highways are covered. So these are some of the visualization on the right you see of the coverage area. So the basically dataset contains around 100,000 ground images, and we using that we form the satellite sequence pairs, and I will tell you the details how we made that pairs. And we do not explicitly keep the panoramic images in the dataset, so that because we just want to focus on the video sequence geolocalization. So, so here are some of the examples from the data set. So these are the sequence of images from the different areas in Vermont, and these dots basically shows the locations from where these images are captured. So, so for example, we have the cars turning around. We have within the city and the suburb area, and in the traffic scenes and like that. So also this is also some other examples. So so this data set is quite diverse, and we try to capture the real world scenario as much as possible. So for the because these images that we have are the continuous sequence for the several hundred kilometers. So the purpose of the benchmarking and to make the data set and make it publicly available for the other people to work on this, we basically make a sequence of the few images for each corresponding satellite images, because we're using the zoom level 19. So we're assuming that we are driving in this direction. So given the given the first location, we keep capturing images, and until the distance is greater than some threshold, which is in our case 50 meters. So we crop that sequence and make it one sequence in data set. Similarly, we start from the middle of the second sequence and the first sequence, and keep capturing the images here, and so on and so forth. So so each for the training data set, we have actually the 7 images which correspond to the one satellite imagery. So as you can see here so this is something. So this is something like this. So we have the 7 images, and these are the corresponding satellite imagery. And the number 7 is not a magic number. We just come up with we just want to capture the sequence of images within one satellite imagery. So that's why, and we observed that this is around 50 meters. So we actually stick to that. Okay, so given the sequence, input sequence, which is the ground level images, we actually extract the CNN features, and then we use the temporal feature aggregation module, which is the transformer, to get the features, and then we do the average pooling. And similarly, we get given the satellite imagery, we get the features. We use the soft margin weighted triplet loss to run the embedding space, so that the distance between these two feature maps is reduced. So one of the challenges which can happen in the real scenario is that because for the training purpose, we can use the benchmarking and use for example, exactly the 7 images for the training purposes which have in our data set. But for the testing purpose, because you have to try in the real world, you never know. We can lose some images. For example, some frames are dropped. So to simulate that thing during the training, we actually drop some of the images during the training purposes. So for example, this is showing the random mask, where basically we have the 7 images, and we randomly drop first and 6 images. So we are not using the information during the average pruning. We are not using the information from these 2 images. Similarly, for example, here we are dropping the frame 2, 4, 5, 6 here, and just using the 2 other frames. Similarly, we're dropping frame 6, and so on and so forth. So, so during the testing, we actually check out the various scenarios where we actually tested the whole sequence, like of the 7 images, and also we tried the different variable length of sequences during the testing, so to simulate the real world environment. Okay, so so the baseline methods, we actually try to simulate the SAFA and vigor on our data set. So using the center images, so this experimentations are performed on our data set, and but the method are used like SAFA and vigor. And the evaluation metrics are the same as before. Okay, so so here are the experimental results. So when we tried this without a sequential dropout, which means that we don't care about whether the images we drop the images during the training or not, so we don't have that much good accuracy. But when we have this use the sequential dropout, we have the better accuracy. So here the thing is that the claim is not that this method is superior from SAFA and vigor, but the claim is that because we are using the video information, so that's why we are better. And and if the method is designed such that SAFA and vigor also use that in the video information, then they can also perform well. So the main idea here is that we want to exploit the video and the correspondence across the frames, and as compared to using only the single limited field of view images, is the sequence is useful, as shown by the results as well. So here are some of the evaluation studies. So we actually during the training we drop different number of images. Sometimes we drop 1 image, only drop 1 image. Sometimes we drop 6 images during the training, and we observe that if we increase the number of the dropout images, which means that the method is robust enough, we get the better accuracy. And here we actually tried with the different parameters of the transformers and observed that in our case, and these parameters works quite well. So during the to evaluate that the real example scenario, these are the graphs which basically shows that we tried variable length during the testing. So for example, here it means that the testing during the testing we drop all the images except the only one image. Here the length 3 means the sequence is random 3 images and the rest are dropped. Here all 5 images and the 5 all 7 images and the 5 images, and so here is the overall the training results. As you can see here is that when we train with a sequential dropout, as we decrease the length, the accuracy does not drop that much. So but if we decrease we don't use the training with sequential dropout, we actually get the sharp decrease in the performance. So which means that if we take care of this frame dropout during the testing, during the training, our results are robust during the training as well. So here are some of the experimental results, qualitative results. And so we given the Curie image. This is the Curie sequence, and these are the top 5 predictions. So these are some of the best results we have. But you can see here is that these all these images looks very similar to each other. Here are some of the more results. So these are the query sequence on the left, and the actual matched images here. Our method doesn't perform very well, but still it's okay. And these are some of the results where we have actually our top 5 images among the top and the last 5, and so on and so forth. And definitely we have there are several. The accuracy is not still very below from the real world application. So we definitely have a lot of challenges in the mathematics as well. So what I presented so far is that we discussed the cross-view image geolocalization sequence, and we have this and the new data set there, which is basically is publicly available, and we observed that using the spatial dropout technique helps to regularize the model, which can better present the sequence of the different length. So all the codes that I discussed are available, publicly available, and the data is available. Okay, thank you very much. Any question, please?
Okay, so for any question, I would suggest that just come to here, let just talk directly that to discuss. Yeah, so he can hear clearly. Any question? Yeah, okay, just come here, yeah.
All right, can you hear me?
Yes, sure.
Okay. Thanks for your nice presentation. I was wondering if you can reflect on, so your approach of integrating temporal information is using a transformer. But if the classical approach in robotics is to do something like a Kalman filter or a particle filter, where you track the vehicle and you integrate multiple sensors, right? So do you think there's a benefit of using a transformer over one of these classical models? Or why would you learn how to integrate the temporal information?
So one of the obvious answers is obviously because when you have the learned features, they perform better because you have the more. I mean, this is just the traditional answer, like, and because you have the more data to learn, and you have this loss function which is specifically designed for your application, and because the Kalman filter like the other handcrafted methods, so they're very good, and actually they works pretty well, but you have to work on top of that to design to handcraft it, and the mechanism to do what on top of that. But here in the we actually learns those features to so that it can have I mean, here we, for example, here basically you learns those features so that it can perform well across it can automatically learn the information from the sequence. So this is overall.
So that I understand, but I wonder, is there a trade-off, or do you observe some trade-off, or for example, in a particle filter, you have the ability to represent ambiguity, right? That you could be, if you don't really know where you are, and you have also the option to still integrate other type of sensors. So is this, I don't know the answer, right? It's a very open question, but is this a useful trade-off?
Yeah, right. So this is obviously and okay. So this is just a second. Just give me a second, because my son somehow appeared from somewhere. Okay.
Your son. Okay. It's Father's Day.
Okay, really sorry. Actually, it's 4 a.m. here, so my son appeared from somewhere inside, and I was hiding.
it's interesting, the results for this technique.
Yeah, so really sorry for the trouble, because I keep stopping him from coming here, and he just appear from somewhere. Okay, so I agree with you, like the about the Kalman filter. You have the flexibility, you have the control over the problem, and the particle filters and the Kalman filters. You can design the different the objective functions and the different modalities. I agree with that. But here, I think that the main benefit here, which we are looking at, we don't have the multiple informations here. So we just have the images, and we want to learn automatically from there.
Okay, thank you.
Thank
you. Any other question? Okay, so let's thank the speaker again, especially that he presented remotely at the early morning at his local time. Yeah, so we appreciate it. Yeah, thank you. Yeah.
Yeah, I actually wake up whole night so that I don't sleep at the morning time. Thank you much.
All right, thank you.
Thank you. Bye.
Okay, bye. Okay, and I think this is our final talk. So we hope this tutorial that today that I think I heard a lot of discussion, a lot of brainstorming. So as CJ mentioned, I think hopefully this is the first step that toward that a lot of communication, convergence of different data set, different approach that in this area. So to us, I think now is an exciting time that in this area really move toward the real world application, even the large scale applications. So we appreciate that you joined today's tutorial. Okay, thank you.
And if you go to the tutorial website.
Yeah, okay.
You have it handy.
Probably not.
Okay.
Okay, I can just search again. Okay, so just go to the website. Huh?
Just go back to Google.
Go back to Google.
Yeah, search cross-view or something.
No. We have a we have a long name.
Yeah, sorry that I couldn't know. I think that was what we wanted to.
Okay. Anyway. Yeah.
And go to project.
Yeah.
And go down.
Okay.
Yeah. Now, for all slides and videos are there.
Yeah.
So anybody wants access to it.
Yeah. So basically, we have all the slides and pre-recording video. Yeah. For all the talks. So all the materials are online. Yeah. Okay. Thank you. Yeah.
I like your rank transformer method quite a bit to do the retrieval, and because it's trying to, you're bringing instead of ransack, you're bringing it inside.
Yeah. Make it into.